It was, at this moment, CodeWebby knew. Things hadn't gone entirely according to plan. I'm going to start with interpolation. Inter meaning between, as in international waters between countries, or intercity rail between cities. Poles are the extremes. It's nothing to do with that country between Germany and Russia. On screen you have two axes of a graph with no labels, which would horrify Randall Munroe, and a whole lot of data points. Those data points are very clearly close to some kind of straight line. In fact, you can very easily draw a straight line through them. It looks like that. There is a gap in the data points left of center. I can zoom in and show you this gap in the data points right there on the screen. But given the data available, assuming that is a large sample of the available data, it is reasonable to assume that any more data you gathered that fell somewhere into that gap would also be fairly close to that straight line. That is interpolation, and it is entirely valid. Well, here's another set of data, also obviously aligned pretty much along a straight line. So you could draw a straight line through that, and this would be valid. This is one of those complicated sets of data in which you have one group of points that are very close to one straight line, another group of points very close to another straight line, and some additional points that aren't really close to either of them. We could color code these. I can adjust the zoom slider just to make sure the screen has actually updated. Color coded, at the top we have 3 red dots that are just above the rest of the data, a whole group of orange ones that are pretty much along that upper straight line, 5 green dots in the middle that are neither on the orange dots line nor on the blue dots line, but in between them, a whole lot of blue dots along that lower straight line, and a couple of indigo dots at the bottom that are below all the others. And this is something you may see in some context in reality, is data that tend to fall onto one of 2 trends, which I can draw in for you there, and I can also zoom in and zoom back out so that the screen actually updates for you, I hope. And you can have data that are mostly grouped along those trends with what we may as well call anomalies, anomalous results. The red, the green, and the indigo, which are neither orange nor blue. Then there's this data set. This is one of those trick question data sets for which you should not be marked down. This is a set of points that are very clearly along a straight line. I know they're along a straight line because I wrote a program to plot the points along a straight line, or extremely close to a straight line. It has a little if line in it. If they're really close to the straight line, draw them. If they're not really close to it, it doesn't draw the point. But it's not actually a straight line. It is the points that happen to be very close to a straight line along a sine wave. Like I said, trick question. Dirty trick. You shouldn't be marked down for not recognizing that as a sine wave. Here's another data set. Not very many points this time. There weren't very many points last time, which is how it was possible to have uncertainty about whether it's the straight line or the sine wave. Here you have very few points, but they are not spaced out along the sine wave. These are along a straight line, right? Well, to the left, they're above the axis rather than carrying on below it. But you could draw in this straight line. You could do that. You could say, at least the data that are beyond that point to the right are all pretty much along this straight line. That's great. There's your trend. What you're doing here is not interpolating. You're not drawing a line between the dots at the extremes of the data set. You're drawing a line beyond them, outside those extremes, outside your data set. This is extrapolating, and sometimes it's entirely valid. Like the t-shirt says, there are two kinds of people in the world: those who can extrapolate from incomplete data, it's perfectly valid to extrapolate that the others are those who can't. But here you have this data set of, again, no labelled axes. This is just some arbitrary data, and actually knowing what the axes are would help you guess whether or not that straight line extrapolation is valid. Having more data can also help you guess whether or not the straight line extrapolation is valid. At this point, it's pretty obviously not valid, because that's a curve. Now those ones that are along the axis rather than below it, they look like they're part of the same trend. It's a curved trend. Allow me to draw in the curve, just incredibly crudely. It looks even worse when I zoom in and the pixels get to inconsistent sizes, but there is a roughly hand-drawn curve matching that larger data set. And that is a better match than the straight line was, but is it correct? No, it's not correct, because here's a more complete data set, and it turns out it's an S shape, not an exponential. Y is not x squared or x cubed. Y is somewhere on this curve. And this is a curve you may actually see in real-life science. For example, you get 52 cages. You put 20 rats into each cage. Each cage has identical bedding, toys, food and water, and places to hide, and high and low platforms in it, and so on. Everything a rat needs. They're all in the same warehouse, climate controlled. They all get the same lighting, they all get the same air quality, they all get the same temperature. Everything's the same. After 1 week, you get one of your assistants to prepare several dilutions of a particular drug in salt and sugar solution. So you have a standard salt and sugar solution which has the same concentrations as rat's blood. Into this you add 1 nanogram per litre, 10 nanograms per litre, 100 nanograms per litre, 1 microgram per litre, 10 micrograms per litre, 100 micrograms per litre, 1 milligram per litre of this drug, this substance that you are testing. And then you have multiple bottles of each of those dilutions. Maybe you have a dozen of the just sugar and salt water with no drug added at all. And then that leaves 40, and you have 10 different dilutions, so you have 4 bottles of each dilution. You get 2 decks of cards. You shuffle 1 deck of cards and deal them out face down to those bottles. You shuffle the other deck of cards and deal them out face down to all the cages. Then you flip all the cards over, and this is how you know which bottle goes to which cage. Then, after 1 week, or on the Tuesday of week 2 or whatever, another assistant weighs all the rats. Just goes cage to cage weighing the rats and injecting each rat into the muscle of the right thigh with 1 milliliter per kilogram body mass of the salt and sugar solution attached to that cage, without knowing what dilution that bottle is, because you've taken away all the cards. All they know is that that bottle goes to that cage. They have no idea whether they're injecting any drug at all. All the rats go into a holding cage. Once all the rats from that cage have been injected, they'll go back into their home cage, move to the next cage. This may take several assistants, for 52 cages, each of 20 rats. And then you continue providing them with food and water. That assistant should probably leave now, because the rats are going to remember being injected, they're not going to be happy about it, and they're likely to bite that assistant. But the assistant who only comes in to change their bedding and make sure they have food and water, they're going to be fine with that assistant. Rats know. They can tell who's who, This is the person that feeds them, this is the person that stabs them. They bite that one, not that one. After a week, hopefully every day you'll be removing any dead rats, but keeping track of how many there were. After a week, you might find that in your control groups of a dozen, that's 240 rats, you have lost 6 rats, 1 in 40, which is 2.5%. of your rats. If that drug has no lethal effect on rats, doesn't kill rats, you would expect to have 97.5% survival in all the other cages. But when you actually add up all the totals in all the other cages, you've got 80 rather than 100, so percentage is going to be not quite as simple as counting rats. You find you have lower numbers in some of them, including much lower numbers. And what you plot on a graph like this, across the x-axis at the bottom, is the dose they got, which is because you went milliliters per kilogram and your dilution was nanograms per litre. This is now, well, if it was a 1 microgram per litre and you injected 1 milliliter per kilogram, this is now 1 nanogram per kilogram would be the dose per kilogram of rat. Across the bottom, this could also be the concentration of something added to the drinking water in that cage. It could be the concentration of something in the air if you're able to isolate these groups of cages into separate tunnels with different air supplies, or something in the bedding. But it's a dose or a concentration across the bottom. And up the y-axis on the left is the percentage of the rats you would expect to survive that didn't. So if 2.5% of them had died in the control cage and in this test cage, well, it's the same result in both, so the drug apparently made no difference to how many died. If 2.5% of them died in the control cages, and this is going to be awkward to work out in my head, but 12.25% have died in this test cage, then 10% of the ones that you would expect to be alive in the test cage, 9.75% of the 97 of the population out of the 97.5% of the population you'd expect would survive, have died, presumably because of the administration of this drug. Therefore, you have a 10% lethality, which would be at the 10% mark on the y-axis and a dot for however far across the dose was. And when you plot all of these doses across the bottom and all the lethalities up the y-axis, you get a curve like this. And halfway up it, at the 50% lethality rate, is the median lethal dose, or LD50. You can look these up. There are tables of them all over the internet. Find them on Wikipedia if you like. And you can use this as an indication of how much more toxic something is. So caffeine has a higher LD50 than metallic arsenic, means caffeine is more toxic than arsenic, which is a rather scary thought. Water and sugar have quite low LD50s. Something like ricin, has very high LD50s, therefore very low toxicity. Something like ricin has a tiny LD50, like 20 micrograms per kilo, therefore very high toxicity. And then botulinum toxin, I think it's 3 nanograms per kilo, which is terrifying. Potent stuff. And rich women pay to have it injected into their face to kill their facial muscles so that they won't form facial expressions, so they won't wrinkle their skin. Yeah, that's smart. You can also get a dose response curve like this that is not a lethal dose response curve. It's a toxic dose where it didn't kill the rat, but it did cause all the rat's fur to fall out. Or it didn't kill your human patient in a hospital, but it did cause an increase in the daily level of headache they're feeling. If every hour while they're awake they record how bad a headache they have, you get a score for how bad a headache this person had in the week before they started taking a twice a day pill, probably. And then in the week after that, or in the 2 weeks after that, they continue to record how bad a headache they get. You will get a reduction or an increase in the score. If it's an increase in the score, that's a toxic response. If it's a reduction, it's a therapeutic response. And then maybe, toxic response was it turned their skin blue. Yeah, colloidal silver will do that to you. Don't take the stuff. But you can then have a reduction in headache caused just by taking a sugar pill, and a greater reduction in headache caused by taking 2 sugar pills, and an even greater reduction caused by receiving an injection of sugar water. That's the placebo effect. And compared to that, you would have a sugar pill that contains a certain dose of your drug, very carefully prepared by some very skilled lab techs to match each patient's body weight. So they're all taking the same sugar pill, but the sugar pill that patient gets has the right dose per kilogram body weight for that patient. Or you would use a standard pill and just adjust your results based on patient's body weight. So you plot each patient in the right place along the x-axis. But you will get a different reduction in headache, and that difference in the reduction in hourly headache score, average hourly headache score, will be your therapeutic effect. And you might have a percentage of patients whose skin reflects significantly less red and green light than blue light, or a lower ratio of red and green light to blue light than it used to, which is the number of patients whose skin has turned blue, and that would be your toxic dose effect. For an ideal drug, you want an ideal medicinal drug, talking about medicine here, you want something that has a very low, very low, an extremely low therapeutic dose, an extremely high toxic dose, and an absolutely immense lethal dose. You want something where you can administer this drug, and right up here in the top right of the therapeutic dose curve, 99.9% of patients do have an end to pain, or they do regain the ability to taste sugar, or they don't get cancer, or whatever it is you're trying to achieve with this drug, at a dose that is lower than the dose at which 0.1% of patients turn blue, or lose all their hair, or have a measurable increase in migraine headaches, or lose the ability to perceive green light, or whatever the toxic effect is. Now, if you get that, that's great, because you can start at that dose that's in between therapeutic for 99.9% and toxic to 0.1%, and you can step the dose down until symptoms reappear, then you bring the dose back up to where they disappear again, and that's the dose that patient gets, minimum cost, and you have never exposed a patient to a toxic dose. If the therapeutic and toxic dose curves overlap, you're going to have to start below the toxic dose, the TD low, toxic dose lowest, the lowest recorded dose that caused a measurable toxic effect. And then if that works, that's great, because you can even reduce the dose slightly. If it doesn't work, you have to increase and watch out for those toxic effects. And if the toxic effects start before the therapeutic effects, maybe that patient needs another much more expensive medicine. If you get to a therapeutic dose that doesn't have toxic effects for that patient, great. But if the two curves don't overlap, you don't have to worry about it. So there you go, a piece of genuine science that you may encounter. Also an example of why extrapolating in straight lines isn't always valid. So what prompted all this? What prompted all this was a question that came up on Quora. This question said that an archer, similar able, shoots an arrow at a target that is, I think it was 36 meters away, at the same height. Just say the target is at the same height as the arrow is released. And at a certain velocity, maybe 40 meters per second, maybe 50, I don't know what the number was. It was specified in the question. And he asked, at what angle should he shoot the arrow, what angle above the horizontal, to hit the center of the target? Now, this is not an actual attempt to help someone score a bullseye in archery. Should make that clear, you know. This is a mathematics examination question, probably GCSE, General Certificate of Secondary Education, age 16 when I went through, 15 in my case, brag point. I suspect this for two reasons. One is that this is not a question anyone has any good reason to ask on Quora. Like, hey, I'm at an archery contest, how high should I lift my bow to hit this target? No. And secondly, it's the name, similar able. I suspect similar able is what passes for a joke in mathematics papers. Might be at 16 plus, might be at 11 plus these days, might be A-level these days. We've had Tories in power. They're always bad for everything. I suspect similar able was drawn using similar triangles. Here is an illustration of similar able the archer, drawn using similar triangles. And here we have two possible angles of the shot. And you may have noticed that he is very badly drawn. You may also have noticed that he has tiny, tiny hips like Johnny Bravo. And you may have noticed that I have actually correctly illustrated how an archer changes that angle of shot, which is that the head tilts very little forwards and backwards, so little that I haven't bothered drawing the head twice, And the right hand, assuming he's a right-handed archer, stays in the same place relative to the head and barely moves at all. The left hand moves up and down. Now this is, and then way over here somewhere we have a target. I went to all the trouble of drawing it. Now this is a problem for this question, if the question was a serious attempt to help someone hit the target, because of course you're pivoting at the neck and at the forward shoulder, which is probably the left shoulder, to raise and lower the bow. But the arrow isn't released until the bow has gone straight. So it's released from the middle of the string with the bow as close to straight as it gets and the bowstring straight. That's where the bowstring very rapidly decelerates and the arrow carries on without it. So your release point actually changes height depending on your angle of aim. This is not accounted for in the question. So here's how to solve that for a GCSE or 11 plus mathematics exam. You're going to be given something in this at the top of the exam paper or the first page. It will tell you to assume that gravity is that. Straight down the page at 9.81 meters per second squared, or meters per second, or 9.81 meters per second every second, or write it how you like. They all mean the same thing. They mean the velocity of an object that is not supported by a light thin wire or a light inextensible string or a table will increase straight down the page by 9.81 meters per second, a velocity, for every second, making an acceleration. Certain other assumptions you make will give you this symmetrical parabolic arc. Now, this isn't actually a parabolic arc. This is a series of straight lines approximating a parabolic arc. Zoom far enough in, you can see them. At the centre, we have an apex A, at which is where the arrow is travelling exactly horizontally and exactly halfway between start or shooter and terminus or target. And what they want is this angle alpha between the horizontal line from the shooter to the target, somewhere above ground level, and the initial direction of the arrow's departure from the bow. And it's probably not going to be an angle that steep. Right. If we just look at the arrow's departure from the bow, we can describe its motion rather than a velocity at an angle, which is Ci combined initially at angle alpha. We can describe it as an initial horizontal velocity, Hi, and an initial vertical velocity, Vi. Horizontal initially and vertical initially in blue and red. If I fiddle with the zoom, I can be confident that you're seeing that on screen now. This produces a right-angle triangle with the horizontal velocity as the side adjacent to angle alpha and the right angle, the adjacent of alpha, the vertical velocity, the initial vertical velocity that is, as the side between the right angle and the hypotenuse, not adjacent to angle alpha, therefore the opposite of angle alpha, and the combined initial velocity, the combination of the horizontal and vertical initial components, as Ci, the hypotenuse of that triangle. Congratulations, you've just done vector addition. Sounds more complicated before you see it. Right, and we know some things about right angle triangles, or rather, to answer this question in the exam, you are expected to demonstrate that you know some things about right angle triangles. For a start, there's Pythagoras' theorem that the square on the hypotenuse is equal to the sum of the squares on the other two sides. Pythagoras was being unnecessarily specific. That comes up later. And that the sine of angle alpha, the sine of an angle is equal to the opposite over the hypotenuse. Sine alpha is initial vertical velocity over initial combined velocity. The cosine of an angle is equal to the opposite over the to the adjacent over the hypotenuse. Therefore, cos alpha equals horizontal initial velocity over combined initial velocity. How do we use those to solve this? Well, because we have that symmetrical arc, symmetrical parabolic arc, we can say that the time it takes to get from launch with its upward velocity of vi to going horizontally at the apex is the time it takes for gravity, g, that 9.81 meters per second that we were told to assume for this paper, to remove all that upwards velocity, and is half the time it takes the arrow to get to the target. So if we call t the time it takes the arrow to get from launch to target, t over 2, the time it takes the arrow to get to the apex of its journey, is vi divided by g. We can also say that d over 2, d the distance from the shooter to the target, is the distance it travels in half the time it takes to get to the target. Half the distance in half the time at a constant speed downrange. It's perfectly reasonable because you're given no reason to change its velocity on the map, only its downward velocity due to gravity. And you know that distance travelled is time multiplied by speed. In this case, distance travelled in a direction is time multiplied by velocity. So half the time, journey time, t over 2, multiplied by the initial horizontal velocity. d over 2 is thi over 2. And because we know that thing about sines, we can say that t over 2, vi over g, is sine alpha ci over g. We're just rearranging the sine alpha is vi over ci to say that vi is sine alpha ci. T over 2 is sine alpha ci over g. And d over 2 is t over 2 hi. So if we rewrite hi as cos alpha ci, we get d over 2 is sine alpha ci cos alpha ci over g. We can rearrange this a little to say that d equals 2 sine alpha cos alpha ci squared over g. Just move the 2 from the denominator on one side to the numerator on the other and put the ci's together to become ci squared. And then we rearrange that again to get sine alpha cos alpha equals dg over 2 ci squared. We are now most of the way to a solution. We have something about, some property of angle alpha that is defined in terms of the distance to the target you were given in the question, the g value you were told to assume throughout the paper when you read that cover sheet before you started answering questions, divided by 2, which is a constant, an integer, and the square of the velocity that you were told in the question. So we're nearly there, but we need to know what sine alpha cos alpha is. This is probably an identity you are meant to know to answer this question, but we can deduce it. We can in fact deduce sine alpha cos alpha. Using BBC Basic, I have a 21st century computer simulating a 1981 computer to run this code. Mode 2 is low resolution but has colour. Gcol1, means add light, turn on pixels, don't turn any off. And 2 is the green pixel. 1 is red, 2 is green, 4 is blue. 3 is 1 plus 2, so red plus green, so yellow. 5 is 1 plus 4, so red plus blue, so magenta. 6 is 2 plus 4, which is green plus blue, and therefore cyan. And 7 is 1 plus 2 plus 4, which is all three of them giving white. Here what we're doing is turning on the green pixels as we go. Move without drawing to 0,500, which is the left edge of the screen and halfway up. Just shy of halfway up. 4, this creates a for loop. Set a variable x to be 0 to 1280, which is the width of the screen. Step 8, we're going 8 at a time because we're in mode 2 and we may as well. The actual pixels on the screen are 8 pixel coordinates wide, so we go in step 8. Draw, which is draw a line from where we left the cursor at 0,500 to x, so we are in fact using x to go left or right across the screen, no surprise to anyone, come back 200 times, so we have an amplitude of 200. We're just scaling it vertically by 200 to make it easier to see. The sine of x over 200. I'm dividing x by 200, so every 200 across the screen, every just shy of a sixth of the way across the screen, is going to be 1 radian. Yep, plus 500 to put the 0 value, the x-axis, at just shy of halfway up the screen where we started. Next x says go back to the 4x equals line until you run out, whereas it's 1280. When it gets there, it's going to run past line 60. Next line, gcol 1,4, start turning on blue pixels instead of green ones. Move 0,700, we're starting at the left edge of the screen again, but we're starting 200 up, as in amplitude of 200. We are starting at the point on the screen that indicates a value of plus 1, because the cosine of 0 is plus 1. And then the same for x equals yada yada line. This time we're drawing to the same thing, but using cosine, not sine. This is going to create two waves, a green sine wave, a blue cosine wave. And those look like this. We have a green starting at 0. I haven't drawn the axes. Lazy of me, I know. I haven't drawn scales. Lazy of me, I know. Green on the left is starting at 0. It's going up to plus 1 at 1 right angle. Back down to 0 at 2 right angles. Down to negative 1 at 3 right angles. And back up to 0 at 4 right angles. 4 right angles being about 6.3 radians. We also have the blue cosine wave, which starts at plus 1. It is going down through 0 at 1 right angle. It is down to negative 1 at 2 right angles. It goes up through 0 at 3 right angles. It goes up to plus 1 at 4 right angles. Both of these are a circle. You can think of these as how far to the right and how far up from the centre of a wheel a light on the rim of the wheel will be as the wheel rotates clockwise. Starting with vertically at the top as 0. Right at the top at 0 degrees, as it starts to rotate to the right, that light is pretty much staying at the top of the wheel. It's not coming down much, it's obviously not going up, but it is very rapidly going to the right. As it gets farther out, how fast it's going to the right is going to slow down, and how fast it's coming down is going to increase until at 1 right angle, it is as far right as it's ever going to go, and it's going down as fast as it's ever going to go, currently level with the centre. As it continues to rotate, how far right it is starts to decrease faster and faster, and how fast it's going down decreases until at 2 right angles it goes under the centre, so it is 0 distance to the right, and it's at the bottom, so it's at -1 as far down as it's ever going to be. And then you repeat that coming up the other side. They are the same shape, just offset by 1 right angle, and in fact the value on the blue line is the gradient of the green line. Now we want to know not sine alpha or cos alpha, but sine alpha cos alpha. So at 0 right angles, the sine is 0, so the product is 0. At 1 right angle, the cosine is 0, the product is 0. 2 right angles, the sine is 0, the product is 0. 3 right angles, the cosine is 0, the product is 0. We have whatever shape we get is going to go through the axis, through 0, every right angle. In between, at half a right angle, 45 degrees, is where those two cross over. 45 degrees up and right from the centre of the wheel is quite obviously where the rim of the wheel is equal distance to the right of and above the centre. That's where the two cross. Go back to Pythagoras and you can work out how far. It's going to be 1 over root 2. So we have a sine of 1 over root 2 and a cosine of 1 over root 2. Multiply those together and get 1 times 1 in the numerator, and root 2 times root 2 in the denominator, so you get 1 over 2. At 3 half right angles, 135 degrees, 3/8 of the way around the circle, the sine has come back down to 1 over root 2, the cosine is negative 1 over root 2. So we have the same multiplication, but we have an odd number of minus signs, so we get a negative result. Negative a half. 5 half right angles is where they cross over again, the bottom left of the wheel, where it is a negative distance to the right and a negative distance above the centre. And there you have negative 1 over root 2, negative 1 over root 2. You have an even number of minus signs, so you're going to get a positive result. The value is back to being 1 over 2. And then 7 half right angles, you're back to having an odd number of minus signs, you get a negative result again. You can also think of this as the area of a square with horizontal and vertical sides, one corner at the centre of the wheel and one corner where that light on the rim is. As long as you don't mind the squares in the lower right and upper left quadrants having negative areas, because we're treating to the right and up as positive. The only part we're interested in, of course, is the first right angle, because similar Able is going to be shooting somewhere between horizontally forwards and vertically straight up. If he shot horizontally forwards, his arrow would immediately drop below the target, so that's no good. If he shoots vertically straight up, his target isn't going down range at all, so that's no good. Also, it's going to come back down on top of him, which is unhealthy. Somewhere in between them is the answer we want, in that first right angle. Now, we can check our logic by adding another line. Starting at line 110, turn on the red pixels, and this time do the same thing but plot the product of cosine and sine of x over 200. And we will be expecting this thing to go up to a maximum value of a half and a minimum value of minus a half, alternating at the half right angles, and to be at 0 at every whole right angle. There we go, the red line. And as previously mentioned, where red and green overlap, it goes yellow. So at very small angles, sine times cos is pretty much the same as sine, which you'd expect because the cosine is pretty much 1. And around one right angle, sine cos is pretty much the same thing as cos, which you'd expect because the sine is pretty much 1. In between, we do indeed have a maximum at half a right angle, a minimum at 3 half right angles, and 0 at every whole number of right angles. We can check that that red really is the same as the green by drawing it at twice the scale and getting a yellow line the whole way. Well, if red is the same as the green but half the wavelength and half the height, then red is 1/2 of the sine alpha cos alpha is 1/2 of sine 2 alpha. It's half as high, the red line on that graph, the red line there is half as high up from the 0 axis as the green line twice as far across the screen. Therefore, sine alpha cos alpha equals half sine 2 alpha. This is, there we go, sine 2 alpha over 2. We already know from our previous slide, earlier slide, that sine alpha cos alpha equals dg over 2 ci squared. Now we know sine 2 alpha is sine 2 alpha over 2 is dg over 2 ci squared. Well, for a start, we have a 2 in each of the denominators, so we can just cancel those out. Sine 2 alpha is dg over ci squared. We didn't want sine 2 alpha, we wanted alpha, so we're going to move sine from this side to that side. You can take a 2 out of the denominator and put it into the numerator on the other side. You have a divide by 2 on one side, it becomes a multiply by 2 on the other. In this case, we have a sine on one side, it becomes an arc sine, or inverse sine, or sine to the minus 1, or ASN in B basic, or ASIN in Python. And we get 2 alpha is arc sine dg over ci squared, and then we just move the 2 across. We get alpha is inverse sine of dg over ci squared all over 2. And that is a general answer to that exam question that you can apply to any form of that exam question, no matter what the distance, the value for gravity and the initial velocity are. You only have to solve it once, and then you just plug the numbers in for every subsequent iteration of the question. Now, based on those equations, we can also write this equation, just rearranging it differently, that d equals ci squared sine 2 alpha over g. This is the distance the arrow is going to travel before it drops back through the height from which it was launched, is the square of the velocity at which it was launched, multiplied by the sine of twice the elevation angle at which it was launched, divided by gravity. Now, those negative square areas you got before, if your angle is more than 90 degrees, you're going to be launching this arrow backwards, and that means you're going to get a negative distance downrange. This is distance with direction, a vector, not just distance, the scalar, which is how it can be a negative number. But this gives us something you should be able to test in a classroom or the gym or the sports field. You could build a Lego trebuchet to launch little steel ball bearings, or a big wooden one to launch medicine balls, and make adjustments to launch them at different velocities and different angles, and measure your results. You can also make a prediction based on this. Sine 2 alpha is going to max out at a value of alpha that is half of the value at which sine alpha maxes out, which is of course one right angle. So you would expect maximum range to be at 45 degrees. Now, we can make predictions based on that formula. It's very simple using BBEM. Here we are in mode 0, we get higher resolution, but it's just in black and white. Down the left we have a column of velocities in meters per second. Down the middle we have a column of colons, separating those from the inputs from the results. Down the right we have a column of ranges. 1 meter per second is a slow walk, and it's going a whopping 102 millimeters, which is not very far. It's about the size of a Burger King Whopper. 3 meters per second is... That's breaking into a jog there, and it's going 917 millimeters, which is 9 times 102 millimeters, and 3 times the velocity, producing 9 times the distance, is exactly what you expect from that formula, because d is proportional to ci squared. Let's jump to 9 meters per second, which is pretty much sprinting for a human. 8.257 meters, which is 9 times 0.917 meters. Again, exactly as expected. There are higher velocities listed here, all the way to 49 meters per second. I think you multiply by 2.37 to convert from meters per second to miles per hour. That's quite fast. That is, you do not want to get hit by a medicine ball at this speed fast, so you probably shouldn't be testing that one in the sports field and finding out whether or not it really will throw a medicine ball 2.5 football field lengths away. But the lower ones you could probably test. Now, if we run this again just with a different range of inputs, instead of 1 to 49, it's 51 to 99, or 151 to 199, we get more values. And again, I don't really recommend testing this inside the classroom. .99 meters per second multiplied by 2.37 miles per hour per meter per second is a pretty respectable speed for a World War II bomber. You don't want to get hit in the face by a medicine ball going that fast. Or a little tiny steel ball bearing going that fast, or a glass marble going that fast, or a World War II bomber going that fast. We have a value there, a range of 999.08 meters. That's quite a long way to try to throw a medicine ball. That's pretty much 1 kilometer. That is a long throw. In the bottom right of this screen, we have 199 meters per second, 4,037 meters. And I know this is wrong. See, under UK law, if you're over 18 with a clean record, you can own an air rifle without having to get a firearms certificate, without having to provide a, quote, good reason, close quote, for wanting to own it, without having to lock it up in a safe, without anyone inspecting how it's stored. You can have an air rifle and keep it under the bed or in your sock drawer or on the wall or whatever. And you can use it for blowing up squirrels. Perfectly valid use for an air rifle. On property where you have permission to do so, as long as you're suitably careful not to hit anyone's dog or any humans or any horses, or not to send pellets across the boundary. If you do try to shoot, say, a filthy, disgusting, disease-spreading feral pigeon that's an absolute ecological disaster off a tree branch, and it moves at just the wrong moment, there's a gust of wind, your sights have been shaken loose by that piston going back and forth, and you miss and just take a few feathers off. Your little airgun pellet ain't going to kill someone 4 kilometers away. It's still bad that you sent the pellet across the property boundary, but the odds of it coming down 4 kilometers away, going just as hard as it was going when it left the muzzle and drilling a hole in someone's skull are pretty tiny. Also known as zero. Unless there's a hurricane blowing through at the time or something. And that air rifle that you can legally buy is limited by law to 12 foot-pounds force muzzle energy. As long as it's below that, you don't need the license. If it's above that, you do. If it's exactly on that, get it tested again until you get a result that is either above or below. Because nobody wants to argue about the exact borderline. 11.95 foot-pounds force muzzle energy with a little 8.6 grain, which is slightly over half a gram, 177 pellet, requires a velocity considerably greater than 199 meters per second. And no way do those pellets go 4 kilometers. So this is obviously not right. It is even more obviously not right when you start at 700 meters per second and go 40 at a time. So somewhere here is 7.62 by 39 millimeter Kalashnikov, and then somewhere around here is 308 or 7.62 by 51 millimeter NATO, and then here's your 5.56 by 45 millimeter NATO, and somewhere there I think is 220 Swift, and then Remington or Winchester. Somebody's come up with a faster one, which is somewhere here. And in theory, you could get 1,524, 5,000 feet per second could be achieved. 1,700 might not be possible with the rapid generation of hot carbon dioxide, water vapor, and nitrogen used in most firearms. Maybe it's possible. Some tank guns get pretty impressive velocities. They're getting close to that. What they do not achieve is a range of 295 kilometers. No, they don't. Doesn't happen. Would have made World War I really interesting if you could do that, just sit in France and lob rifle bullets into Berlin. But you can't. Can't be done. Now might be a good time to pause and ask, why not? What on earth is stopping you? Also might be a good time to pause and ask, what else is wrong with this prediction? Well, here's something else that's wrong with that prediction. You launch from here, 1,700 meters per second, and it comes down 294.6 kilometers away at the same level. On that horizontal line from where it was launched back here is actually that far above a curve with a radius of 6,371 kilometers. So if you're trying to hit a target at that distance that's sitting on the same curve as you, well, you missed by that much. There's also this problem that, there is your curved thing and the direction of down is actually pretty much towards the center of it rather than straight down the screen on this scale. similar Able is not shooting at something 295 kilometers away. He's shooting at something 36 meters away, and nobody's going to worry about this detail on that scale. It doesn't make enough difference to be worth worrying about. The bullseye of an archery target is quite large. Arrows are quite wide. They make quite large holes. As long as some part of the hole made by the arrow is inside the bullseye circle, you scored the maximum score. You don't care about the nanometers. So it is okay to ignore this for your archery. Good enough approximation. But if we do want to take into account the circle, mode 0, high resolution. Ignore line 20, it doesn't need to be there. We define gravity to be 9.81, just like the exam paper did. We define an interval, a number of seconds that we are advancing per cycle through the program, or through the loop within the program. We define the radius of the circle above which we are doing our shooting. We define our launch angle in degrees, and then we define a launch angle in radians to be the radian equivalent of that launch angle in degrees. Half a right angle, the maximum range. And we have this number, drag equals 0.02. Now, this is not an official number. This is a number I'm using for this program. The force of air resistance pushing back on an object, bonus points to anyone who guessed, that's why airgun pellets don't go 4 kilometers. It's why arrows don't go 4 kilometers, or even 1. Air resistance is a thing. It's really obvious in badminton when you see that little cork with its plastic or feather tail go hurtling down across the net and just slow down and drop to the floor. The actual force of air resistance on an object, within certain ranges, because you get issues when you go from one side to the other of the speed of sound. But for our subsonic airgun pellet and our arrow, it is the cross-section of the object's path through the air, multiplied by the density of the air, tell you the mass of air per unit distance that is in the thing's way, multiplied by some number based on the shape of the object. Because some things are more streamlined than others. Multiplied by the square of the velocity. If you want to know how fast this thing is losing speed downrange is accelerating uprange. They are the same thing. Because losing velocity downrange, we should say. Because it is we are defining downrange as a positive direction, so uprange is negative. And acceleration uprange is a negative acceleration downrange. It is losing downrange speed. You divide that force by mass. So here, drag equals 0.02. Drag is a variable that is standing in for cross-section times air density divided by mass. Yeah. Sorry, shape times cross-section times air density divided by mass. It is all of those things combined into a single variable. Then we get our loop. This is another for loop. Here we are incrementing the launch velocity from 2 meters per second to 40 in steps of 2. So we're going to get even numbers, not the odd numbers we had before. dx, change in x. This is the change in x per second. This is how far forwards the thing moves per second. It's velocity across the map in the downrange direction, or along the map in the downrange direction if you prefer. dy, it's velocity in the y direction, which is in this case vertical, is the launch velocity times the sine of the launch angle in radians, because this computer program software uses radians. This is exactly what we had in that diagram of a right angle triangle earlier. Start by setting the x-coordinate to 0 and the y-coordinate to the radius of the Earth, so we are starting top centre of our circle that has the same radius as the Earth, or has a radius that is the Earth's volumetric mean radius, if we want to be really precise. Max r, this is the greatest distance from the centre of the Earth that this projectile has ever been, is 0. It had to be set to something. Repeat. A repeat is a different kind of loop. It means pretty much what it says. Repeat all of this until something happens. Do everything between repeat and until whatever it says after until comes true, and then carry on down the program. So we are going to zoom out very slightly so you can see the width of that line. Add dx times the interval. because if we're only going 1/32th of a second at a time, we only go the velocity in meters per second divided by 32 meters at a time, forwards and upwards. We're adding dy times interval to y as well as dx times interval to x. Calculate the velocity. V is the square root of dx times dx plus dy times dy. The square of the hypotenuse is equal to the sum of the square on the other two sides. And r equals square root of x squared plus y squared. Velocity and distance from the centre of the Earth. The direction in which the thing is moving has a tangent that is dy over dx. The gradient of its trajectory through the air, or its trajectory on our graph, if you like. Resist. The acceleration due to air resistance has a magnitude of the square of the velocity times drag. Resist in the x direction and resist in the y direction are based on the cosine and sine of the direction, exactly like the original dx and dy were cosine and sine of the launch angle. We then subtract the magnitude of the acceleration due to air resistance multiplied by the interval from the velocity. And of course we have to subtract the acceleration due to gravity multiplied by the interval from the vertical velocity. Lines 220 to 240. Line 250 is just keeping track of max r. If the distance from the centre of the Earth is greater than the maximum ever recorded distance from the centre of the Earth, then set the new maximum ever recorded distance from the centre of the Earth to be the current distance from the centre of the Earth. Until, here's the end of that repeat loop, until r is less than radius. If r is less than radius, your projectile has gone inside that circle, it has hit the ground, here is where the repeat loop stops. The next thing we do is print vel colon space, and then the value that's in lvel for launch velocity, which was set with that for loop. And then this string with the arrow and range colon space. And then at the end, open bracket, x times 1000, close bracket, div1, close bracket, divided by 1000, which is really ugly. You could just put x there, but it would put a whole lot of decimal points in the end. Div is an instruction to divide by something and ignore everything after the decimal point. It has a complementary function mod. So as an example, 17 div 5 is 3, 17 mod 5 is 2, 17 divided by 5 is 3 remainder 2. In this case what I'm doing is multiplying x by 1000 to convert from meters to millimeters, div 1 to ignore everything after the decimal point, everything smaller than 1 millimeter, and then divide by 1000 to convert back to meters. This gives me an answer that is in meters to the nearest millimeter. And max height achieved the same thing, just with max r. And then next launch velocity. And we have output from that here. With a velocity of 2 meters per second, we got a range of 0.483 meters and a maximum height of 0.126. With a velocity of 10 meters per second, a range of 9.14 meters, a maximum height of 2.455 meters. From 2 to 10 is a multiplication by 5, so you should get 25 times the range. 25 times nearly a half is about 12, and we only got 9 and a bit, because air resistance. Now at 12 meters per second, yes, we've got nearly 12 and a half, but that's 6 times, not 5 times, the velocity that gave us that nearly half a meter. So the air resistance, that arbitrary 0.02, is costing us range, as expected. If we go to a much higher velocity, let's go from 20, range 26.2, to 40, range 54.3. That's doubling the velocity you would expect 4 times the range if it wasn't for air resistance. Instead, we got barely over twice the range. Because air resistance is proportional to the square of the velocity, the more velocity you have, the more of a difference it's going to make. Well, those were all the even number values for the velocity. Previously we had odd numbers, so a small tweak to make it go at odd numbers. And here we get these. Range 0.13, velocity 1 meter per second. We originally calculated 102 millimeters, now we're getting 132. I believe this is because this is applying gravity at the end of each 1/32th of a second, rather than applying it throughout. We have delayed gravity, which is giving us that extra range. The number on the left should be more accurate, as long as you're happy to ignore air resistance. When we get down to 49 meters per second, 244.75 meters without the air resistance, just 63.40 meters with. And the 64 is probably the more realistic value. What if we reduce the drag? Instead of 0.02, 0.002. Well, okay. We still get 132 millimeters with 1 meter per second. Because at that very low velocity, air resistance is pretty much negligible. We've gone from 0.983 to 0.993, so just gained 1 centimeter there. From 2.576 to 2.753, so we're starting to see it making more and more difference. If we go to 25 meters per second, we get from 34.3 meters range to 58.8 meters range, which is a huge difference at, what's that, nearly 60 miles per hour? This is why making sure your car is a lovely streamlined shape can save you so much money. The difference between 19 meters per second and 25 meters per second is why slowing down can save you so much money. The difference between how much difference it makes at 19 and how much difference it makes at 25. Seriously, you could be in a car that gets 30 miles per gallon at 60 miles an hour and you just tuck in behind a truck and cruise along at 45 and suddenly are getting 65 miles per gallon. And the price of fuel these days and how little some jobs pay, you could actually save your employer money that way, because the extra time they're paying you to drive the car doesn't cost them anything like as much as the fuel you're not burning would have cost. And down here in the bottom right we have a range. Velocity is 51 meters per second, range 192 meters. Again, that's probably a higher velocity and a longer range than you want to test on the school sports field, or in the gym, or in the classroom, which is maybe 10 meters wide. Nah, 7 by 7 at the most is a classroom, isn't it? 10 meter diagonal. Of course, if we go for silly velocities again, 200 meters per second, not even an air rifle. 300 meters per second is a bit faster than 4.5 ACP. 400 is about a 9 by 19 millimeter. 500 for a Magnum pistol. 600, I can't think of anything offhand. 700 AKM. 800 for your... there's got to be something there. 900 is maybe an M4 carbine, or is it 308? The FAL, or the SLR to the UK. FAL to the rest of the world. And there's about 1,600 for a tank cannon. We're getting ranges 4 kilometers, 9 kilometers, 16 kilometers, 25.5 kilometers, 37 kilometers, 50 kilometers. By the time you're up to 1,600, 266 kilometers, we're into the no range again. We're out in that ain't happening, dude, country. 2,700 meters per second, range 789 kilometers. Now at this point, the direction of down, as hinted by the background, that's quite a long way. That's 7 degrees around the curve. The direction of down is going to change by 7 degrees. You probably ought to be taking that into account, but not in BBC Basic with 32 kilobytes of 8-bit RAM. Let's have really silly velocities. 4,200 up to 8,600 meters per second, but with realistic air resistance. Give this thing a realistic air resistance value, which matches the air resistance values of, well, which produces results that match what you see on charts of real-world ballistics. And you get this effect. This is not an exact match for any particular real-world ballistics, but from 4,200 to 4,400 meters per second, you're gaining a whole 14 meters in range. From 8,400 to 8,600, you're gaining 3.5 meters range. Just a whole lot of extra work to get that extra speed in, and it didn't really go much farther. Pause here to let someone clever point something clever out. And then I'll point it out myself. If you have that much air resistance, then that 45-degree angle is no longer optimum. Now, rather than that symmetrical arc, you're getting an arc which is quite long and fast in the first part, but it's getting slower and slower and dropping steeper and more and more steeply later and later in the arc. So what you really want to do isn't lob it high into the air and have it come down nearly vertically. It's get it as far down range as you can with just that little bit of extra height. Remember that sine increases very rapidly, so the extra height you get increases very rapidly with a small angle, and cosine hardly drops at all, so the distance downrange you're getting is hardly decreasing at all. But the greater the angle, the more distance downrange you're losing and the less extra height you're gaining. So instead of where the two values cross over, now that we're taking air resistance into account, there's your maximum range at silly velocity, 2,449 meters downrange at only 19 degrees angle of elevation. Again, for the exam paper asking about similar able, they did not tell you to take air resistance into account, so you don't have to do this. But in actual real-world archery, air resistance is a thing. Arrows do lose energy as they go downrange. Here we have two different values of velocity, I think. Might be air resistance. I forget. It's been a while. It's been a while since I created the images, and somewhere during the several weeks of not being up to narrating this, resulting from eating one sandwich prepared by one person with one cough, I lost the script. Nobody's surprised. Hey, I lost the plot. Is anybody surprised? No. But with these two different values, I think it's different air resistance values. I think it's high air resistance on the left and lower resistance on the right. You do get different angles of maximum range, but not by much. Or this might be different values of velocity. Notice that at the top, 12.5 degrees elevation, only 1,482 meters on the left, 2,577 on the right. Huge difference. Get down here to 48.5 degrees, and it's 1,310 versus 2,374, which is a very slightly smaller difference. So I still don't know whether that was a velocity or resistance. I'm sorry. And I'm also sorry for making you look at this. Yeah, rather than using BBEM, I'm using Python. And I don't like Python. At the top is a comment line. It doesn't do anything, it's just there so that anybody else looking at this can have some idea what it's supposed to do. Chuck a thing and see how far it goes. Import math, because Python is American. Over here in the UK we have mathematics. We shorten that to maths, and we do several maths at once. Sines and cosines and squares and square roots and halving and doubling. Already demonstrated. In the USA, apparently they can only handle one math at a time, so they just import math. Then there are two blank lines. 2 shall be the number of blank lines, and the number of blank lines shall be 2. One blank line shalt thou not insert, saving only that thou then insertest a second, nor shalt thou insert 3 blank lines. 4 is right out. Then we define a routine or function or procedure or whatever you want to call it, called fire. It's going to print a nice dramatic boom. Mostly so that I know it actually got as far as calling this routine. And it's going to do very much what the BBEM program did. Set x to 0, set y to the Earth radius, set dx to... You have to say math dot cos, because if you don't put math dot, it doesn't realise that cosine is a mathematical function. It has no idea what you're talking about. Is the mathematical function cosine of the mathematical function radians of the elevation angle. Yeah. Set a lot of min and max values so we can track the minimum and maximum values that ever arose. Time to 0, projectile radius to Earth radius, that is r equals radius rather than r equals 0, r equals radius. Min and max are from BBEM. Min PV, max PV, min and max velocity. Arc length equals 0, because this thing is going to complain if I don't set arc length to something. While 10 double asterisk 9, double asterisk is to the power of. While 1 and 9 zeros, 1 milliard meters if you're European, 1 billion if you're American, 1 million kilometers, 1,000 megameters, or 1 gigameter, whatever you prefer to call it, is greater than the projectile radius, the distance from the centre of the Earth, which is in turn greater than or equal to the Earth radius, which means while this thing is on or above the Earth's surface, but not a gigameter away, while it has neither hit the ground nor disappeared into the wide black yonder, star-spangled yonder if you prefer, increase time by time res being the equivalent of interval before, increase x by dx times time res. This is exactly what we did with the BBEM. Calculate projectile radius the exact same way as we did with the BBEM. Calculate the acceleration due to Earth's gravity. Earth GM, what's that? This is Newtonian gravity. A smart chap called Kepler, watching things go around each other in the sky, noticed a few things. Noticed that the time it takes a satellite to complete a full orbit of its parent, which is to say something like Ganymede or Europa or Io or Callisto to go once around Jupiter, or Luna to go once around the Earth, or Mars to go once around the Sun, squared is proportional to the thing's distance from its parent, cubed. Square of the orbital period is proportional to the cube of the orbital radius. And that the area swept out by an orbit, which is, say, find the distance from the distance between Jupiter and Callisto, and see how far Callisto has gone relative to Jupiter from 30 seconds before that measurement to 30 seconds afterwards, and call that a triangle. The area of that triangle is always the same no matter when you do it, even though Callisto's orbit isn't a circle, because it's faster when it's closer and slower when it's farther away. Same applies to all the orbits. You can add up any 60 consecutive minutes over the course of a lunar month or a Callisto month, whatever that is, or a whole year. You'll always get the same answer for the same parent and satellite. Newton came along and looked at Kepler's work and said, "Oh, that's weird." Newton also noticed a few things. He noticed that an object will tend to remain at rest or continue in a straight line at uniform speed unless some exterior force acts upon it, and that the acceleration is proportional to the force and inversely proportional to the mass, and that for every action there is an equal and opposite reaction. Combine that with Kepler's observations, and there must be, or there very strongly appears to be, a force of attraction between every two objects that have mass, which is proportional to each of their masses and inversely proportional to the square of the distance between them. Which means if you know the mass of the Earth and the mass of the Moon, and the distance between them, you can calculate that force of attraction. Well, weighing the Earth, that was left for Cavendish to do ages later. Been repeated hundreds of times. Blue Marble Science is a really good recreation of that. Calculating the GM of the Earth is a whole lot easier, because the acceleration is proportional to the force and inversely proportional to the mass. So the acceleration of the Moon towards the Earth is proportional to the Earth's mass, and inversely proportional to the Moon's mass. So you can cancel those out and work out the GM of the Earth, the universal gravitational constant, the proportionality thing. The force equals the universal gravitational constant multiplied by both masses divided by the square of the radius. You can calculate that universal gravitational constant times the mass of the parent. You can measure that by observing the orbits. Calculating the actual value of the constant or the actual value of one of those masses is harder and therefore less accurate. We can get the Earth GM. Divide by the square of the projectile radius, because it is inversely proportional to the square of the distance between them. That will tell you how fast your projectile, wherever it is, should be accelerating towards the Earth, treating the Earth as a point. Then we have if y is not equal to 0. Bear in mind that our x-coordinate is how far forwards from the launcher it's gone, our y-coordinate is how far up, how far it is from the centre of the Earth in the direction that is up from the launcher. If y is 0, this thing is currently in a direction from the centre of the Earth that is exactly forwards from the launcher, which is presumably a heck of a long way away, and Earth's acceleration is not up or down from the launcher's point of view at all. Sorry, its acceleration due to Earth's gravity. It's not that. It's just straight forwards or back from the launcher's point of view. If it's not 0, we calculate the direction of that acceleration using a mathematical function, math equals a tan x over y. If y was 0, this would return a division by 0 error. Except it wouldn't return a division by 0 error, because Python doesn't tell you it's a division by 0 error. It just goes because it's Python. Right. But if x is greater than 0, if your projectile is somewhere in front of you, it accelerates towards the Earth, so it accelerates in the negative x direction. And if x is not greater than 0, it's somewhere behind you and accelerates in the positive x direction. And then if y is greater than 0, it's going to accelerate in the negative y direction, which is down from the launcher's point of view. If y is less than 0, if this thing has gone so far around the Earth that it is now farther in the direction that is down from the launcher's point of view than the centre of the Earth, it's going to accelerate in a direction that is up from the launcher's point of view due to Earth's gravity. So that's the top bunch of lines. Then there's an else. Now, due to indents, and Python really does rely entirely on the indents to know where the if ends. So if y is not equal to 0, that stuff, else y equals 0. So you simply have, if x is greater than 0, accelerate backwards, if else accelerate forwards. And accelerate not at all in the y direction, obviously. Then dx plus equals ax times time res. We apply that acceleration due to gravity to the object's velocity in the x direction and in the y direction. Calculate the velocity, and then we keep track of whether or not this is a bunch of new records with all that if x is greater than max x, etc. Having updated all of our records, this commented line, print that stuff, is a line that I put in so that I could see what was going on and then commented out so that it wouldn't fill the screen with what was going on. If x is greater than or equal to 0 and y is greater than or equal to 0, or x is greater than or equal to 0 and 0 is greater than y, or x is less than 0 and y is less than 0, or x is less than 0, which is less than or equal to y, 4 different ways of working out the arc length, which is really awkward, really annoying to have to do, but there it is. There may be a better way. Drop. Drop is how far the Earth's surface at that distance is below where this thing started. Well, no, it's how far in a direction down from the launcher's point of view the projectile eventually came to rest, which is not quite the same thing because we're using the coordinate of the projectile, which is now below the surface rather than using the actual surface. Pretty close. And then we print all of this output. The time, the coordinates, the velocity at which it hit the ground, which was calculated again when I could have just used PV, but never mind. And the minima and maxima of various variables, linear distance achieved, the arc length, the drop and the parabolic approximation. I have a video explaining the parabolic approximation titled Man's Got to Know His Limitations. And you can go and watch that. I won't explain it here. Next we have another two blank lines. They're up there at the top. There was one at the bottom of the previous slide, there's one at the top of this. There are two blank lines. 2 shall be the number of blank lines, the number of blank lines shall be 2. And then there is absolutely nothing saying that this is the main program. Python just runs out of comments and includes and define this routine to be this and hits earth radius equals that. So I guess that's where we start. And it starts there. We're defining the earth radius to be 6,371,000, which seems reasonable because that is the volumetric mean radius of the earth in meters, according to NASA. Earth GM is 3,986 times 10 to the 11. NASA have it in some weird units, I think 0.39860, in units that work out as times 10 to the 12. 3986E11 is easier to type. 3.986 times 10 to the 14 if you want to be proper about it. Elevation angle in degrees, 45, because that's the angle at which you get the maximum range, right? Launch velocity, 1,000 meters per second. Time resolution 1/64. We're being more precise than we were with the B this time, because we can, because this is a 64-bit computer. The answer is F. It has to have some kind of answer, so that we can have while the answer is not Q. While is like a repeat until, but instead of repeat all of this stuff until this comes true, it is while this is true, repeat all of this stuff. It's going to print a bunch of stuff on the screen, which is effectively a menu, and then it's going to wait for an answer. A equals input, adjust or fire. Puts adjust or fire on the screen, you put in some string and it sets the variable A to be whatever string you entered. If it's an A, upper or lowercase, it will print earth radius in meters, wait for an input, convert that input to an integer, and set the radius of the earth in meters to be that integer. If you enter a 0, it will set it to the default value of 6371000. If you enter a B, it'll do the same thing, but it's going to set a variable called beep to that integer, and then it will ask for the exponent, and set a variable of fish to be that integer, and it will set the Earth's GM to be beep times 10 to the fish. Beep should probably be a float, so you can insert decimal points if you want to. I could make fish a float, and you could define the Earth's GM as 1 times 10 to the something really weird, if you're into that kind of thing. But unless you know how to use a slide rule, you're probably not. If you enter a C, it's going to change the elevation angle. If you enter a D, it's going to let you change the launch velocity. And the launch velocity of all things, I allow you to put in a decimal point, but not on the elevation angle and not on the Earth radius or Earth GM values. Bad program. I'm not all that bothered. Right. And finally, if you enter an E, it will set the time resolution. You can tell it whether you want to go 1 second or ½ second or ¼ second or 3.1415926 something seconds at a time. If you enter an F, it will fire. It will call the routine that was called fire that was defined at the top of this program. And then it will come back here after that routine runs out. There is nothing below that. There is simply an end of indented text. So that is the end of the while loop. And of course the while was while A is not Q. So until you enter a Q, it's going to go round and round this loop. If you enter an X or a Y or a Z, it's just going to reprint the menu and ask for another input. If you enter a Q, it will run off the bottom of the program and stop. There's no end. It just runs out of code. And here it is running. It very helpfully tells you that my username on this computer is me. It didn't need to put the addresses up there, but it did. There's the menu as described. F for fire. It does indeed say boom, very dramatically, time 146 seconds. Yeah, it was a long time. 102.657 kilometers forwards and 6,370.171 kilometers up from the center of the Earth, with a velocity of 1,000.12 meters per second. It came down faster than it went up, which is a little weird, but it's pretty close, and that is pretty much what we'd expect from that symmetrical parabolic arc that we had way back when I was answering that question about similar able. This is still a parabolic arc. It's just a parabolic arc that's been kind of converted to polar coordinates. It's just curved in a little, like you extended the picture way down and got hold of the two bottom corners and pinched them together. Turned that rectangle into a triangle. A very tall, narrow triangle. And we've got the min and max x, min and max y, min and max dx, min and max dy, min and max distance, min and max velocity. This thing slowed down to 704 meters per second, sped back up to 1,000.123. 8, 5, 8, 8, 2, 4, 6, 8, yeah, whatever. And that 704 is about what we would expect, because that's what the x component of your velocity is going to be. That's your initial forward velocity. It's 1,000 times the cosine of 45 degrees, which is 1 over root 2. 1 over root 2 being 0.70 something. Okay, seems reasonable. Linear distance, 102.660 kilometers, that's the linear distance, not the horizontal distance. That is the hypotenuse of a right angle triangle that also has the drop, which is why it's slightly farther than the x displacement. Arc length, 102.661 kilometers. It's just that 1 meter farther if you take the curved route along the surface rather than a straight line through the Earth. Pretty much the same answer. And if you're throwing arrows at a target most of 103 kilometers away, you're probably throwing arrows that are big enough for 1 meter not to matter all that much. Like, you still hit the same palace or hardened aircraft shelter or chemical weapons factory or, drinking water treatment plant or power generation station or hospital, if you happen to be into shelling hospitals and drinking water treatment plants. And a drop in a parabolic approximation, as before, 828.68 meters, 826.80 meters, similar but not exactly the same. Again, good enough approximation, assuming you're into really big arrows and really big targets. And then, having run off the bottom of the fire loop, it goes back to the main menu and just asks for another input. Okay. And there are those results, and there are BBEM results, and we can compare. And we can't compare directly because there is no 1,000 meters per second among the BBEM results, so we add 97900.102 to 106055.046 and halve it, and we get 101,977.574 meters. That's our range according to BBEM with the very early program, and according to this much more sophisticated program, our range is 102.66 kilometers. So we're out by 0.683-ish kilometers, 683 meters, which is quite significant, but you're close enough. I mean, you're within half a mile. I would hope your artillery spotter isn't within half a mile of the target and can tell you where it came down and what adjustment to make. So neither of these is perfect, but at least they're giving similar results. They might be considered good enough. And yeah, I should have paused to give you time for the smart kids in the class to point out the problem. Here is a hint to the problem that has been in the background for quite a long time, only it wasn't this zoomed in. This is the Earth from the Himawari 8. This is just before sunrise somewhere over the Pacific, or just after sunrise somewhere farther east in the Pacific. The Himawari 8 is a geostationary satellite sitting high above the equator, slightly east of Japan, and obviously south of Japan because it's over the equator. It gives that lovely view of Australia that we had before. and it's used by the Japanese to watch weather over the Pacific. It takes a photograph of the whole Earth every 10 minutes, except when the sun is in a really awkward place and spoiling it. And this was one taken when the sun was still out of sight behind the Earth, but sunlight was shining around the Earth. It may have been actually after the sun got just far enough out not to be in the way. It might be just before the sun got far enough out to be in the way. But either way, you have sunlight lighting up the atmosphere from behind the Earth, and some of the red light, the blue light hidden in the atmosphere and getting scattered, which is why the atmosphere glows blue. The red light is coming through the atmosphere, being refracted down by the atmospheric density gradient, atmospheric optical density gradient, and lighting up the clouds over the Pacific, this side of the terminator line, ahead of sunrise, which is why you see that pink glow of the clouds. Well, the previous program didn't have air resistance at all. If we're going to incorporate air resistance, we want to take this into account. Maybe not for a similar Able, who's shooting at a 36-meter range, but for that shell that went 25 kilometers up, oh yes it did. Oh yes it did. Max Y, 6396565.74. Max distance, 6396771.7. With a radius of 6371000, that is 25.77 kilometers above the surface. And there's an atmospheric density gradient. So if we want to incorporate drag into our calculations and produce a much more realistic simulation, we're going to need to put the atmospheric density gradient into our calculations. Specifically, we're going to want to incorporate this atmosphere into our calculations. This is from the Engineering Toolbox, which is a wonderful website if you want to know the density and crush strength of various types of stone, so that you can calculate how wide the base of the Tower of Babel would have to be to support a given height. Or if you want a standard atmosphere, or if you want to know how the density of seawater increases with increasing depth, because water is actually slightly compressible to a limit, the Engineering Toolbox is the place to go to find stuff like this. And here's your standard atmosphere. On the left we have the height in kilometers, or the altitude in kilometers really, but they've listed it as h. From -1 to +110. It's not every kilometre, because that would be a very long list, and it has some peculiar values towards the bottom, but it's a good list. We have a temperature in degrees centigrade, capital T in the second column, from 21.5 centigrade, which is quite warm, a kilometre below sea level, presumably down a mine, through 15 centigrade at sea level, which is long sleeve t-shirt weather, and 8.5 centigrade just 1 kilometre up, which you can even achieve in Wales. Not in England, not quite, unless you're incredibly tall, but in Wales you can. 8.5 centigrade, you're going to want a jacket. Up to just 2 centigrade, which is fridge temperature, 2 kilometres up. -4.5 centigrade, which is frozen, literally, 3 kilometres up, and that's before you even get into altitude sickness. So right there we have a note to anyone thinking of climbing Mount Hood. Yeah, it may be long sleeve t-shirt weather at the bottom. It's literally frozen at the top. You're going to want some warm gear, some warm socks, some serious boots, probably some means of walking on snow and or ice safely. Waterproof jacket and trousers, warm liners for them, a face mask and goggles probably. Especially if it's windy, because that would suck the heat right out of you. Third column, P, the pressure in kilopascals. Kilopascal, well, 1 pascal is 1 newton per square meter, so kilopascals is thousands of newtons per square meter, or newtons per square 31.6 centimeters, slightly more than a foot. We have 113.9 down that mine, 101.325, the standard atmosphere at sea level, decreasing as you go up until by the time you're 10 kilometers up, which is higher than Everest, you're down to just 26.436 kilopascals. And when you get up there to 100.4 kilometers, which is just past the Kármán line being this arbitrary designation at 100 kilometers, because that's a nice round number, that below that you might be able to reorient your aircraft, your vessel, your vehicle, using wings and ailerons and elevators and vertical stabilizers and tail fins and rudders and things like that. And above it, you can't. This does not mean that they work just fine at 99.9 kilometers and not at all at 100.1. It means they have less and less effect as you get higher and higher in altitude. And by the time you're at 100 kilometers, forget about it. And then, finally, on the right, we have the column we actually want from this. That is not a lowercase p, that is the Greek letter rho. You'll also see this adopted into Russian. It is an R, not a P. When you're reading Russian, don't read it as P, read it as R. In kilograms per cubic meter, down that mine, 1.3470. At sea level, 1.225. 1 kilometer up, 1.1116. Kilograms per cubic meter, density of the air. And this is the column we want so that we can take that into account when calculating the air resistance, because of course air resistance is the mass of air that's in the way per unit distance, times the square of the velocity, times that factor for how awkward the shape of your object is. We can incorporate that into Python by adding a couple of new variables. Sea level density 1.225 and density gradient 0.99986. So every time you go up 1 meter in altitude, you multiply the air density, yes, by 0.99986. Or to calculate it for any arbitrary altitude, you take the sea level density, 1.225, and you multiply that by 0.99986 to the power of the altitude in meters. And that will give you a number from the previous chart. Taking this into account to get a sensible sort of result, drag coefficient of 0.0022 seemed reasonable. To get a result that's fairly similar to what we had before. Not immediately before, but earlier. We now have this same menu, except we have inserted F is now sea level air density and G is air density gradient. And H is drag times cross-section over mass. So we can no longer use F for fire, it is no longer F for fire, it is now Y for yeet. But Q is still quit and it still works the same way. And here we have the same routine as before, doing the same thing, but there in the middle, we have the line that calculates the local air density to be sea level density times density gradient to the power of altitude, how far the projectile is from the centre of the Earth minus the radius of the Earth is your altitude. And now drag isn't just drag coefficient times velocity squared, it is drag coefficient times local density times velocity squared. And as well as applying gravity, you also have to apply drag in the opposite to the direction of travel. It's an acceleration opposite direction of travel through the air. And that gives us results. I modified the commented outline and I removed the comment out part, so it now is outputting the coordinates, the velocity components, and the air density as it goes, and you can see that as it came down, the air density was increasing, and it matches the standard atmosphere. As it hits the surface, 1.22500, as you'd expect. This is still a 430-second flight, and it's still going 108 kilometers, so not much has changed there. But it came down at just 59.5 meters per second rather than 1,000, because air resistance did affect it. In fact, that was its minimum velocity. It was slowing down the whole way. Having been launched at 900 rather than 1,000 meters per second initially, as you can see from the max velocity and from launch velocity in the menu below. That gives you the criteria that were used for the data, the results above the menu. And because 25 degrees gave a better range than 45, this one was launched at 25 degrees, not at 45 degrees. So now we have this range of 108 kilometres. Okay. Is this better than what we had before that didn't take drag into account? Heck yes. Obviously. Vastly superior. Is it perfect? No. Is it a good approximation? Probably. Maybe. Depends what you're using it for. So let's change the drag coefficient. Enter an H. It asks for drag coefficient in square meters, which isn't exactly the right unit. Square meters per kilogram it should be. 0.013. This number was chosen by a process of trial and error, comparing the output to data from a ballistic chart for 5.56 by 45mm NATO ammunition. Back to 45 degrees and 1,000 meters per second, and now this thing is coming down a mere 1.944 kilometers away. Which is less than 2 kilometers, which is kind of disappointing, and it's nothing like the phenomenal ranges that we were calculating earlier. Because air resistance is serious, and it does affect those little tiny 4-gram bullets quite a lot, especially at the crazy velocities at which they're launched. 1,000 meters per second being a bit faster than they are launched. Yeah. What on earth is that lot? Well, maybe you can't see it yet, so here you go. You can see it now, can't you? What on earth is that lot? This is to answer a question that may have come up among the audience. That how is Himawari 8, and in fact how are Himawari 8 and 9 these days, just sitting there above the equator? See, we have all the software to calculate how something that is above the Earth is going to fall down and hit it, but Himawari 8 doesn't. Explain that. Go back to what I said about Newton's equations. The force between two objects, attracting them together, little g, is big G, universal gravitational constant, times mass of the large object, big M, times the mass of the other object, little m, divided by the square of the distance between them, r squared. We also know, from experiments involving standing in the playground, holding 2 buckets of water and spinning round and round in circles, or maybe some things a little more sophisticated than that, that an object travelling in a circle is accelerating towards the centre. You can tell this by the fact that you have to pull those buckets inwards to keep hold of them as you go round in circles. You could also derive this, if you're into circular rotating reference frames, derive this from a change in the velocity of an object travelling in a circle. It is accelerating towards the centre at a rate proportional to the square of its angular velocity, that curly letter there that looks vaguely like a little w, that is omega. Last letter of the Greek alphabet, lowercase, looks like that. Angular velocity, radians per second. The square of that multiplied by the radius, meaning the farther out it is, the harder you have to pull it in to swing it round at once every 2 seconds, or once every 3 seconds, or once a minute, or whatever. Angular velocity is what you get, what is consistent from clock to clock. If you have an old-fashioned clock, I suppose these days, as in on the Elizabeth Tower in London, or on so many hundreds of churches elsewhere, but that's the only one anybody ever recognises, all the minute hands should be going round at the same rate. They all have the same angular velocity. They all take the same amount of time to complete one circuit. V, the linear velocity, is how fast the very tip of the minute hand is going, and that is going to be faster on a bigger clock face. In fact, V is the linear velocity is the angular velocity times the radius, which means omega squared times the radius is V squared divided by the radius. And if an object is going in a circle, due to gravity, that inward acceleration is the acceleration due to gravity, and that equals sign right there between gmm over r squared and omega squared r is incorrect because there is a one-term difference. My bad. We also know from Newton F equals ma. The force is the mass times acceleration. The acceleration of of an object is proportional to the force and inversely proportional to the mass of the object. Just rearranged to F equals ma. If we rearrange it to say that the acceleration is the force divided by the mass, and we say that the force is little g, then the acceleration is gmm over r squared divided by little m, so you can remove the little m. You get gm over r squared, which is what we used in that Python script. The acceleration then, gm over r squared, equals omega squared r equals v squared over r. For an object to be where the Himawari 8 is and not falling down, the acceleration towards the Earth due to the Earth's gravity must be equal to the acceleration required to keep it going in a circle of that radius at that rate. If we combine and rearrange those formulae, we get omega squared is gm over r cubed, v squared is gm over r. The second line of text on your screen now. And we know the orbital period of the Earth. The Earth goes round once, which is 2 pi radians, every 86,164.09 seconds. Not 86,400, that's a mean solar day. We're using the sidereal day here. The actual rotation, not average time from noon to noon. So the angular velocity of the Earth is 2 pi over 86164.09. If you want this thing to stay above a point on the equator, you want it to go round exactly once every time the Earth goes round, exactly once. And in the same direction, that's very important. And it has to be above the equator and going east. You could have it that distance above the North Pole going in some direction, but it wouldn't stay above one point that way. It would just keep going round while the Earth rotated inside its orbit at right angles to the path of its orbit. It would always pass over the same point on the equator going south and the same other point going north, but it wouldn't, actually it would be the same point on both sides. It wouldn't sit over one point. It has to be over the equator and going east. It's wonderful for Himawari 8. It's wonderful for satellite television satellites, because you can just point your dish at it and it's there. Relative to the Earth's surface, it's always there because it's staying at the same distance and it's going round with the Earth. It's like horses on a merry-go-round, a carousel thing. You can be on the inner horse and the outer horse, reach out and shake hands. The direction relative to that inner horse to the outer horse doesn't change. The direction from a point on the surface to the satellite doesn't change. Very useful. From omega equals 2 pi over 86164.09 and omega squared equals gm over r cubed, we can calculate that r is the cube root of 3.9860 times 10 to the 14, Earth's gm, divided by 5.45893 times 10 to the negative 11, which is the square of 2 pi over 86164.09. You're dividing 10 to the 14 by 10 to the negative 11. Dividing by 10 to the negative 11 is multiplying by 10 to the 11. Multiplying 10 to the 14 by 10 to the 11, you get 10 to the 14 plus 11, which is 10 to the 25. And dividing 4 by 5.5, you get, I forget exactly, but you then take the cube root of that, you get a huge number, don't you? You get 4 divided by 5.5, what's it going to be? 8/11. You get 8/11 of 10 to the 25. Then you want a cube root. Well, 8/11 is what? Well, 11th is 0.0909, so it'll be 0.7272. Okay. 10 to 10 to 25, or 7.272, 727 times 10 to the 24. Therefore, your radius is the cube root of 7.272727 times 10 to the 1/3 of 24, 10 to the 8, right? Which is, right there, 42,164,154 meters. That's the radius of a geostationary orbit. The GM and orbital and sidereal period of the Earth define geostationary orbit to be that radius. Now that we have the radius, v squared is gm over r. So v is the square root of 3.9860 times 10 to the 14 over 4.2164 times 10 to the 7, which is 3,074.66 meters per second. Himawari 8 stays up by being that far up and going east at just over 3 kilometers per second. Fair enough. Fair enough. So in effect, going east 42,000 kilometers up at 3 kilometers per second prevents you falling down. Not going east means you do fall down. Presumably going west 42,000 kilometers up at 3 kilometers per second would also prevent you falling down, but of course you'd meet the people coming the other way. Probably make you unpopular. This logically implies that going east at, say, 6,300 and some kilometers up, 6,400 kilometers up, at 1 kilometer per second, while it won't be enough to stop you falling down, because of course your orbital period should be proportional to the square root of the cube of your orbital radius, and that is nothing like fast enough for that low radius. It won't stop you falling down, but it should make you fall down less. It should reduce how much you fall down. And the particular radius in question is your distance from the axis of the Earth's rotation, which is that blue line on the left. And how fast you are going is, of course, once around that axis per sidereal day. So we need to know how far out from the axis you are. Now, on a sphere, this is quite simply a matter of the cosine of your latitude, the angle between this indigo line that's horizontal near the bottom of the screen, very near the bottom on that image, if I scroll up a little, and wherever you are, any of these other lines along which you happen to be positioned. Or it's the sine of the angle between the pale blue line pointing up straight up, the axis of rotation, linking north and south poles, and your position on the surface. Obviously, on a sphere, the tips of all of these lines, the outer tips of all these different coloured lines in between, are actual circles of equal latitude around it, and you would not be partway out along one of these lines. You'll be somewhere on the surface between these circles described by the tips of these lines as this cross-section rotates. You can convert from angle to distance just by matching the colours in this handy diagram. These are 10-degree intervals, and there are distance from the axis 10-degree markers of the same colours across the top. But, and depending on context, it could be a very big but, or it could be a tiny but. If anything that's going east falls down less than stuff that isn't going east, and the whole Earth's surface is going east, but the farther it is from the equator, the less it's going east, the farther it is from the pole, the faster it's going east, then the Earth's surface itself, all the trees and the hills and the lakes and whole mountains, the entire Earth's crust and the mantle below, well, the entire lithosphere and the asthenosphere below it, if we're into those terms, should weigh less at the equator for the same volume of the same material with the same density than it does at the pole, and have that decrease in weight as shown across the top. Which should mean that the force of gravity that is pulling all this material together into a sphere should actually pull it down a little tighter pole to pole than across the equator, which means the Earth shouldn't be spherical. And that's true, it's not. A better approximation would be an ellipsoid, which is a 6,356,752 meter radius from the center to a pole, a 6,378,137 metre radius from the centre to the equator. So, this diagram that we have here with these different colours showing how far out from the axis you would be on a sphere, at a particular altitude on a sphere, it's not good enough. I mean, it's fairly close, but it's not really right. Really right, you need that. Just go back, and now there's the sphere, and there's the ellipse. At the centre, in the bottom left of the image, but the centre of the circle, you can see that photonegative part that disappears and reappears as I go back and forth between the images. At least I hope you can. I don't know whether the screen's refreshing for you, but this bit here. This bit down here, where it's photonegative, that's on the ellipse, and it looks like it's perfectly superimposed on top of the sphere, doesn't it? Because there really isn't that much difference. But with it zoomed in this far, if I come way up here, photonegative green is purple, and there it is. Sea level at the pole is just that little bit closer to the centre of the Earth than the volumetric mean radius, and then it increases until they match somewhere around there. If you get nearer to the equator than that, the actual radius becomes greater, and it's just proportionally just that little bit farther out at the equator than at the centre. So if we really want to account for this in our program, we need to take that into account. We need to do calculations that take into account not just the rotation, but also the ellipticity that results from the rotation. And of course that means even more Python. Doesn't matter how much you hate Python, it's on the screen. We have the same program but with more variables in it. Yeah. A lot more variables in it. The Earth's polar radius, defined as 6356752. The Earth's equatorial radius, defined as 6378137. The Earth GM is still in there. The sidereal day, we need that. That's how long it takes the Earth to rotate once. We need to know that because that's the whole big deal about everything going east. We still have sea level density and density gradient. Now you have to know where on this spheroid your gun, launcher, archer, whatever, is. Because of course that matters now. We were just sitting you on top of an arbitrary stationary sphere before, but with rotation and ellipticity taken into account, we need to know where you are. So, we are arbitrarily 50 degrees north, 30 degrees east, and 200 metres above sea level. That matters too. The farther above sea level you are, unless you're actually at the pole, the farther out from the axis of rotation you are. We also need to know what direction you're sending this thing, because if you send an arrow to the east, assuming you are something like 40, 50, 60 degrees north, an arrow shot to the east is adding the launch speed, 50 metres per second, whatever, to the speed of the surface of the Earth that's going to the east. An arrow shot to the west is subtracting its launch speed from the speed of the surface of the Earth. So now, the direction in which you're shooting matters. It matters in more ways than that, but that's the big deal for now, is that it should effectively weigh less. It should fall more slowly, let's say, going east than going west. So we need to know the direction in which you shoot it. Azimuth D, azimuth in degrees. And of course we need the elevation angle, we always need that, and the launch velocity, we always need that, and this drag coefficient, which is now down to 0.001, which is a pretty small number, compared to the 0.013 I had before for the 5.56 bullet. And we need the target's altitude so that we know when your projectile has fallen below the target. So we can say, when it is time to check whether you hit it or not. And the target's latitude, which is likely to be different from that of the launcher, so you need to recalculate all the stuff about distance from the axis, distance from the centre of the Earth for the target. I've tightened the time resolution down to 1/256th of a second, and there are two more variables in there, stepwise and verbose. Stepwise is what it sounds like. Well, it's what it might sound like. It might sound like going step by step, which is what it is. It might sound like someone who is really smart about putting one foot in front of the other, which is not what it is. Verbose means using a lot of words. That's me. Hi, pleased to meet you. That is an option for whether or not it should tell you what's going on as it goes through. And then we have the same thing of setting a value for A just so it has a value while it's not Q. And now we have this huge menu of options that can be set. And of course, we're now all the way up to O, or at least up to O. In fact, we're up to P for verbose. So obviously it's not F for fire, it's still Y for yeet. There is no letter on the third row of that menu. Yeah, that's because just like with the two different variables you input for EarthGM, you can input two different variables in response to two prompts, having just given one response to the menu. So B will now let you set EarthGM and sidereal day. Because I didn't fancy going through adjusting everything by one letter, that's why. Really, this could be A for Earth radii and GM and sidereal day, B for sea level air density and air density gradient, E for the drag times cross-section over mass of your projectile. Sorry, no. It wouldn't be E, would it be? A for the Earth, B for the atmosphere, C for the projectile, and then D for launch latitude, longitude, azimuth, altitude, elevation angle, and velocity if you wanted to, but I have it set up as mostly one letter per variable. And at the top of that program, yeah, we started with the main part and then we moved back up to the top to see all the defined stuff, because Python. You do this in C as well, but at least in C you tell it what the main is, and you put a little closed curly bracket at the end of each function. I have a new function, give me radius, and in brackets lat. This means this function is going to be passed something which, for the purpose of this function, is going to be called lat. Whatever we pass to it is now an internal variable called lat in this function. Give me radius sets up two more internal variables, sila and cola, the sine and cosine of the latitude. And then four more terms alpha, bravo, charlie and delta, which are those functions on the screen. Just those. And then calculates a radius, which is the square root of the sum of the squares of the radii times appropriate cosine sine divided by the sum of the squares of the radii multiplied by sine and cosine, as a way of scaling from a Pythagorean, right angle triangle thing in a sphere to one in an ellipse. Then it has this line return radius. This is going to pass the calculated value of radius back to whatever called this function. Then I have give me x, give me y, give me z. These let me take a latitude, longitude and altitude of a thing at a known latitude, longitude and altitude, and return the x, y and z coordinates. This is in the reference frame used by a GPS system in which x goes from the centre of the Earth out through the prime meridian on the equator. Or it goes from 180 degrees east through the centre of the Earth and out through the prime meridian on the equator if you prefer. Y is at right angles to that, going from 90 degrees west through the centre of the Earth and out through 90 degrees east at the equator. And Z is at right angles to both of them, going from the South Pole through the centre of the Earth out through the North Pole. So we have out through the sea south of West Africa, out through somewhere near Indonesia, I guess, or in the Indian Ocean or something like that, and out through the North Pole as our directions. And that gives us the XYZ coordinates for a 3D Cartesian system in which we can do all our calculations, rather than having to do them in polar coordinates. Then we have the reverse functions, give me latitude, give me longitude. If we have something at a known x, y and z coordinate, we want its latitude and longitude, we call these functions, they return angles, the latitude and longitude of those coordinates. And then, of course, we have to define yeet, which prints yeet, rather than printing boom. And still, just let me know that it got as far as calling this function. And then we have an internal variable for this function called step by step, which is set to the same as stepwise, because stepwise is a variable for the whole program, and a function can't change it. If you want to change it, it becomes an internal variable, and the whole program would lose it. Because Python. If you do this in C, you can use the same variable and it will change within the function and just revert back when the function ends. In Python, you've got to set an internal variable to be equal to stepwise. So step by step, stepwise is, were we going step by step when I pressed fire or when I pressed yeet? Step by step is, are we going step by step now? Earth angular velocity, because we need to know that, is 2 pi, because 2 pi radians to a circle, per sidereal day. This is not new. There's a comment in there. I do occasionally insert comments so that somebody else can have some clue what they're looking at if I'm not there to explain it. Latitude in radians is the radians version of latitude in degrees, and so on for a whole lot of angles. Launch radius is give me radius, latitude radius, and plus the launch altitude. So your distance from the centre of the Earth at the launch site is the radius of the sea level at the launch site plus the altitude of the launch above sea level, which makes a certain amount of sense, you know, in terms of being exactly what it is. Launch X, launch Y, and launch Z, the position from which this thing is launched, are give me X, give me Y, give me Z, up to the latitude, longitude, and altitude of the launch, obviously. X, Y, and Z, the current coordinates of the projectile, are launch X, Y, and Z, because that's the place from which it's about to be launched. Next, we need to convert vectors from, well, convert angles and a scalar for the speed into vectors, combining magnitude and direction. So, how fast it's going north. If your gun is pointing north, it is horizontally north, it is going north exactly as fast as you launch it. If you raise your gun or swing your gun away from true north, it's still going pretty much as fast as you launch it north at first, but the farther away you swing it, the faster that's going to decrease. That's the cosine wave that was in blue ages ago. Starts off at 1, stays pretty near to 1 for a while, then decreases faster and faster. So the cosine of the elevation angle and the cosine of the azimuth times the velocity. How fast it's going east, if it's pointing horizontally east, is your launch velocity. If it's pointing horizontally north, it's 0, right? So you want something that starts at 0 and increases quite rapidly as you swing away from north towards the east. How fast it sets off east is going to increase very rapidly. As you approach true east, it's going to be pretty close to 1, and it's going to increase very slowly, like last little bit to 1, and then drop off again. That's the sine wave. Maxes out at 1 right angle from true north. And your azimuth is measured from true north. So the sine of the azimuth. But you have the same effect of raising the gun above horizontal is going to decrease how fast horizontally east your projectile sets off. So the cosine of the elevation in both. Whereas how fast your projectile sets off upwards, it doesn't matter whether you're pointing north, east, south, or west, or anywhere in between. What matters is how far above horizontally your gun is pointing, and a slight increase at first from horizontal is going to give you a huge increase in how fast this thing sets off upwards. But that increase for each additional degree of elevation angle is going to decrease until pointing vertically up, it's going up at its entire launch velocity, and it's going to come right back down your head, so that's stupid, don't do it. And anywhere near to vertically up, it's pretty much going up at its launch velocity, which is back to the sine wave, so the sine of the elevation angle. Then we add the surface velocity, because your launcher is going east. Even before you shoot, the projectile sitting in your launcher is going east at the speed of the surface of the Earth. So, distance from axis, that was the thing that was shown across the top of that image with the green arc. It's your radius at your latitude, plus your altitude, plus, all times the cosine of your latitude. That tells you how far from the axis your launch site is, which tells you how fast it's already going east. Just multiply that by the Earth's angular velocity, because v equals omega r. Then we add that ground velocity east to the eastward velocity, the initial eastward velocity of our projectile. Of course, this is still north, east, and up in a frame of reference that is currently 50 degrees north, 30 degrees east, arbitrarily. And we want it in that XYZ coordinate system. So we tilt this thing towards the pole. And just as tilting the gun from horizontally north towards up creates this cosine of the elevation times velocity north and sine of elevation times velocity up effect, tilting the entire launch site from north is the z direction at the equator and up is out from the axis at the equator, towards north is towards the axis and up is in the z direction very near the pole, is going to give us a sine and cosine thing, but it applies to both now. You have the sine of one and the cosine of the other on each. So your velocity north is velocity times the cosine of the latitude and your velocity in the z direction, say, is your velocity north times the cosine of your latitude, and your velocity up times the sine of your latitude, and your velocity out from the axis is your velocity up times the cosine of your latitude, your velocity north times the sine of your latitude. Minus, not plus the velocity north times the sine of latitude, because as you get north of the equator, north becomes towards the axis, not out from it. If you have a negative latitude, you are south of the equator and north is out from the axis, subtracting a negative is adding a positive, and the faster your shell, projectile, arrow, bullet, whatever, sets off north, the faster it's going out from the axis of rotation. And that's great, but we still have a local out from the axis of rotation, not a GPS X direction and Y direction, so rotate them to longitude is the next comment, and we do the same thing, but this is rotating from arbitrary position to its longitude, east from Greenwich, to convert from locally out to X and Y directions. We now have our launch set up. We can set time equals 0. We still have some other variables, projectile radius, the minimum maximum. Set the velocity to be the launch velocity. Set the arc length to be 0 so that Python doesn't whine about arc length not having been set. And of course we need that target position so we know when the thing has fallen below the target and no longer has time to reach it. So target latitude in radians, and target radius is the radius at the target's latitude plus the target's altitude. Finally, we can set a variable called ready to yes. That's going to come in handy later. Two more variables. Gone is 0 and splash is 0. The thing has not gone off into the star-spangled black yonder, and it has not splashed down yet. Then here's our while loop. While it hasn't gone and it hasn't splashed down and ready hasn't been changed to the letter Q, we move the thing. And then we see whether it's gone or splashed down, and possibly whether anybody wants to change ready to the letter Q. So, just as before, time plus equals time resolution, x plus equals dx times time resolution, etc. We have a new variable to introduce, old projectile radius equals projectile radius. We set that after we've moved x, y, and z, which isn't quite right, but it's okay because we haven't yet recalculated projectile radius. We set old projectile radius to store the projectile radius, distance from the centre of the Earth, that it had before the move we just did. Then we recalculate the new radius, which is, well, the sum of which, I got it wrong. Then we recalculate the new projectile radius, the square of which is the sum of the squares on the other three sides. I told you, Pythagoras, specifying two sides as being unnecessarily narrow in scope. In 3 dimensions, you can still have a hypotenuse on a thing that is no longer a triangle, but you have 3 vectors at right angles, the x, y, and z, and the sum of their squares is the square of the vector sum of those 3 vectors, which is effectively the hypotenuse, just we're in 3 dimensions now. Then we calculate the latitude and longitude of the projectile, or of the point beneath it. So give me latitude and give me longitude kick in. And just as before, acceleration due to Earth's gravity is Earth gem divided by the square of the radius, the projectile radius, the distance from the centre of mass of the Earth. And then we very elegantly, look at that, look at those 3 lines. Let me just zoom in so you can really appreciate the beauty of those 3 lines, gx, gy, and gz. Look at that. Isn't that graceful mathematics? Those, the x, y, and z components of the projectile's acceleration towards the centre of the Earth due to the Earth's gravity. Then we calculate projectile altitude, which is projectile radius minus give me radius at the projectile's latitude, because we want to be able to keep track of its altitude. We need that to calculate the local air density, sea level density times density gradient to the power of altitude. And that's what we use to calculate drag, but the atmosphere isn't sitting still around the Earth. The Earth isn't spinning inside a stationary atmosphere. That would create problems. Really, really big problems. The atmosphere rotates with the Earth. So we can't just say that drag is based on the projectile's velocity. It has to be the projectile's velocity through the air. So we need to know how fast the air is moving. And we do pretty much the same thing here as we did for how fast the ground was moving. Before the launch, we're just using the latitude of wherever the thing is now and whatever altitude it is at now to calculate the air density. Which is up here at the top. And then just as we had to rotate the launch east and out velocities to get x and y velocities, we rotate the air's eastward velocity to get the air's x and y velocities. Then we can compare them, which mathematically means subtract the air's x direction velocity from the projectile's x direction velocity, and likewise with y. We don't have to worry about dz because the air isn't moving north and south, it's rotating around the Earth's axis to the east. So dz in air is dz. We don't worry about that part. So then we can get the projectile's velocity through the air, which is the square root of the sum of the squares of those three components. And that lets us do pretty much exactly what we did for the acceleration due to gravity. We now have the acceleration due to air resistance, which gives us drag x, drag y, and drag z. And then we can add the sum of the gravity and drag effects times the time resolution to dx, dy, and dz. This is how we move the thing and adjust its course, simulating physics, applying to it. Then keep track of maxima and minima. If the projectile's radius, distance from the centre of the Earth, is less than the previous value, it is on its way down. If it is on its way down and it is closer to the centre of the Earth than the target, then it has had its chance to get there. Either it's hit it, or it's fallen short, or it's gone way past it. But it isn't still on its way and on course to hit it anymore. So splash equals 1. Likewise, if the projectile's altitude is less than negative 400, if it is more than 400 meters below sea level, splash equals 1. Because whether you're in the Norfolk Broads or the Netherlands or next to the Salton Sea or next to the Dead Sea, 400 meters below sea level is below ground level. And then we have that same thing, that if the projectile's radius is greater than 1 gigameter, it's gone. Your GoPro is gone, bro. Then we have if step by step equals 1. If step by step is not equal to 1, everything below that's indented below that line is going to be ignored. If it is, we look at the first indented line, which is if verbose equals 1. If verbose equals 1, what's indented below that is all of these print lines, in which we print all of the data about it. Whether or not verbose was 1, if step by step equals 1, ready is input step. So it will put on the screen the word step and it will wait for you to input something. This is your opportunity to change ready to Q and just stop here. It is also your opportunity to change ready to G, which will change step by step to 0, which means you can watch it step by step with verbose output for a while, and then you just go, type a G to go, and it will go to the end, to the point where either splash or gone becomes 1, at which point it runs off the bottom of the while loop. There is a comment there, while loop ends, which is the only thing indicating the end of a while loop apart from the decrease in indent, because Python. Having run off the end of the while loop means that either you've typed a Q, or it has splashed down, or it is gone. And yeah, that's pretty much what happens. That's how you get to what's after that comment. At that point, we work out the angle through which the Earth has rotated. It's angular velocity times time. We work out the latitude and longitude of the thing's current location, which is presumably a splash. And we work out where the launcher is now, because of course the launcher is on a rotating planet, and it has been rotating with the planet the whole time that projectile has been on its way. So the new position of the launcher has new x and y coordinates, but the same z coordinate. We find out how far the thing is in x, y, and z directions with a comparison, also known as a subtraction. Find out how far it's gone. The square of the linear distance is the sum of the squares of, again, the 3 component vectors. And then we have mean radius. Where did that come from? That came from the Haversine formula, or rather from my desire to apply the Haversine formula to get the arc length. Dr. Bob the science guy, has a video explaining the Haversine formula. I copied the formula from him. I'm not ashamed to admit it. We know the launcher's radius, we know the target's radius. We just take half the sum of those two to get the mean radius. Which is not exactly right, but you can assume that over the kind of distances at which an artillery simulator is actually useful, it's going to be close enough to be right enough to be good enough to be useful. The arc length, there's your Haversine formula. Half the inverse sine, half their sine. And then we print all that output. The time, location, altitude, velocity, min and max velocity, linear distance, and arc length. And here is that program with all of that work put into it, ready to go. Menu option P is verbose. I typed AP to turn verbose on. So we are going to get to see this step by step. And then Y for yeet, and it does indeed say yeet. It should also say splash if it splashes, and gone if it's actually gone, but I'm sure you'd be able to tell from the X, Y, and Z coordinates, at least one of which would be absolutely huge if it had gone. So, after 1/256th of a second, it is at those X, Y, and Z coordinates in meters from the centre of the Earth, and a latitude of 0.87665, and a longitude of 0.615481. Have you guessed? Radians. It's printing the latitude and longitude in radians. Oops. An altitude of 202.77 meters. Well, I did shoot it at an upward angle from 202 meters, so this makes sense. With an air density slightly less than what it would be at sea level, which makes sense, and a gravity around 9.8 meters per second, which is what you expect on Earth. Components of the velocity, it is going in a direction from the prime meridian to the international dateline at 341.4 meters per second. In our direction from, what is 90 degrees west on the equator? Probably Ecuador. Towards Indonesia, or whatever's out there, at 669.8 meters per second, and from the South Pole toward the North Pole at 885.7 meters per second. Again, you would expect this from something that is 30 degrees east and being fired in a northeasterly direction. 30 degrees east and 50 degrees north being fired in a northeasterly direction. With a velocity of 1002 meters per second. This is a lot like the velocity at which the thing came back down on a much simpler program a long time ago now, where it was just, universal gravity in one direction, don't worry about the air resistance. Somehow it was told to fire at 1,000 meters per second and it came down at 1,002 and a bit. Here we have 1,002 and a little bit. So now we know where the 2 and a little bit came from. It came from the same place then as it did now, wherever that was. And we have the components of the air resistance, which are very appropriately all with the opposite sign to the components of the velocity and in a fairly similar ratio, or a similar ratio to the squares of the components of the velocity, which is what they should be. That's great. And then I let it run for a few more steps, but after a fifth of a second I was tired of going stepwise. So it got that far, and it's already slowed down to 803 meters per second, just in the first 1/5 of a second. And then I typed a G and told it to just go. Just get on with it. Get it done. Just run until splash or gone. At 33.58 seconds, it had splashed. 50.02257 degrees north and 35.52377 degrees east, which is quite a long way short of a target at 55 point some degrees north. It didn't go anything like far enough. With an altitude of negative 400 meters, which means it actually got 400 meters below sea level at that latitude before it got 140 meters above sea level at target latitude, due to the Earth having that much of an elliptical shape. Or the software went wrong. It came down with a really lame velocity of 87.6 meters per second. I say lame, that would be lame for a UK legal air pistol limited to 6 foot-pounds force muzzle energy. It's extremely lame for a military rifle bullet. You really wouldn't want to get hit by a truck doing 87.6 meters per second. You wouldn't know about it for long. Minimum max velocity, the lowest velocity it had on its way was 55.9 meters per second, which is even slower, so it was picking up speed as it came back down. The maximum was that 1,002 and a little bit at launch, well, recalculated just after launch. 2 and a bit meters per second, rounding error, frankly. Linear distance from where the launcher is now, after 33.58 seconds, to where this splash was detected, 2,932.3 meters, and the arc length 2,932.3 meters. If you want to be more precise, 277 millimeters, 936 microns for linear distance and 962 microns for arc length. Nobody cares. And then it goes straight back to the menu asking, what do you want to do next? Well, okay, this is cool. We've thrown a thing and it's gone just shy of 3 kilometers, which is itself just shy of 2 miles. Is that realistic? I don't know. And here's step by step on that. Intervals of just shy of 0.004 seconds, meaning intervals of 1/256th of a second. You can see the coordinates changing, you can see the velocities changing, you can see the altitude changing, the air density changing, recalculated from 1.169904 to 1.169542. It's everything step by step. But is this realistic? Frankly, I don't know. Because lobbing shells northeast from 50 degrees north and 30 degrees east at a target 55 degrees north is something I have never done. So obviously we should go to something with which I am familiar. This is Strensel Range. Oh, that's Alpha Range, or just part of it over there on the left. Here we have Bravo, Charlie. You can't see Delta because it's hidden. You can see a little bit of echo there. The sound, I'm going to zoom right in, show horrible resolution. The big rectangular patch of sand, centre of the screen now, is the backstop, also known as the butts. This green sausage with sand patches on one side of it is the butts, and where they get hit is just bare sand, where they don't is grass. In front of them, this pale white stripe is a gravel track running across all the ranges. In front of that is a row of metal frames on which targets can be raised and lowered. In front of the metal frames is a concrete step on which crew can stand to tend to the targets and patch up holes in them and record the scores and that kind of thing. In front of that, behind it from the crew's point of view if they're facing the targets, is a raised bit of ground with a concrete wall that surrounds them on three sides that overhangs them. And there's raised earth piled against it. This is the mantlet, and you shouldn't be shooting it, but sometimes that happens and it makes this very loud sound when it does. Sometimes bullets skip off the top and go off into the distance. I have heard and seen the effects of one of them hitting the wooden frame of the target. A beautifully neat outline of a sideways on 5.56 bullet in the front of the wooden frame and removed a foot-long part of the back of it. A big shower of splinters. Yeah. Then, from there you have a 100-metre gap, and then that is the 100-metre firing position. Then there's another 100-metre gap to the 200-metre firing position, another 100-metre gap, and a 300-metre firing position, and then there's another track. Across all the ranges at 300 metres. Back here is 400, back here 500, and here is the latitude. Latitude of the 400-metre firing position on Charlie range, apparently. There are also these little huts. That is a hut. There's another one over here, another one there. Approximately level with the 400-metre firing position. So if you're back here at 500, you're shooting past those. Better be good. At your target's down here. This is Strensall Range, northeast of York. And I have the latitude and longitude, both of one of the firing positions and of one of the butts. Or you can call this the 400-metre position, one of the butts, one of the targets. 400-metre position on Charlie range. It's kind of 450 metres on Charlie range. And the centre target on Charlie range, because you shoot on the range you are using, not at targets on the next range over. Lobbing 5.56 bullets down this range is something I have done, so this is something I can compare to real-world experience to check whether the software is actually working. It's great. Here we have the Ordnance Survey map of the same area. That's the ranges there. Cowthorpe Common, common ground which everyone has the right to use, except it's also a rifle range, so you probably shouldn't be there. Alpha Range at the top left with its separate butts, and then Bravo Charlie Delta Echo in the middle, and there's Foxtrot. And on this being an Ordnance Survey map, they have lovingly detailed the unfenced track crossing at 300 metres there. Apparently has a wall on its downrange side between Echo and Foxtrot. Fence or wall on the sides of Echo and Foxtrot. I don't remember seeing one, but apparently there is. And track or path, double line or single line of short black dashes between the ranges, where you have these little black triangles pointing outwards, such as Charlie range 100 metres, Delta range 100 metres, and around all the butts, that is raised ground. You'll also see that as a railway embankment. If you see them pointing inwards, it's a railway cutting. Where you see just a line of black dashes, that is a path. It is not raised ground. And if you look at Alpha range at 100 metres, they have triangles pointing downrange only. So there's a short, steep slope. You have 100 metres of low ground, and then a slope to the 100-metre firing position, and then 100 metres of higher ground, and just a path at 200 metres. Well, ground that is not grazing because it is bare rocks, which looks like a path, therefore is marked like a path. At 200 metres, you've got the track at 300, and the firing position isn't shown. There appears to be a path at 400. There is an actual raised ridge at 500, another at 600. And back here you can see there are also firing positions at 7, 8, 900, 1000 and 1100 metres, way back to Lamb's Hill. But they're outside the marked danger area, so they probably aren't in use anymore. Also, you might upset whoever's in these houses by shooting from that close to them. Maybe some people get permission to use them. We never did. Zooming back out, you've got the rifle ranges here now in the bottom left, and this huge danger area extending to the upper right. Danger area implying an area in which danger exists. And yes, it does. Bullets. Because every so often, just rarely, one of those bullets will skip off the mantlet and go clean over the butt. Or someone will shoot so badly the bullet goes clean over the butt. Or maybe, if you're really feeling wicked, from 600 metres on Charlie range, you could shoot past the left end of the butts on Bravo range at just the right angle and drop bullets around the 18th hole at York Golf Club. Might make golf interesting for the first time in history. You're not supposed to, of course. You're supposed to shoot along the range. Whereas the central four ranges are parallel down the centre of the danger area. Alpha and Foxtrot are angled inwards, so that the expected spread of really bad shooting left and right of the target doesn't go outside that danger area. I'm not quite sure why the danger area extends around that building north of Harim Hill. I actually not quite sure. I really don't get it. But there it is for some reason. Maybe they throw grenades there. Maybe that's a grenade practice area. Also visible are lots of pale blue features. Kidney Pond and all these drainage ditches and all these other ponds. So implying this is kind of wet. The little green marks that look like tufts of grass indicate it is rough grazing, which it is. And yes, shooting someone's sheep as it wanders across the ranges will cost you a lot of money. Also dotted around are these little numbers. There's a 17 there. And there's an 18 there. See the little orange dot above the 18? That is the actual location of the spot height. That spot there, where, well, that's an interesting feature, isn't it? This double line of black dashes implies a track. Up to that point where one of them suddenly becomes a ditch. It's a footpath along a ditch, and then it's back to being a track here. I might not try walking along that. There are lots of those spot heights around. There are also numbered contours. 20 there isn't aligned to the contour, so which is unusual. Maybe there wasn't room for it. Normally, a contour line on an OS map is numbered like this. Actually interrupted by the numbers, the altitude of that contour, and the tops of the digits are uphill. So this is a raised bit of ground. Inside that loop is more than 20 metres above sea level. Outside it is less. And that's all over it. You've got 18s, 19s and 20s, and just that one 17. This is all fairly close to level ground out in the Vale of York, which is handy because it's a rifle range and you don't really want dirty great hills getting in the way, or to be shooting up and down very steep slopes. You're going to be shooting pretty much level towards a great big artificial sand dune that will stop your bullets. And you do. From this we have the 20 metre altitude. From the previous page we have the latitude and longitude. We can now input that into our program. And, well, there it is as input. All the same Earth stuff. We have a 0.0012 drag number, which seems to match 556 ballistics charts found online. Launch azimuth has been changed to 44.45 degrees. I measured the azimuth along sea range. Launch altitude 20 metres, target altitude 20 metres. Launch latitude 54.020806 degrees and target latitude 54.024209 degrees. It's a tiny difference that is going to make almost no difference to the radius of the Earth, but I put them both in correctly. We're still running like that. We're still running verbose. Excuse me.
launch velocity 940 meters per second, because that is what you expect out of a fairly standard rifle barrel length with 4 gram, 62 grain modern NATO ammunition. And we yeeted. Not stepwise. It doesn't matter whether you're verbose or not. If you're not stepwise, it's just going to go to the end. 1.16 seconds, which is about right. The latitude and longitude are pretty much what we expected. Altitude 19.99 meters, which is where I would hope a bullet would be when the computer detected that it had gone below 20 meters altitude. At a velocity of 361.8 meters per second, it is still supersonic at that range. Oh yeah, that is the lowest velocity it achieved. The highest velocity it ever had was right after it launched, 940, and that tiny rounding error. 407 microns per second, nobody cares. Linear distance and arc length are accurate to how many decimal places here? Well, 651.712216 meters. So there's a difference in there, but it's measured in nanometers. Nobody cares. So here we have, a pretty good simulation of a 5.56 rifle shot down Charlie Range at Strensel with an elevation angle of just 0.3 degrees. Yeah, this is in my experience. This matches. So we now have this thing which, in my opinion, as far as I can tell, realistically simulates throwing things through the atmosphere on a rotating planet. We can now use this to answer similar Abel's request. Except it wasn't a real request, it was just a maths question paper. And actually we answered it correctly the first time with that formula we developed. The maximum range achieved was somewhere near 25 degrees, wasn't it? Remember? Yes, it was. So, at a launch elevation angle of 25 degrees, what do we get? Get a linear distance and arc length of 2,156.15 meters. How long was that danger area? Little bit more than that, but not much. Which is reasonable, because the area in which there is a threat of bullets doesn't need to be any longer than the maximum distance the bullets can go. Right? If an air rifle could launch a pellet 4 kilometers, a 5.56 could certainly get a bullet more than 4 kilometers, and that danger area would need to be longer. The fact that it isn't strongly implies that the people who laid it out don't believe a 5.56 rifle launches bullets any farther than the length of that area. Well, the length of that area extends behind the butts, or the length of that area from the 100-meter firing point, I suppose, rather than the total length, because the total length is all the way back to behind the 600. What if we make a change to that? Here's the change up at the top to make it clear. K is change launch velocity. Let's increase the launch velocity to 2 kilometers per second, which 5.56 just doesn't. But 2 kilometers per second, we get a range of 2,747 meters. It's still 2 and a bit kilometers. It's a sight more than it was, but it's not made 3 kilometers yet. Let's go absolutely nuts and change your launch velocity to 8 kilometers per second. Yeah, right. How? And we achieve 3,837 meters range. So, 4 times the velocity, 16 times the kinetic energy at launch. And this thing has come down less than 4 kilometers away. It's gone from 2,700 and some, was it, to 3,800 and some. Great. It's added, what is that, about 2/5 to the range for 16 times the energy. Woo-hoo. Alright, so clearly increasing the velocity, well, it's great at first for small values of velocity, increasing from 5 to 10 to 15 to 20 gets you fast increases in range. Increasing from 940 meters per second to 8,000 meters per second didn't double the range. So that's obviously not how to go about getting a thing from 50 degrees north to 55 degrees north. We need to change something else. Insert small pause here to let people suggest other things we could change. Now, earlier we had things when we weren't taking drag into account, weren't taking air resistance into account, that were going hundreds of kilometers, thousands of kilometers at stupid velocities. So obviously the thing to change would be air resistance. In fact, there was a side-by-side comparison, wasn't there? That may or may not have been high and low air resistance. How about we insert an extra 0 into that variable on option E? We can do that. Just zoom in and zoom back out to make sure the screen is updated. We can do that. First, just going to compare 20 degree and 30 degree elevation angles to confirm that neither of those gets a longer range than 25 degree elevation angle, even at this crazy velocity. And down there on arc length you can see neither of them does. Then we can insert our extra 0. There it is, drag coefficient in square meters per kilogram, 0.00012. Everything else is pretty much the same. We're back to 940 meters per second. We're not being silly. With 2 or 8 kilometers per second, we're back to realistic velocities here. This time it's taken 46 1/4 seconds to get anywhere. And it has come down 14.3 kilometers away, 14,307 meters downrange, well outside the danger area marked on the map. It's a phenomenal distance. That's out of one valley, clean over the one between, into the next valley up. Next but one valley up from where it was launched. That is a huge range that could be incredibly useful to some people who are currently approximately 50 degrees north and 30 degrees east. How do you get that extra 0 into drag? Now there may be some people who know perfectly well that when you want to shoot extreme distances you don't use 5.56, you use 338 Lapua Magnum. Lapua Magnum I think is the correct stress. Or 12.7 by 99mm, also known as 50 BMG. 338 being 8.6 by 70mm. Not only is it a whole lot more energy, it's a whole lot more bullet. If you look at a hypothetical one in between, the 11.12mm would be exactly twice the diameter of the 5.56. Let's get a little more carried away than that, because you don't use any of those rifles to shoot 14 kilometers. Let's change from having a rifle chambered for 5.56 by 45mm with a barrel length that gets you maybe 98% of the maximum available velocity, 940 meters per second, to a rifle chambered for 5.56 by 45 centimeter with a presumably much longer barrel set up to get you about 98% of the maximum possible velocity, 940 meters per second. Right. Your bullet is now 10 times as wide, 10 times as high, and 10 times as long. Sitting in the neck of a case is 10 times as wide, 10 times as high, and 10 times as long, containing a mass of powder that is 10 times as wide, 10 times as high, and 10 times as long. So when you're calculating that drag times cross-section over mass, right, the bullet's shape is the same. It is the same shaped object going through the same air. The air density is the same, the air viscosity is the same, the turbulence is the same. How badly this thing stirs up the air as it goes through it is going to be the same multiple of cross-section times square of velocity. and how much air there is in the way for it to stir up is going to be the same. Pardon me. The same density, but obviously it's a larger volume. That cross-section applies. The cross-section of its path through the air, because it's 10 times as wide and 10 times as high, is 100 times as big. It is disturbing 100 times as much air, equally badly, at the same velocity. So it is going to experience 100 times the force of air resistance pushing back on it at that velocity. But being 10 times as wide and 10 times as high and 10 times as long, it has 1,000 times the mass. 100 times the force on 1,000 times the mass gives you 1/10 the acceleration in the rearward direction, 1/10 the rate of loss of velocity, loss of forward speed, which means it's going to take 10 times as long to get from 940 meters per second down to 900, and 10 times as long to get down to 800, and 10 times as long to get down to 700, which means it's going to travel 10 times as far in that interval. It's going to be 10 times as far downrange before it gets down to 900 meters per second, and 10 times as far downrange before it gets down to 800 meters per second, and so on, as the 5.56 millimeter was. And that is how this thing is able to reach 14.3 kilometers. Tiny change. Oh, launch elevation, 40 degrees. There's a tiny change. We've cranked it from 25 degrees elevation to 40. Why? Well, the reason we were down at 25 degrees was that air resistance was slowing down our projectile so quickly, right? Well, it's not anymore, is it? We've got so much less drag now that it's worth going back up towards that 45 degree elevation angle that is optimum with 0 air resistance. And as you can see at the bottom, oh wait, let me do that zooming thing to make sure you can see. There we go. J for elevation angle, end of 40, there it is. It's been set to 40, yeet, 66 and 3/8 seconds. And this thing was still doing 222 meters per second, even at the top of its arc. Came down at 256 meters per second, 16,559 meters downrange. So we are now getting longer range at 40 degrees elevation than at 25, which we weren't with the 5.56 millimeter rifle. Okay. Is this right now? Is this thing now perfectly simulating it? Well, I'll insert a pause so you can discuss it among yourselves. Just, don't take too long. Well, if your answer to is it working correctly was we can't tell because this was supposed to distinguish between shots to the east and shots to the west, and you haven't compared them yet, congratulations, you were paying attention, and thank you for that. It makes me feel all validated and warm and fuzzy. So, very slight change. Launch azimuth is now 45 degrees. Tiny change. And the result of that tiny change is that it goes 16,559.19 meters, or 16.56 kilometers, which is pretty much what it was doing before. Because it was a tiny change in azimuth, you wouldn't expect much of a change in results. We can compare those results to these results, where we have changed the launch azimuth to 90 degrees. We are shooting due east. And now we get 66.25 seconds, 54.01990 degrees north, and 0.502144 degrees west, which is kind of... What was our launch longitude? Our launch longitude is 1 degree west, so it is now half degree east of where it was, which is about 55 kilometers. Having travelled 16.5 kilometers. So maybe that's not working perfectly. Maybe the thing with how much the Earth has rotated and where the launcher is now isn't quite worked out right. Oh! Yes, the location is in an XYZ reference frame that was aligned to the Greenwich Meridian and 90 degrees east and the North Pole at the time of launch. Right, so it is now at minus half a degree west in that reference frame, but the Earth is no longer aligned there. That explains it. Sorry. Yes. I remember. Maybe more significantly, our distance is now 16.54 kilometres rather than 16.56. Which I think is a little odd. But launching it the same way, but on every 15-degree increment of azimuth, we get these ranges. You get this compass rose of ranges. And over here on the right we have 16.54, over here on the left 16.51. So it goes 32 metres, just under 32 metres farther east than west. That's great. That is what we expected. What bothers me is that it goes 16561.22 on bearing 030 and 16489.46 on bearing 210. Why would it go farthest slightly north of northeast and the least distance slightly south of southwest? This I found strange. I was not happy with this. You can also see at the top and bottom the negative 0.75463 and negative 0.758035. Those are the longitudes at which it landed. Again, this is in a reference frame that is still aligned the way it was when the shot was fired, not in a reference frame that's correctly aligned when the shot comes down. If I ever want to actually seriously use this program, I should fix that. And here we see that a shot sent due north has landed farther east, and a shot sent due south has landed farther west. This you would expect. Honestly, I'm confusing myself with reference frames here. You would expect a shot fired straight at a target at a great distance, when firing away from the equator at a latitude between the tropics and the pole, to miss to the east. And a shot fired directly at a target, well, with the correct elevation, but azimuth directly at a target, a great distance toward the equator from any latitude outside the tropics, to miss to the west. Because the launcher is going east, the launcher is on ground that is going east faster than the target, faster than the ground under the target, if you're shooting away from the equator, and not as fast as the ground under the target if you're shooting towards the equator. So in the time it takes the shell to get there, the shell goes a certain amount east in the direction of rotation, turn-wise, to borrow from Terry Pratchett. The target farther from the equator goes less distance turn-wise, and the target close to the equator goes more distance turn-wise. Therefore your shell comes down ahead of a target farther from the equator, behind a target close to it, meaning east and west respectively. So that was fine, but this thing with the distances not matching, that bothered me. And due north and due south, the distances don't match. It goes farther north than south. And for a while I didn't have an explanation of why, which also bothered me. Well, if your answer to is it working correctly was we can't tell because this was supposed to distinguish between shots to the east and shots to the west, and you haven't compared them yet, congratulations, you were paying attention, and thank you for that. It makes me feel all validated and warm and fuzzy. So, very slight change. Launch azimuth is now 45 degrees. Tiny change. And the result of that tiny change is that it goes 16,559.19 meters, or 16.56 kilometers, which is pretty much what it was doing before, because it was a tiny change in azimuth. You wouldn't expect much of a change in results. We can compare those results to these results, where we have changed the launch azimuth to 90 degrees. We are shooting due east. And now we get 66.25 seconds, 54.01990 degrees north, and 0.502144 degrees west, which is kind of... What was our launch longitude? Our launch longitude is 1 degree west, so it is now half degree east of where it was, which is about 55 kilometres. Having travelled 16.5 kilometres. So maybe that's not working perfectly. Maybe the thing with how much the Earth has rotated and where the launcher is now isn't quite worked out right. Oh! Yes, the location is in an XYZ reference frame that was aligned to the Greenwich Meridian and 90 degrees east and the North Pole at the time of launch. Right, so it is now at minus half a degree west in that reference frame, but the Earth is no longer aligned there. That explains it. Sorry. Yes. I remember. Maybe more significantly, our distance is now 16.54 kilometres rather than 16.56. Which I think is a little odd. But launching it the same way, but on every 15 degree increment of azimuth, we get these ranges. You get this compass rose of ranges. And over here on the right we have 16.54, over here on the left 16.51. So it goes 32 metres, just under 32 metres farther east than west. That's great. That is what we expected. What bothers me is that it goes 16561.22 on bearing 030 and 16489.46 on bearing 210. Why would it go farthest slightly north of northeast and the least distance slightly south of southwest? This I found strange. I was not happy with this. You can also see at the top and bottom the negative 0.75463 and negative 0.758035. Those are the longitudes at which it landed. Again, this is in a reference frame that is still aligned the way it was when the shot was fired, not in a reference frame that's correctly aligned when the shot comes down. If I ever want to actually seriously use this program, I should fix that. And here we see that a shot sent due north has landed farther east, and a shot sent due south has landed farther west. This you would expect. Honestly, I'm confusing myself with reference frames here. You would expect a shot fired straight at a target at a great distance, when firing away from the equator at a latitude between the tropics and the pole, to miss to the east. And a shot fired directly at a target, well, with the correct elevation, but azimuth directly at a target, a great distance toward the equator from any latitude outside the tropics, to miss to the west. because the launcher is going east, the launcher is on ground that is going east faster than the target, faster than the ground under the target if you're shooting away from the equator, and not as fast as the ground under the target if you're shooting towards the equator. So in the time it takes the shell to get there, the shell goes a certain amount east in the direction of rotation, turn-wise, to borrow from Terry Pratchett. The target farther from the equator goes less distance turn-wise, and the target close to the equator goes more distance turn-wise. Therefore your shell comes down ahead of a target farther from the equator, behind a target close to it, meaning east and west respectively. So that was fine, but this thing with the distances not matching, that bothered me. And due north and due south, the distances don't match. It goes farther north than south. And for a while I didn't have an explanation of why, which also bothered me. So due to being bothered by that, I went back to the familiar rifle range situation. I didn't go back to 0.3 degrees elevation, I went to 1.0 degrees angle of elevation. But we are back to 0.0012 for that drag value, 940 meters per second, very low angle of elevation. And shooting on the left, due north, and on the right, due south, we have these things starting at 30 degrees east and coming down 35.277 east and 35.275 east. Just 1.5 seconds later. This was not expected. Also, if you look at the distances at which they come down, and the latitude at which they come down is fine. One of them's gone 0.0082 degrees north, one of them has gone 0.0089 degrees south. So they've gone in the correct direction in terms of latitude, but why they've gone that far east is a bit weird. Look at the linear distance and arc length, 911.645 meters north, only 766.859 meters south. Why? This was definitely bothering me at this point. When you go and lay on the floor and stare at the ceiling to save your brain the effort of keeping yourself upright while it thinks about what you may have gotten wrong. I can't remember all the thoughts I had and all the lines of code I checked, but I launched from longitude 0.0 degrees. Makes it simpler, doesn't it? Just start at longitude 0 so you can see what's really going on. And took this shot. Where's the azimuth? Azimuth also 0.0, shooting due north. Going step by step with full output, so one step of 1/256th of a second. We've got those coordinates, those velocity components, that latitude and longitude. The longitude is not 2.848, it is 0.00000002848. E negative 07 is times 10 to the negative 7, which means move the decimal point 7 places to the left. Or the decimal point has been moved 7 places to the right, if you prefer. Rather than printing all the zeros, it's easy to put E negative 07 on the end at that point. Again, radians really should fix that. And we've got all the other output there. For the first 2 steps, and then for more steps, well, the first 3 steps. And I looked at this and thought, I don't know what's wrong here. And eventually it came down. At a distance of 1,190 meters. 50.01 degrees north and 0.014 degrees east. After 3.336 seconds. Now, if a fiber optic gyroscope sitting on a desk in an office somewhere picks up a drift, a 15 degree per hour drift. Thanks, Bob. That's 1 degree in 4 minutes, which is 1 arc minute in 4 seconds, 1/60th of a degree per second. In 3.36 seconds, you would expect 1/20th and 1/200th of a degree, and that's not where it's come down. I remain confused and annoyed. Another shot. And my understanding was not improving. Like, at all. If you see anything in there that explains what was going wrong, feel free to tell me. And there it is coming down at 1096.48 meters after just 2.82 seconds. And the different shot, 3.09 seconds, 1147 meters distance. There we go. And so on. Slightly different results at slightly different azimuths produce eventually this. And on this, because I have shortened the range, reduced the angle of elevation and increased the susceptibility to drag of this projectile, we have reduced the difference between shooting east and shooting west down to just not quite 3.5 meters. We've got 537 2/5 to the right and 534 to the left, to the nearest fifth. Sorry, to the east and to the west. Top and bottom, north and south, 705 meters north, 303 meters south. There's this huge difference. And now, with this shorter range shot, I've created a situation where due north is the longest range and due south is the shortest range. And now, as far as I am aware, that is not right. At this point, I did have a thought about this thing. I had a thought that, if you remember all that stuff with sines and cosines, I was rotating things by an angle which is how much they're tilted back from the equator. That's fine because that's correct for your latitude. But treating that as also being the angle from the centre of the Earth to that object, and that's not quite right. This not quite right part was shown up with my camera simulations earlier, as in months, maybe years ago now, when I simulated the view from Southport Beach past Blackpool Tower to the Lake District, and simulated the view from Marbella across to the top of the Rock of Gibraltar and the top of Jebel Musa, with the Mediterranean in the way, obscuring the lower mountain in front of Jebel Musa, as which it had been incorrectly identified by some individual. Looking north and south, it worked fine. Looking east or west, my program and spreadsheet, both doing the same calculations, both produced sloping horizons. The horizon was visibly sloping, slightly higher on the equator side of the image and slightly lower on the pole side. Because I had straight down within the camera, pointing at the centre of the Earth, not in the direction of gravity at its location. Straight down as shown by a plumb bob at somewhere on the surface of the Earth, outside the tropics and the polar circles, or anywhere that isn't the equator and the pole, but let's say outside the tropics and polar circles, is beyond the centre of the Earth. If you're 50 degrees north or 55 degrees north, straight down is pointing at a place that is south of the centre of the Earth. But I'm making my shot assuming that straight down is towards the centre of the Earth. So my supposedly level turntable on which I'm setting up this azimuth is tilted towards the equator. And that means if I'm pointing away from the equator, I'm shooting at a higher angle than if I shoot towards the equator, and that would create this effect. All right then, we've got a candidate to solve this problem. So what do? Well, I've got, polar and equatorial radius as variables, and I go into the software and I set them to both be the same value, and that should solve that problem. That takes care of that. It means that the program's doing a lot of work it doesn't need to do anymore, but it solves that problem. And now we should get the results we expect to see. And we got... Interestingly, it did reduce the problem. But it didn't get rid of it. Range to the north is still greater than range to the south. And even worse, the range to the west is now greater than the range to the east. So it was at this moment that I knew this program wasn't working. This moment right here. Which puts me somewhere in that low bit in the middle of the Dunning-Kruger graph with Mount Stupid up in the top left and people who actually know their stuff up in the top right. I'm in that bit where I know I don't know my stuff and need to listen to the people who are in the top right. So I went to one of them, scienced it out, and said, hey, this ain't working. But I've got this other idea for a different approach I could take to this. Would it work? And he gave it some thought and said, yes, that should work. So I rewrote the whole program and took that different approach. And it was worse. So I eventually uploaded the entire script to Discord, and he and someone else looked over it and could not find the problem. That makes 3 of us. Eventually the third person described it as a possible undocumented, unintended behaviour, presumably of PyCharm, which I think is a lovely way of saying something appears to be going wrong and nobody knows why. Yeah, we already actually knew that, but it's great. Doesn't it sound good? Possible undocumented, unintended behaviour, also known as bug. Yeah. Well, I felt a little better about it when, nobody could see what I'd done wrong. Okay, so I'm right that there is something wrong here, and apparently I haven't made a total mess of it myself in any obvious way. They looked at it and they thought it should work. So, we don't know. But, well, it was never really meant to be precise, was it? It was only meant to be good enough. Now, is that good enough? Probably not. It was never going to be precise because of this thing. What is this thing? This thing, I have zoomed in too far for you to see what this thing is. This is a photograph I took in Iran. To zoom out to see what it's a photograph of. Oh yeah, that. See, that is a lot smaller than the Earth and has a lot less mass than the Earth, and it's a lot farther away from similar Able, or some dude 50 degrees north and 30 degrees east, or someone at Strensel Range, than the Earth. And a gravitational pull on a bullet on the way down Strensel Range, or on a medicine ball on its way across your sports field, is a lot less than that of the Earth. But it's not zero. So if you really want to be precise, you need to include that thing's gravitational pull. And of course, that thing's going round the Earth, so the direction of that gravitational pull changes. So you need to take that into account. So you want to know the time and the phase of the moon, or the longitude of the moon. But it's a little worse than that, because that isn't going round the Earth. Technically speaking, that and the Earth are going round each other. Now, this is yet another one of those approximations you can ignore a lot of the time. Sorry, approximations you can use a lot of the time, is saying that the moon can go around the Earth. The technicality that the moon and the Earth are going around their shared centre of mass is the thing you can ignore a lot of the time. if you want to know the direction to the moon, if you want the latitude and longitude of the sublunar point, if you want the phase of the moon, you don't actually care about this detail. If you're trying to understand tides, if you want to know why we have 2 high tides per day rather than just one where the water is pulled towards the moon, the explanation involves the fact that the Earth and the moon are going around their shared centre of mass. These are GM figures for the Earth and Moon. From NASA, I've shifted the decimal point to be SI notation, so rather than 0.39860 times 10 to the 14, it's 3.9860 times 10 to the 15. It is 3.9860 times 10 to the 14 for the Earth, and rather than 0.00490 times 10 to the 15, it is 4.90 times 10 to the 12 for the Moon. Same thing. Either way, 4.90 times 10 to the 12 is only 1.21% of the combined mass there, which would be 4.035 times 10 to the 14, something like that. 1.21% of it is the Moon. Therefore, the centre of gravity, centre of mass, is 1.21% of the way from the centre of the Earth to the centre of the Moon. And we're both going around that. 1.21% is a small fraction, but it's a big distance. And the Earth is huge, but not huge compared to that distance. Where is that, you may need to know? Well, it's actually inside the Earth. 1.21% of a very long way indeed to the Moon is inside the Earth. So to scale, seriously, Earth and Moon to scale, the barycenter is there, nearer the surface than the centre, but inside the Earth. That means if the Moon is overhead, you're going in the same direction as the Moon, east, due to this orbit. But because the Earth is spinning to the east, the Moon appears to be going west, because the Earth's rotation is carrying you through that space between the Earth and the Moon. If you're on the opposite side, where the Moon is the far side of the Earth beneath your feet, you're also going east due to this rotation, the orbit of the two, and due to Earth's rotation, you're going faster. Going faster means you weigh less. If you're on the, in this view, the near side or the far side, where the Moon is due east or due west of you, moon rise or moon set, you are going up or down, not necessarily in that order. If you're on the far side where the Moon is setting, you're going down due to this Earth-Moon orbit. If you're on the near side where the Moon is rising, you're coming up. So you have this change in weight, where stuff weighs more at moonrise and moonset and less when the Moon's overhead or directly below. And that, the fact that it weighs less in two places is where you get the two full moons. The two high tides. I'm very old and very tired and my brain does not work properly anymore. Having two places where stuff weighs less due to this and two places where it weighs more around that path around the middle of the Earth is where you get two high tides. The same can be said of the Earth-Moon system orbiting the Moon, orbiting the Sun. Grief. I've been thinking I need to cut down on my caffeine consumption. So when I get up, I only have 1 cup of coffee. Then I get a cup of coffee with my breakfast. Then when I go to work, I tend to have a cup of coffee, like the kind of cup of coffee you get with a donut. Only I never get the donut, I just get the cup of coffee. It seems to have worn off. Yeah, the Earth-Moon system goes around the Sun. Again, that's the approximation. Really, everything, including the Sun, is going around the shared centre of mass of the solar system. But an approximation of the Earth and Moon together going around the Sun is a really good approximation. And that means at full moon, when the Sun is out in one direction and the Moon is out in the other direction, you're going east on the surface of the Earth due to this Earth-Moon rotation, and that direction is opposite to your travel around the Sun. at midday. And at midnight at full moon, you are going east due to this Earth-Moon orbit in the direction of the Earth-Moon system's orbit around the Sun. So you're going slower at midday and faster at midnight. Whereas at new moon, when the moon is approximately between the Earth and the Sun, you are going faster at midnight and slower at midday because of this orbit. And at dawn and dusk, sunrise and sunset, you're either going up or down again. Sunrise you're going up, sunset you're going down, due to your orbit around the Sun. So these combine to give you two poles. One is towards and away from the moon, humping up the water. The other is towards and away from the Sun. And at different moon phases, when the direction to the moon and the direction to the Sun are at different angles, you get different heights of tide. That's why you have those funny tide height diagrams. So if you really wanted to account for, all of these gravitational pulls, you really ought to take into account the state of the tide, in effect, which means you need to know the phase of the moon and the time. Is it that simple? Oh, no, it's not. From NASA. Over on the left, details of the moon. In particular, if you look at the mass and the GM, you'll see the exact same ratio, 0.0123. The moon has just about 1/80th the mass of the Earth. Our moon, that is, specifically. But over on the right, we have some details about the orbit. The moon, and this is, again, it's described as the moon's orbit around the Earth because that's good enough. And in particular, you've got the distance, semi-major axis in millions of kilometres, 0.3844. Yeah, 0.3844 times 10 to the 6. Also known as 3.844 times 10 to the 5. Or 384,400. But immediately below that, perigee and apogee. The closest it gets to the Earth and the farthest it gets from the Earth. 363,300, 405,500. Yeah. So see, if you want to work out in really accurate detail the moon's gravity, you don't just need the moon phase and the time. You also need to know where in its orbit it is, because the full moon and the new moon occur at different points in that orbit, going around from perigee, measuring it that way, over the course of a year. So you need to know the date and, just keep reading down, inclination to Earth equator in degrees, 18.28 to 28.58. Because the Earth's axis is tilted one way and the Moon-Earth orbit is tilted another, and at some times of year it's lined up and at others it isn't. And line above that, inclination to ecliptic, 5.145 degrees. That's why we don't get a solar eclipse and a lunar eclipse every lunar month. It is because the moon's orbit is tilted 5.145 degrees to the Earth's orbit around the Sun, to use the approximation, which looks something like this, down here at the bottom. There are 3 yellow lines coming in from the left because the Sun has that angular size. It is not a single point source. It is quite large. Coming to the Earth, and to scale with that Earth, the distance to the Moon is way out here at perigee and way over here at apogee, and that is 5.145 degrees tilt there. So it's nowhere near casting a shadow on the Earth, and nowhere near the Earth's shadow up there. At a different time of year, when that orbit is crossing through the plane of the Earth-Moon system's orbit around the Sun, which of course isn't a plane because the Earth is wobbling around it in that same orbit, then you can get an eclipse. But only at those 2 points in the orbit, those 2 times of year. And what does a lunar eclipse look like? Well, to scale, lines coming from top, centre and bottom, north, centre and south, a visible part of the sun, hitting the Earth and stopping in the middle and passing it, north and south there, create this full umbra, the black space in the middle, and the penumbra, where there are just some lines, not lots of lines, at the edges of that. And by the time they get out to the moon, the penumbra is considerably larger, the umbra considerably narrower, but the moon is smaller than the umbra, which is why you can have a total lunar eclipse that lasts quite a while. And yes, to scale with the size of the moon, the difference between perigee and apogee is that far. The reason it's shown red, go back to that Himawari photograph of just before sunrise, with red light being refracted around the Earth's atmosphere, around the Earth by the Earth's atmosphere, and lighting up the clouds. Well, some red light gets refracted down around the Earth and then escapes from the atmosphere and hits the moon. And in a total lunar eclipse, the moon is lit up red by a little bit of sunlight that came through the Earth's atmosphere. Not very brightly. Alan Evans' trick here, a correctly exposed photograph of the full moon with stars. If you catch it during a total lunar eclipse, it's so dark that you can correctly expose it with a large enough aperture and a long enough exposure time to also photograph stars. If it's not in an eclipse, it is so brightly lit by direct sunlight that correct exposure for the moon, you won't see the stars at all. There's also the second largest mass in the solar system, that big stripy fellow there, which has 4 little friends, the Galilean moons of Jupiter, in no particular order: Callisto, Io, Ganymede and Europa. Observing those was part of how Kepler worked out his laws of motion. Now that is a lot farther away than the moon, and in fact a lot farther away than the sun, but there is a heck of a lot of it. Its moons are quite small, and about as far away as it is, but you really ought to take them into account. I mean, it has nearly 318 times the mass of the Earth. That's huge. It's a gas giant, so instead of a surface radius, they have a radius to the altitude at which you get 1 standard Earth atmosphere of pressure. And it's 11.2 times as far at the equator of Jupiter as it is to sea level at the equator on Earth. Just quite big. Jupiter is huge. Very low mean density because it's a gas giant, of course. And right down at the bottom, oh, yeah, it has 4 little friends, does it? No, it has 92 little friends. It's just that only 4 of them are big enough to be seen with a telescope that was available during Galileo's time. There is the URL to go to find the article from which I copied this image, showing from 3 different angles the orbits of Jupiter's moons, or at least some of them. Probably not all 92, I haven't counted. Who else would you need to take into account? Dr. Becky Smethurst's favourite, Saturn, with a much more prominent ring system than Jupiter, and in fact, all of them. This, just for the record, is a painting, not a photograph. We haven't sent a camera out there to take that picture and brought it back. It's an illustration. And nobody's pretending it's an actual photograph of the Milky Way. It's just to give you an idea. But really, the fact that we're going around that thing at 25,000 light years and once every 200 million years, that is going to affect your trajectories, depending which side of the Earth you're on at what time of year. Not by much. But if you really, really want to be precise, you would have to take that into account. You wouldn't bother because good enough approximations are good enough. Especially if you're in an artillery unit and you're throwing those 155mm shells downrange. Because if you're aiming at the little window in someone's front door and you hit the cat flap instead with a shell that turns a house into a rockery and a lawn into a fish pond, yeah, that counts as a direct hit. But even if you did take all this into account, even if you did the whole, Barnard's Star and Betelgeuse and Bellatrix and Risa and Anitark, Anilar, Mintaka and Safe and Rigel and Sirius and Vega and Polaris and Proxima Centauri, because that one's actually close, relatively speaking, a mere 4 light years away, right? And all those other stars, and Mercury and Venus and Mars and Phobos and Deimos and Neptune and Uranus, and I got those two the wrong way around, and Pluto and Ceres and Halley's Comet and everything, it still wouldn't be right. Still wouldn't quite be right. Why? Newton did all his calculations, worked out all those formulae, and showed that they worked, and convinced the world that they worked, and they do. But they're an approximation. They're an approximation that is good enough for every job on Earth. Until you go to somewhere like CERN, or you want to image a black hole, or something like that. Or you need GPS. GPS doesn't work on just Newtonian physics. GPS has to use something a little more complicated, given to us by Albert Einstein. Oh yeah. So if you do all the calculations based on Newton's formulae and everything that was available pre-Einstein, you can calculate the trajectories of all the planets around moons and moons around planets, and planets around stars, and stars around the galaxy and everything. And you can predict that the orbit of Mercury, which is one of these elliptical orbits where it's closer at one side than the other, should change in orientation over time. The direction from the Sun to Mercury, at the moment Mercury is at its greatest distance from the Sun, should change. But if you work it out with Newton's physics, you calculate that it should change at 531 arc seconds per century, which is just shy of 9 arc minutes over a whole century. And it doesn't. It changes at 574, a difference of 43 arc seconds, 3/4 of an arc minute per century. So, go to a firing range, look at the 100-yard target, look at 3/4 of an inch on that target. Now, over the course of a century, that direction from the Sun to Mercury is that angle, the angle subtended at your position by that 3/4 inch blob, different from where it would be predicted by Newton's physics. General relativity predicts the full 574 arc seconds. General relativity also accounts for light bending as it passes a black hole, and certain other things with these tiny subatomic particles and phenomenally high densities and very long periods of time. So for any job in which you are not using things travelling at or very close to the speed of light, or making predictions 100 years in advance, or messing about trying to bounce subatomic particles off each other, you probably aren't bothering with general relativity. You use Newtonian physics, which is far easier, and you just correct your course once every 10 years or so, and avoid going faster than half the speed of light, and you're fine. It's a good enough approximation. And speaking of good enough approximations, we're back to having the correct dimensions of the Earth. We're back to launching at 45-degree angle of elevation. In this case, we are 45 degrees north and 0 degrees east as an arbitrary location from which to launch. Launching at 0 meters altitude, just arbitrary, launching from sea level, with a launch velocity of only 11 meters per second. Our results, 1.59 seconds to achieve a range of 12 meters, 224 millimeters, 409 microns, 401 nanometers, 430-ish picometers, and honestly, nobody cares about the picometers. Like bond length in a water molecule country here. Right. What are these green lines? Well, those green lines are across to the BBEM. 12.334 meters, 12.224 meters. A difference of 11 centimeters. Width of the palm of my hand plus my thumb. 11 centimeters. At more than the... probably more than the width of a classroom away. Is that length for badminton courts? 12.22 meters? It's something like that. So it might make the difference of whether your shot was out or in tennis, but it's not going to make a huge difference. So in terms of demonstrating this principle, this concept, demonstrating that distance range is proportional to the sine of twice the elevation angle and to the square of the launch velocity, at these velocities, good enough. The compass rows of results, just to show that yes, it is still being weird and sending things farther west than east and farther north than south. Probably due to rounding errors. But they are all approximately 12.2 degrees, 12.2 meters range. So around 12.2, or 12 and a fifth to 12 and a third meters expected range at that velocity. Another mathematical approximation for which I don't have a slide prepared. Another hypothetical exam paper question. A sprinkler wets an area with a radius of 10 meters. Flexible fencing is sold in panels 2 meters long. How many panels are required to fully enclose the area wetted by the sprinkler? Now, this is already an approximation because it's not taking into account the width of the fence posts or fastenings between panels or whatever you're going to do there. It's just asking you to recognize what you need to do to give an answer and then perform it correctly. The crude approach to this would be to say that the circumference is 2 pi r. So if radius is 10 meters, 2 pi r is 20 times pi. And then you can approximate pi to be 3.15, which is 3 and 3/20ths, which gives you an answer of 63 meters for your circumference. You then divide this by 2, which is the length of a fence panel, to get 31.5. Well, you're not going to go and buy half a fence panel, so the answer is 32 fence panels. The better way to do this would be to say that the number of fence panels you need is 2 pi r over 2. Cancel out the 2's and just multiply pi by the radius, which is 10 meters, which is really easy. You just move the decimal point in pi one place to the right. If your approximation for pi is 3.142, you need 31.42 fence panels. And you're not going to go and buy 0.42 of a fence panel, so you need 32 fence panels. If your approximation for pi is 3.1415965, then you need 31.4159265 fence panels, and you're not going to go and buy 0.4159265 fence panel, so the answer is 32. So you can calculate, you can store pi. You can get one of those T-shirts with the first 1,000 digits of pi on it, or however many digits they print on them these days. You can calculate all of them if you want to, but the answer is 32, and you get that just from the first 3 digits. So it's a good enough approximation for that job. And the more decimal places of pi you use, the smaller your error gets, down to the point where thermal expansion of the fence panel as you flex it is going to change its length by more than that. So using that many decimal places gets more and more silly the more you use. Here's a different approximation. Southbound on the M1. It's a blue sign, so it's a motorway. At the top, M1, it is the M1, the very first motorway in Britain. Links London and Leeds. In the direction of the south. Next destinations, Rotherham 12, Sheffield 19. This being UK, those are distances in miles. So when you see this sign, you know you have 19 miles to go to get to Sheffield, if that's where you're going. You are 19 miles from Sheffield. If you're driving to Sheffield, you will arrive in Sheffield having covered 19 miles more than you have already covered. Right, now is that 19 miles from the sign, or from where you are when you read the sign? And when we say into Sheffield, well, here's Sheffield. Way up here in the top right is a little bit of the M1, an M1 junction. And we have some major roads coming this way. And Sheffield city centre is this area here. We have Peace Gardens and the Millennium Gallery and the Moor Market and Sheffield Cathedral and so on. Possibly somewhere in Sheffield is a big copper nail hammered into the ground and marked this spot right here. And that 19-mile distance is from that spot right there. This does not apply to Middlesbrough, because if they hammer a big copper nail into the ground in Middlesbrough, someone will dig it up and sell it for scrap. But even if there is a nail there, you're not actually going to that spot. You're going to somewhere in Sheffield. You're going to some car park or someone's house or some shop. And you don't know for sure how many times you're going to change lane, and that's going to affect your distance. So you don't need to know to the yard or to the foot or to the inch or to the barleycorn how far it is to that copper nail in the ground in Sheffield, should such a thing exist. You want to know that it's roughly 19 miles, so it's going to take you roughly 20 minutes, or 25 depending on traffic, or maybe 40 depending on traffic. And you're going to burn roughly half a gallon of fuel, or 2 litres-ish. And you use that to decide whether or not you're going to stop for coffee before you get there. You're not trying to predict when you're going to arrive to the nearest second. So roughly 19 miles from roughly there on the road is a good enough approximation for the job for which it's being used. Here's another approximation. Some people may be offended hearing this called an approximation. This is the Ordnance Survey 1 in 25,000 scale outdoor leisure map. In particular, this is showing Coniston Moor, obviously over on the left, Mossdale, the valley that is in the centre and left of the image, and a little bit of Nidderdale over on the right. Friarhood Gill, Rotten Heath Wham, what a name, and South Gill come together and run down a privately owned gully called Howstein Gorge, which you can visit. It's not necessarily safe to do so, but you can. There are public footpaths, rights of way, routes along which you have the legal right to walk. They are marked on these maps with these short green dashes that will bypass Howstein Gorge, so you don't have to pay to get in, and you can walk from Nidderdale, from the side of the Nid, down down the steep hill from Middlesmoor, across from Lofthouse, on the 27 Dales Way route, up this line of short green dashes, north of a wall and up across this rough grazing with significant gradient, up to this ridge at 540 metres above sea level. The solid black line marks a wall that's running along the ridge. You cross it, presumably at a gate where it's labelled Sandy Gate. There are also boundary stones marked BS. It stands for boundary stones. Then on the other side of that wall, the short dashes become long dashes because on the west side, on the way down into Mossdale, it's a bridleway. You have the legal right to ride a bicycle or a horse on that route. Good luck actually doing either. You might have more luck with a canoe some days. And as you go down, you can see that you'll be setting off on one bearing and then you swing to the left to follow the route, if you can find it on the ground. You'll pass between the 4th and 5th from the top in this row of grouse butts sloping down the side of the valley. These are open-topped and open-backed wooden boxes sunk into the ground in which rich people like to spend a day standing with a shotgun and a dog and occasionally murdering birds. Having passed the grouse butts, you'll also cross this track, the double line of short black dashes going straight up and down the side of the valley, which is probably how the truck comes round to deliver lunch to all of those people with their shotguns. And then you go past a little trickle of water on your right. You take a slight turn to the right because the bridleway changes orientation a little. Cross a stream. Come down past this little black square, which is not a parked Ford Escort. It is some sort of building. And then onto an actual visible path on the ground. Won't that be nice? Follow that down to where there is another building on your left, and in fact it becomes a track in front of that building. FB, footbridge. You can cross on a footbridge. You're on a track, and you go to a slightly offset, slightly kinked crossroad of tracks. Turn left and follow the track. I'd call that bearing 220 just by eye. To a loop in the river, where the track kinks to go approximately, I would say, 235-ish. And you follow that track, which is visible on the ground. It's going to be very easy to follow. I've been there. I've made video from the bottom end of this river. And you can follow that track out and over to Coniston Dib. It's in fact the 27 Dales Way route, over down Coniston Dib and up Littondale. We have a whole lot of other features here. Other rows of grouse butts, more footbridges, more tracks. Line of shafts, mines disused. Shafts disused, area of disused mines. Worth staying out of there at night. You might fall down one. The blue grid on here is a 1 kilometre grid. And they are approximately squares. Again, it's a usable approximation. If you actually work out how much difference Earth curvature makes to the scale on a flat paper map that is only showing whatever size one of these shows, it's really tiny. It's like, oh, I'm sorry, I was standing on the strip of grass between the wheel ruts, not in the left wheel rut. My bad. What a terrible mistake. This particular blue line across the north side of this grid square is 357 pixels long. These green dashes marking the bridleway are approximately 3.57 pixels wide, which means, as shown on this map, that bridleway is 10 meters wide. Yeah, it's more like half meter wide, slightly less dense rough ground, rough grazing, heather bushes and so on, and slightly more mud, where it's slightly easier to walk and you're considerably less likely to disturb a grouse nest. It is not a 10 metre wide strip, and if you look at the track crossing it there, south of that line of grouse butts, that's shown even wider than the green strip. So that would be, what, one lane each way with a central turning lane down the middle? It isn't. It's just about wide enough for one of those little gator vehicles. The solid black line marking the wall, that's maybe a pixel and a half-ish, so maybe 5 meters thick on the map. Of course the wall isn't 5 meters thick, but you don't need to know where the wall is to the nearest quarter of a meter. You want to be able to easily spot that there is a wall there. So there's a kink in the wall here, and it's not necessarily count the individual pixels and multiply appropriately that many centimeters from this wall junction just south of it, but it's probably accurate to within a couple of paces. So you can use this to navigate. You just wouldn't want to use it to try to play marbles. Of course, you're using it to navigate, not to play marbles, so it's a good enough approximation for the job for which it's intended. People who have been studying physics may recognise this one. I think this is a GCSE physics kind of thing. We have a big cylinder with a piston that moves up and down it, or left to right within it in this case, containing a volume V. We have a little rim around the inside near the base just to stop that piston crushing the probes, because I'm nice like that. And we have a couple of probes inserted through the base, measuring temperature T and pressure P. And the ideal gas law tells us that PV over T is a constant for an ideal gas. This means if you lock that piston in place and increase the temperature, the pressure will increase in proportion to the temperature. Now, I should point out that's absolute temperature. Going from 10 centigrade to 20 centigrade is not doubling the absolute temperature. Going from 40 Fahrenheit to 50 Fahrenheit is not a 25% increase in the absolute temperature. Those are quite small. Absolute temperature is measured from absolute zero. If you release the plunger, it will move away. Temperature and pressure will both drop eventually, assuming if you turn off the heat, if you keep the heat low, the temperature will stabilise at a higher temperature, the pressure will go back to atmospheric pressure, and the volume will have increased in proportion to the temperature. Turn off the heat, let it go back to ambient temperature, the plunger will go back in and to keep the pressure equal, and the volume will return to what it was. If you get hold of that plunger and shove it in, you will increase the temperature and pressure, and then the temperature will drop back to ambient and the pressure will drop with it, back to being inversely proportional to the volume. This is the ideal gas law, and it is a perfectly good approximation for jobs for which it is suitable. But if you take something down to the point where the nitrogen in the air starts to condense out as a liquid in the bottom of the cylinder, it's probably not going to keep being correct around that point. At very, very high pressures and very, very low temperatures, the sheer size of a molecule of your gas starts to really matter. At reasonable temperatures and pressures for a desktop apparatus, it's good enough. It's plenty good enough. If we go back to our program we had before that had the atmospheric density gradient, well, there was the standard atmosphere on Engineering Toolbox from which I got that also had a pressure gradient. We have just one pressure probe. Shouldn't there be a gradient inside that? Well, yes, there should. Put two probes in, you get two different pressures. So just make sure that showed up on your screens. Yes. But if this is an apparatus sitting on your desk, how big is it? 10 centimeters? How far apart are those probes? Is one of them 10 centimeters above the other? So that gradient, 0.999835, was it? Times to the power 1/10. 0.9999835 times as much pressure at that upper probe as at the lower. Well, how accurately can you read off the pressure on a pressure gauge? Really? How well calibrated is it? And how much do you care? If you're building a steam engine, somewhere where this might really matter, are you going to make all your pipes and joints and seals and valves so finely tuned that being wrong by 1% of 1% of 1/6 of the pressure is going to cause it to rupture? No. You're going to add like 20% or 25% safety margin when you're calculating stuff. Otherwise, the day someone is half an hour late polishing it, it rusts and weakens enough to explode in your face next time you fire it up. So that difference in pressure inside that apparatus, yes, it's there, but no one cares because no one's judging things that finely. It's an approximation that's good enough for the jobs for which it's used. What's this? What's all this? Well, that's another approximation, isn't it? Oh yeah. We have a hill. Partway down the hill is a reservoir. There are presumably some streams flowing down that hill, filling the reservoir. And an overflow and some fish ladder so we're not disrupting the ecosystem and some nice details like that. From the bottom of the dam, we have a pipe feeding down to a turbine house down here. The inlet at the bottom of the dam, which presumably drops the pressure down to one atmosphere, is 320 meters above the turbine. How much power can we generate? Well, you multiply the flow rate down that pipe in litres per second by the density of water, 0.997 kilograms per litre, by the gravitational field, 9.81 newtons per kilogram, by the height dropped, 320 meters, by the efficiency of your system. Because everything up to that point was how much gravitational potential energy is being lost from the water as it flows down. Some fraction of that becomes generated electricity. That fraction is efficiency. By multiplying all of those, you get the power output. And again, this is an approximation. For example, 0.997 kilograms per litre. Exactly, at all times, no matter the temperature. Yeah, that's not right. That's an average, that's a standard value. 9.81 newtons per kilogram. Well, that may be correct at this location. It may not, because as previously demonstrated, it varies all over the Earth, including with altitude. 320 meters may be right, although you probably haven't measured that to the nearest micron. So it's approximately 320 meters. You don't really know the efficiency to 50 decimal places. We can also represent the amount of available gravitational potential energy as the area, the coloured area on a graph. To the right, along the x-axis, in the direction to the right, we have weight in newtons per litre, which is gravity times density, as shown by that black arrow pointing down to where 9.81 newtons per kilogram times 0.997 kilograms per litre puts the right side of the rectangle for water, the head of water that's available. If on top of that you have less dense oil floating, the oil doesn't extend as far to the right, but you can show the height of the water and the height of the oil on top of it as height on the y-axis, and the area coloured in is the amount of GPE available. But of course, because it's that much higher up, it's subject to slightly less weight, fewer newtons per kilogram at higher altitude. So the top of that rectangle should actually be only 0.999899552 times as wide as the bottom of the rectangle, which wouldn't show up unless I drew this thing on a ludicrously big scale. Again, good enough approximation for the job. That fraction there. So if you make draw this thing so big that this rectangle is 10,000 pixels wide. At the bottom, the top of it should only be 9,999 pixels wide. No one's going to worry about that detail. Let's have another approximation. One to really annoy flat earthers. Oh yeah. In the best NASA accent. A linear aircraft model for a rigid aircraft of constant mass flying over a flat, non-rotating Earth is derived and defined. The derivation makes no assumptions of reference trajectory or vehicle symmetry. The linear system equations are derived and evaluated along a general trajectory and include both aircraft dynamics and observation variables. August the 1st, 1988. This is flight simulator software that came out 1 year after the Acorn Archimedes. This was at a time when a lot of computer system manufacturers were jumping from 8-bit to 16-bit. The BBM, the BBC Micro, Model B, was a thing of the past now. It still worked, you could still use it, but it was 8-bit, and all the new systems were 16-bit, and ARM came out with a 32-bit system, the Acorn Archimedes, and this thing was incredible. You know? You could have 256 colours. Never mind your 8 on the Beeb. 256. Didn't have to worry about modes. It had plenty of memory. You had full colour and full resolution in the mode. Wonderful machine. And it could run flight simulators. Like Interdictor 2, which quite definitely did fly over a flat, non-rotating landscape, and I mean a very flat landscape. The mountains in Interdictor 2 are just pyramids. The lake is a different coloured patch of flat surface. Very low polygon counts in Interdictor 2. Extremely low polygon counts. There will be this horrifying moment when that dot on the landscape in front of you suddenly turned into a full-size power station. Realize you're a lot closer than you thought you were. So in 1988 they had this simulation of a rigid aircraft. Your aircraft does not flex at all. Anyone who's ever tried landing at Kathmandu, or sat in the back while someone else tried landing at Kathmandu, may have noticed the aircraft wings do flex while the pilot's trying to get around in between the mountains and the thunderstorms to get down to that runway. Of constant mass. Anyone who knows anything about powered flight, and indeed powered boats and powered road vehicles and powered lawnmowers, is probably aware that quite a lot of them have to be refueled occasionally because they burn fuel and that the fuel has mass. So an aircraft of constant mass is an aircraft that's not burning fuel. So that's not entirely realistic, and neither is a flat non-rotating Earth. But this was 1988 and we had limited capability. The Ark was a huge leap forward. But it wasn't a... it wasn't going to... What do you call those things? Federation starships. Yeah, it wasn't one of those. Next flight sim, and I apologise for the colours in this one. I did a lousy job of making it comfortable to look at and readable. But there's the date, May 1995. So this was 7 years later, maybe slightly less. LarkSim is a set of ANSI-C routines that implement a full set of equations of motion for a rigid body aircraft, still rigid, in atmospheric and low Earth orbital flight, that's new, low Earth orbital, suitable for pilot-in-the-loop simulations, otherwise known as flight sims, on a workstation class computer. This is something you can run on a computer at home or in your cubicle in the office or in a classroom in a flight school rather than a computer the size of the Saturn V. All 6 rigid body degrees of freedom are modelled, which means your aircraft can move forwards, backwards, left, right, up and down, and it can tilt forwards, backwards, left, and right, and it can turn left and right. All 6 movements. The modules provided include calculations of the typical aircraft rigid body simulator, variables, Earth geodesy, so now it has Earth curve in, gravity, and atmosphere models, including that density gradient and pressure gradient. Interdictor 2 did not have an atmosphere model. Your engine worked fine until you went to 40,000 feet, and then suddenly it dropped to minimum thrust. Got below 40,000 feet, it worked fine. That was as much of an atmosphere model as they had. And supports several data recording options. Great in a flight school. Features/limitations of the current version include English units of measure, barleycorns, inches, hands, feet, yards, furlongs, rods, chains, miles, leagues, roods, acres, gills, grams, those silly things, yeah. A 1962 atmosphere model in cubic spline function lookup form. It's going to be something similar to what I had, but maybe not quite the same. Ranging from sea level to 75,000 feet, because they're not trying to simulate aircraft that go above 75,000 feet, because aircraft don't go above 75,000 feet. Much. Very few of them. A rotating oblate spheroidal Earth model. Oh yeah, that's an upgrade. With aircraft centre of gravity coordinates in both geocentric and geodetic axes. Geocentric meaning from the centre of the Earth, geodetic meaning relative to the orientation of the ground beneath you. A level surface beneath you. And the introduction says it used to be done on larger mini computers or mainframe computers. Those things that look like, the size of a whole Dragon capsule. Due to limited processing speed and data storage capabilities on smaller workstation and desktop computers, with the advent of more powerful reduced instruction set computer, RISC architecture, as in RISC-OS, the operating system on the Archimedes, but plus 7 years of development, the processing capability of a desktop computer exceeds that of a supercomputer of a decade ago. Which is why now we are able to include all of those things that weren't in the 1988 simulator in our 1995 simulator. Because we have computers that make the work of doing that trivial and can handle that work fast enough to run a flight sim, rather than sitting there for half an hour calculating each second of the aircraft's movement with an abacus, sliding beads back and forth on wires. Earth geodesy. Oh yes, rotating oblate spheroidal Earth model. Gravity. How to annoy a flat earther. Point out that actually the NASA flight sims do account for that once they have access to computers that can account for that fast enough to run the flight sim in real time. Our next decision of what to show, whether or not to show particular things. We have this family tree. This is part of a family tree of life. It is not fully detailed. You can divide living things between possibly viruses and plasmids, depending quite how you define life, prokaryotes, eukaryotes, and the archaea, and we're still not quite sure about them. Among eukaryotes, just things that have a nucleus. They have a cell membrane around the outside, may or may not have a cell wall. Plants do, animals don't, generally speaking. But they have a cell membrane, and within the cytoplasm they have membrane pockets containing mitochondria. They may also have membrane pockets containing chloroplasts. That's not a defining feature of eukaryotes. And they have a large membrane pocket with pores in it containing the nuclear DNA. That's the nucleus.
And generally speaking, that smooth endoplasmic reticulum and the rough endoplasmic reticulum with the ribosomes and yada yada on them, things that have nuclear DNA and mitochondria, basically. Eukaryotes. Within the eukaryotes is Animalia, the animals. You've got plants, and on another branch, you've got fungi and animals. Among the animals, you have chordata, you have the things with bilateral symmetry, and among them you have chordata, things that have spinal cords, and among them you have vertebrates, things that have spinal cords and vertebra. And among them you have mammals, things that produce milk in mammary glands and secrete it to feed their young. And then within mammals you have orders and you have families. And within families you have genuses, and within genuses you have species. And you can also have these like superorders and suborders. So we have these terms: a domain of eukaryotes, a kingdom of animals, a phylum of chordates, a class of mammals, an order like Carnivora. It's there at the upper right. And then now the family Canidae. And within that you got the genus like Vulpes, the fox, Vulpes vulpes, the red fox, or Lupus, a wolf. This is an approximation because these are arbitrary labels that we apply. And we can illustrate that right in the middle. I mean, there is a fairly obvious division here. Down the right there is dark grey space. Just to the left of that, the right most interesting thing, you've got Placentalia, which is all of these guys, and Marsupialia down here, and then at the very bottom, Monotremata. And that is a big difference between things that gestate babies for a very long time to a very high level of development, and things that gestate babies for a much shorter length of time and then carry them in a pouch while they continue developing. And right down at the bottom you've got things that lay eggs. But they're all mammals. So we applied this label, mammal, as a defining feature of this class of animal. And then we divide them again, and it's not a class or an order, it's something in between. Marsupialia and Placentalia and Monotremata, they're somewhere between class and order. Then you've got all the orders within all of these, like Cetartiodactyla, Perissodactyla, Carnivora, Chiroptera, Ulipotifla, Dermoptera, primates. Otherwise they're all obviously Greek or Latin or something like that, and primates in English. Rodentia, or rodents. Lagomorpha, the lagomorphs, rabbits and hares. Scandentia. Scandentia are their own thing. This little purple line down here, they're just their own thing. A single family, Tupaiidae. I think it's only 2 species. They're adorable, by the way. They are absolutely adorable. And then suddenly there's a Xenarthra. Everything from Dermoptera to Scandentia is in Euarchontoglires, the true top ontogles. Then Xenarthra is its own thing. It's not in there. And it isn't subdivided either, like Euarchontoglires are. And then you've got Afrotheria, the African animals, which are subdivided. Proboscideae, things with long noses. And we have 2 genuses of Proboscideae, Elephantidae, the elephants, and Elephantidae, the elephants. So we do bother to distinguish between them as genuses, but we don't bother giving them different names. Hyracoidae, Procavidae, and again we have 2 genuses of Procavidae, but they're both Procavidae. And then Sirenia, the sirens, the beautiful women who lie on the rocks and sing amazing, enchanting songs that lure sailors to crash their ships into the rocks trying to get to them. Which includes Trichechidae and Dugongidae, the dugongs. Have you seen a dugong? Now you may think dugongs are beautiful, you may think dugongs are very graceful, you may think dugongs are adorable. But mistaking them for beautiful women, you would have to be at sea a long time. Tubuli dentata.
things with tubular teeth. Orioteropodidae, whatever that means. And then you've got the Afrosoricida. Sorex being a shrew, that's African shrews, only they're not shrews because they're Afrotheria and shrews aren't. Tenrechidae, which is more like a hedgehog. And you'll notice there that Tenrechidae and Chrysochloridae are all in the same colour because they're all Afrosoricida. But the Chrysochloridae branch off from a branch that also has another branch which becomes both the branches of Macroscelididae, the things with very big scelids. Right. So whatever that was behind there, whatever this thing labelled 64100 is, let me zoom in on it. There, that 64100 was a common ancestor of all macroscelids and some Chrysochloridae, but it wasn't the common ancestor of Tenrechidae. To find a common ancestor of Chrysochloridae and Tenrechidae, you have to go back to this 78100, where you find a common ancestor of all the Macroscelididae, all the Chrysochloridae, all the Tenrechidae, and all the Oryctopodidae. So Macroscelidae and Afrosoricida and Tubulidentata. So this Afrosoricida isn't actually descendants of a single ancestor. It's some descendants of the one way back there, but not all of them. It's a little strange. Because it's an arbitrary name applied by humans, it's not an actual magical glowing thing. It's not like distinguishing between elves and high elves. It's a label we applied. It's more like distinguishing between Tooks and Bagginses. So what even is this family tree? This is a mitochondrial DNA family tree. As mentioned, this is mammals, which are within vertebrae, which are within... No, mammals are within tetrapods, which are within vertebrae, which are within chordates, which are within bilateral animals, which are within animals. Yeah. So we are well inside the eukaryotes, things that have nuclei and mitochondria. And when eukaryotes reproduce, in most cases, I think fungi might do it differently, but generally speaking, you get the nucleus from one, nucleus out of a specialist cell called a gamete from one parent, inserted into a specialist cell called a gamete from the other parent, to form a fertilized ovum, which becomes a zygote. Now, I don't know whether you call it a zygote in a plant, but in animals, certainly in mammals, you have one parent has organs with particular tissues in them in which cells duplicate their entire nuclear DNA. So they have, 12 or 13 or 22 or 23 or 34 chromosome pairs. 2 copies of each chromosome. They duplicate every chromosome they have, whether that's 24 or 26 or 28 or 78 chromosomes. 1 copy of each chromosome gets pulled to each end of the cell, and the cell, each end of the nucleus divides to form 2 nuclei, and 1 nucleus goes to each end of the cell. The cell divides down the middle. The individual mitochondria also duplicate their single chromosomes that each of them has, and then they divide in 2 to form 2 mitochondria, and then the pocket around them divides in 2 to give them 1 pocket each. The cell divides in 2, and some mitochondria get caught on each side. So each of those 2 cells that is produced has a full copy of the nucleus with a full set of nuclear DNA from the parent cell, and some copies of the mitochondria from the parent cell in all tissue development throughout all mammal bodies. Except in these specialist organs in which some cells will divide like that, but then they divide again without duplicating the nuclear DNA. And instead of sending 1 copy of each chromosome to each end of the cell before it divides, they send 1 chromosome of each chromosome pair to each end of the cell before it divides. Then you get these 2 little product daughter cells that each have just 12 or 13 or 14 or 22 or 35 chromosomes, not chromosome pairs. And one of these is a large, squishy ovum. The other one is much smaller and has a tail and can swim, is a spermatozoan. Spermatozoan hits ovum, docks to it. The ovum reacts to this by changing in a way that prevents other spermatozoa from fusing with it, so it only gets the one. Spermatozoan reacts to this contact by injecting its nucleus, but only the nucleus. The mitochondria don't get transferred. I don't know why they actually couldn't, but as far as I'm aware, it never happens. It's just the nucleus, and the nucleus goes through the fusion point and gets combined with the ovum's nucleus to create a fertilized ovum that now has one of each chromosome pair from the parent that produced the ovum, one of each chromosome pair from the parent that produced the spermatozoan, which creates a full set of chromosome pairs, just with a random mixture from both parents. This random mixture is great as a way to drive evolution, because instead of having the chromosome from your parent, which is what mitochondria produce, a mitochondrion has a chromosome and duplicates it, and each of the two mitochondria that result from it splitting down the middle has that chromosome. With 23, in the case of humans, chromosome pairs, you have 4 possible combinations of each chromosome pair, so you have 4 to the power 23, which is a very big number, possible combinations of chromosomes from the two parents. Assuming the parents aren't closely enough related to have identical chromosomes, you have that huge number of possible offspring. And as long as you have a whole large population producing lots of offspring, the ideal combinations of chromosomes are likely to be produced somewhere, as well as nearly but not quite ideal, and good but bordering on mediocre, and actually mediocre, and definitely suboptimal, and really bad combinations. And evolution, well, natural selection, gets to pick them. And of course, what's ideal may vary from place to place. If we take the Elder Scrolls as an example, imagine we have some kind of small cat species, or maybe a badger. Yeah, smaller than a European badger, kind of a fennec fox-sized badger-like animal. If this thing is living in Daggerfall, there are forests everywhere, it rains a lot, there's plenty of food around, if you don't mind getting soaked on a regular basis. If it's living in Sentinel, it rains a whole lot less and it's all sand everywhere. Food is now insects and snakes and things in the sand, and you're going to have to dig it out of sand rather than out of wet mud. You're not going to get soaked. You're not going to be able to dig a lovely home in the firm clay, because there isn't any, because you're living on sand. And you're going to have to be water efficient. Oh, our little, fennec fox-sized badger is going to have to be water efficient. Head up north into Redguard territory, and the mountains, very high altitude, very thin air. Mainly certain adaptations that may be more expensive in terms of how many amino acids, how much energy it takes to produce an adult animal, but make the animal better at coping with thinner air, may be worthwhile there, but not worthwhile on the coasts of Daggerfall and Sentinel. So the same animal may be able to live and eat and reproduce in all 3 places, but the offspring with this randomized combination of chromosomes that do best in each place will be slightly different. Carry on north into Skyrim, and suddenly your biggest problem is that it's cold, and suddenly that one offspring that has hollow hairs that are so much better at keeping you warm than single hairs is going to be the one that does the best. And the odds are that a few generations later, a large proportion of the population of these little fennec fox-eyed badgers in Skyrim will be descendants of that one and will have inherited that hollow hair effect. Go the opposite way, you're in Elsewhere, the swamp, and apart from having to avoid those Khajiit, you really need to be able to cope with being soaking wet all the time, or maybe you need to be able to climb trees to dry out. Different adaptations become ideal. This is not to say that the basic standard Imperial Province fennec fox-eyed badger couldn't survive in Elsewhere, but is going to be outcompeted by mutated badgers, or changed badgers, badgers with different combinations of chromosomes that happen to be better suited to that environment. So over time, in all these different places, the ones out to the east in Morrowind, goodness knows what they're going to do because there's the volcanic ash and plague blowing in the wind on a daily basis. Over time, your fennec fox-eyed badger-like animals are going to change, generation by generation, with tiny changes. And how they change is natural selection and acting on this randomized mixture of chromosomes from pretty much the entire population, generation by generation. And they will develop, a sandy colour that allows them to be better camouflaged in Sentinel, and maybe larger ears that can radiate heat away, well, not radiate, convect heat away, shed heat to the environment better in Sentinel, and forest camouflage for Daggerfall. Maybe the ability to see in the dark better, to avoid certain predators. Because those little dragonling things, dragonette things, they're dangerous, they're mean, I don't like them. Maybe in Sentinel, obviously, in Skyrim, obviously white coloration to blend in with the fur, pale greyish blue, maybe black and white, or black and pale grey, so they blend in with snow and rock, because they won't want to be all the way up there in the glaciers, they'll want to be where there is at least something to eat, rather than the browns and greys of Daggerfall and the sort of tawny colours of Sentinel. In Elsewhere, they'll develop tree climbing abilities. In Morrowind, they'll develop really long moustaches to filter the volcanic ash out of the air as they breathe. Or longer noses, so they have longer distance for the nasal hairs to filter the air they inhale, or something like that. Really good eyelashes to protect their eyes from it, because volcanic ash is nasty. Over time, this mixing of nuclear DNA is going to drive evolution. That's great. In terms of tracking which animal is the offspring of which animal, then it gets a little tricky. Because if you went and took one of those forest-dwelling fennec fox-eyed badger-like animals from Daggerfall and a jungle-dwelling fennec fox-eyed tree-climbing badger-like animal from Elsewhere, and you adopted them both, they might have babies, which would be a mixture of both. And they wouldn't be Daggerfall badgers or Elsewhere badgers, they would just be Elder Scrolls badgers, some weird hybrid. And we like to classify things into species. This one stops here at families, like Herpestidae and Felidae and Canidae. Doesn't even go as far as genus. Canidae is dog-like things. It includes wolves, jackals, coyotes, foxes, different kinds of foxes, Arctic foxes, fennec foxes, red foxes, grey foxes, the African wolves, the red South Carolina wolf that the people of South Carolina keep trying to drive to extinction, Canadian timber wolves, European wolves. It includes all those wolf-like things in South America and the fox-like things in South America and the coyote-like things in South America that all descended from the same coyote-like animal that crossed from North America and just diversified because every combination was, for a while, the best dog in the area. And we like to define them. We like to say, that right there is an Ethiopian wolf, and that is a European wolf, and they are different species. Well, if they can have babies? Well, if they can have babies, they're the same species. What if the Ethiopian wolf and the European wolf can have babies together, and a European wolf and a red wolf can have babies together, and a red wolf and a coyote can have babies together? beneath the Ethiopian wolf and the coyote can't. So those two are the same species, those two are the same species, those two are the same species, but those two aren't the same species. Oops. Same for our hypothetical little badgers in the Elder Scrolls. What if a male daggerfall badger and a female wayrest badger are fertile, but a female daggerfall badger and a male wayrest badger aren't? Or what if both combinations are fertile, but it's only the female offspring of either pair that's fertile with either of them, with another male from either province? Are they the same species or not? So again, species is an arbitrary thing that we have applied to make it easy to describe things, rather than being an absolutely precise definition of something. Meanwhile, you've got those mitochondria. The mitochondria in the spermatozoon get discarded along with the rest of it once it has done its job of delivering its nucleus. The mitochondria in the ovum, they reproduce. When that ovum duplicates that now complete nucleus and its complete nuclear DNA complement, you get two nuclei and then divides down the middle. Some of the mitochondria inherited from the parent that the parent whose cell divided to produce two cells, one of which divided to produce two ova, one of which was the one that got fertilized, are going to be in both of those daughter cells. And then those divide, you get a 4-cell zygote. Those divide, you get an 8-cell zygote. Those divide, you get a 16-cell zygote. At some point, in placentalia at least, this implants in the uterine lining, forms a placenta, draws nutrients through that, continues to develop, it becomes a recognizable embryo, develops into a fetus, then eventually gets born and becomes a living, breathing baby. In some fraction of cases. A lot of them don't ever implant. A lot of them implant but don't grow any farther. Some of them will grow quite a long way and not make it. Some of them will be born but never breathe. And if you're a Bible follower, by the way, the biblical definition of the start of life is actually the second time they draw breath after being born. So living, breathing baby is actually the biblical definition. So no whining. But that offspring, that produced tadpole, fish fry, baby octopus, kitten, that's the baby rabbit, by the way, or wolf cub or bear cub or whatever it is going to get all its mitochondria from, for lack of a better term, its mother, right? The one that produced the ovum. The one who had ovaries and produced an ovum, which got fertilized and became a zygote, which became an embryo, which became a fetus, which became that baby, provided all the mitochondria in that baby. So if you extract the mitochondria from an animal and compare the DNA sequence in that mitochondrion to the DNA sequence of a mitochondrion from another animal, you can see how different they are. And there hasn't been any mixing in the inheritance of that DNA. The DNA in that mitochondrion is simply passed down from mother to daughter all the way down to whatever that animal is from which you extracted it. So you're looking at DNA that was inherited from that animal's mother, all the way back through time. And we happen to know that mitochondrial DNA does occasionally mutate. One thing for which royal families are actually useful, we have these family trees that go back hundreds of years, and you can take mitochondrial DNA from very distant relatives, but with known female line descent, and see how different they are. And you can do this with pedigree dogs and purebred horses and all these animals that people track very carefully, with herds of cattle, and see how fast mitochondrial DNA changes. And you find it's the same across all these species. For whatever worth the word species actually has. All these different animals have mitochondrial DNA that changes at the same rate. That means the more difference there is between the mitochondrial DNA sequences, the longer it's been since those sequences were identical, the longer it has been since the one animal's mother, and the different animals' mother were actually the same animal. And that's how you get this family tree. So, way over on the left, we have that vertical line a very long time ago. And one branch of it, across the bottom, Ornitho. Something to do with birds? Rhynchidae. Noses. Possibly duck-billed. And I can't read the other one because it got cut off. The other branch from that common ancestor way over there on the left comes forwards to this vertical line that's still nearly the left of the screen. Its lower branch has all these branches. Didelphidae, two-podded. Caenolestidae, whatever that means. Thylacinidae. Thylacines, we know what thylacines are, don't we? They're Tasmanian tigers. Dasyuridae. Something that's uri is very dassy. Myrmecobiidae. I think Myrmec is termites. Myrmecobiidae. I don't know what obi is though. Something that obi is termites. Microbiotheridae. Tiny biology animals. It's a cute name. Nolodrictidae, Thylacomidae, Peramelidae, Phasco... Wombatidae, there we go. Well, Vombatidae if you read it as a V. Wombatidae if you read it in classic Latin. That's wombats. Phalangeridae, things that have phalanges. Macropodidae, things with big feet. Polaroidae. Polaroids, really? Animals that are Polaroid. Acrobatidae, very acrobatic animals. Tarsipedidae, things with feet like a tarsier. Petoridae and Pseudocheridae, fake Caries. Those are all across here, and you can see they are divided. Didelphimorphia, Porsituberculata, Dasyuromorphia. Dasyuromorphia, things that are like Dasyuridae. Dasyuro-shaped things. Microbiotheria again, same word. And Diprotodontia. Di, two. Proto, it's not quite there yet. Dont, teeth. Animals that have two things that are not yet quite teeth. Those are all marsupials. So those are those strange Australian things. I'll zoom out just a little here. The upper branch of that, not the last common ancestor of all mammals, the last common ancestor of all marsupials and placental mammals, is of course the last common ancestor of all placental mammals on the left side of the screen now. And that has these four descendants. Afrotheria, where you've got the elephants, the hyraxes, the dugongs and Trichichidae. And that weird group where the black colour of we don't have a name for this extends quite a long way forwards and has multiple colours coming off it, including one that's on two different branches. All of which are Afrotheria. Then you've got Xenarthra. Xen, strange or different or foreign. Alien. Arth, as in arthritis. Joints. Articulation of a articulated lorry. Strangely jointed animals. We have Megalonychidae, things with big niches. Bradypodidae and Dasypodidae are two-toed and three-toed, or possibly three-toed and two-toed, I forget which round they are, sloths. And in between them, so the first branch off here, the branch longest to go, was the Dasypodidae, which is one kind of sloths. Then you have another branch, which is Myrmecophagidae. Myrmeco, termite. Phage, eater. P-H-A-G. When you see bacteriophage, that is a virus that eats bacteria. Myrmecophage is an animal that eats termites. So anteaters. Then Bradypodidae, more sloths. Branch off, and Megalonychidae, whatever those are. I should know, but I have forgotten. It's very annoying. Sloths, and I'll tell you in a minute anyway. The next branch here includes this little, and it's another one where the colours change at different places. Like you have one offspring that is the last common ancestor of Tupaidae, which are the only order within the family Scandentia. I think I've got that the right way around. Sorry, the only family within the order Scandentia. Then another descendant was the last common ancestor, well, descendant, not direct offspring, descendant with the length of, excuse me while I zoom in, the length of that little line right there is time that elapsed between this common ancestor of all these things and this common ancestor of the lagomorphs, rabbits and hares, and rodentia, where we have cavies, Thrionomidae, things that non-3, Muridae, mice and rats, Cricketidae, Spalachidae, Dipodidae, two-footed things. Those are also kind of adorable. They don't look real, but spring mouse in German. Sciuridae, squirrel, and Gliridae. Right? So all your rodents and your lagomorphs share a common ancestor more recently than the common ancestor of Scandentia, Lagomorpha, Rodentia, primates, and Dermoptera. This third branch of our branch of Placentalia is two colours. One of them straight away, Chenocephalidae, things with hollow heads? Something about the head. In Dermoptera. Dermo, as in hypodermic needle, epidermis, dermatologist, and so on. That's skin, and optera are wings, as in Hymenoptera and Hemioptera, and so on. So, Dermoptera are skin wings. Chenocephalidae are the flying lemurs. Those get their own colour and their own name, despite being no more distantly related than Tarsiidae and Helobatidae, for example, which are all in primates. But they don't have wings, so they're not counted as Dermoptera. Within primates, that's the pink group here, you've got 3 descendants of the last common ancestor. One of them, Tarsiidae, right away, just branched off early. Another one got this little arm here, to a common ancestor of Lorisidae, the lorises, and the common ancestor of Dobentonidae, and the common ancestor of Lemuridae and Indriidae, which are both lemurs. And the other one here has this very long arm across there. I don't know whether the cursor appears. So this, centre of the screen, very long arm, to that common ancestor of that common ancestor and that common ancestor, this one being Aotidae and Cebidae, this one being the common ancestor of Cercopithecidae, which is squirrel monkeys, and that thing, whatever it was, which was the common ancestor of Helobatidae and Hominidae. Hominidae is us, great apes, humans, good time to figure out what they're called, humans, chimpanzees, bonobos, there's the word, and gorillas, maybe orangutans. Helobatidae are therefore our closest relatives that are not hominids. That was a bit of a long way to zoom out. Which are gibbons, making this a good time to shout out to Gutsick Gibbon, who is great. You should go and check out Gutsick Gibbon. She's way more interesting than I am. That accounts for this group, Euarchontogleraes, the true top ontogles. And then there is this fourth branch from the very tall black line there, which branches out quite a lot. Its first branch is this pale blue. So the part of that branch that is least closely related to all of the others, or the part of that branch to which the others are not as closely related as they are to each other, is Eulipotifla, which includes Talpidae and Soricidae, the moles and the shrews. And that is in fact the branch. There is a common ancestor there between the common ancestor of all moles and the common ancestor of all shrews. So when you're way down here in Afrotheria and you see, in Marsupialia and you see Pseudoceridae, was it Pseudoceridae? No, so there was a Soricida. There was a Sorix somewhere down here, damn it. I know I saw a Sorix. I thought I saw a Sorix. I just sworn I saw a Sorix down here. Maybe it's in Afrotheria. Macrocelididae? No, that's not Sorix. Huh, never mind. I was going to say, when you see Megasaurix or Sauricomorpha or something, that's big shrew or shrew-shaped, but not an actual shrew. Only you don't see that down there, so my bad. Next branch off, Chiroptera, the bats. All of these things, Rhinolophidae, nose leaf, pteropod, webbed feet, Mystacinidae, strange something, Philostomidae, maybe that's the leaf, phylum, and Vespertilionidae. Is that the wormtails or mousetail, or is that the evening bats? Right, those are all bats. And notice, bats are on that branch, flying lemurs are on this branch. So between Dimoptera and Eulipatifla, there is this, you can follow white between Euarchontogleraes and Larasiotheria, all the way back between them, way back to that vertical line there, which is about 90 million years ago. They may have webbed hands and glide between branches, but they ain't bats. And the bats are up here in Larasiotheria, and the mice are down here in Rodentia, in Euarchontogleraes. So bats are not flying mice. Sorry, Germany, but Fledermaus is an inaccurate description. Then you have this branch which it splits two ways, really. In fact, they've changed how they drew this. They've been putting the oldest branch at the bottom, now the older branch is at the top. The oldest branch is Cetartiodactyla, this dark indigo at the top, which branches into Camelidae, the camels, Suidae and Tiosuidae, the pigs and the Tias pigs, Bovidae, Cervidae and Giraffidae, bovines, cattle, cows, buffalo, bison, kind of thing, and deer and giraffes. So next time you look at a deer, compare it to a cow, and then compare both of them to a giraffe. You'll see certain similarities. And the other branch it has a branch for Hippopotamidae, which is now being the oldest one coming off the bottom again, and a branch that is right up here at the top centre, this one up here, still at the top centre, which is the last common ancestor of Escherichidae, Balanopteridae, Neobalenidae, Balenidae, Monodontidae, Phocoenidae, Delphinidae, Inidae, Ziphiidae, Physeteridae and Platanistidae, which are whales, dolphins, porpoises, river dolphins, and whales. Also, Monodontidae, single tooth. A single very long tooth, famously more useful than a knife when fighting on London Bridge. That's your narwhals right there. So based on this chart, we can say that all the dolphins and whales are more closely related to each other, and porpoises and the narwhal, are more closely related to each other than to anything else. And of the things outside dolphins and whales, the thing most closely related to them that isn't one of them is a hippo. Hippopotamidae, the horse of the river. Might not be an accurate description. It might not be an accurate description because horses are equidae, which are down there in Perissodactyla, which is a branch off the other branch, the one I haven't mentioned yet. It's in the green and purple branch. Green being Perissodactyla, Equidae is horses, Tapiridae is tapirs, which are... Imagine a cross between a shrew, a pig and a horse, but kind of cute. And they are actually horse-like. You can tell by comparing the mitochondria that they're closely related. You can also tell by comparing the feet, the dentition. Monkey Scientist and Aaron Ra, recent live stream, and Gutsy Gibbon will both tell you, compare the teeth. Look at the teeth. The teeth can tell you a lot. You know? Same number of the same kinds of teeth with the same number of crowns on each molar and so on, or the same gap with the same kink in the gap. That's a Clint's Reptiles recent video thing. Is a pretty strong hint of being related, right? But it also tells you a lot about what this animal ate. Rhinocerotidae, nose, and rhino is nose, as in common cold, rhinovirus, and keratin is what your fingernails and hair are made out of. This is something that has a single very big hair, or a few very big hairs, on its nose. It's a rhinoceros. A rhinoceros is actually in there with the horses. Perissodactyla probably refers to them having a single enormous fingernail on each foot. Probably. So there was an old classification, pachyderm, thick-skinned animal, but that included hippos, rhinos and elephants. And more recent study has shown this to be a really nonsense classification, so it's been dropped, because science actually adapts when it gets new information. The other branch of our green and purple is the purple, the carnivora, flesh eater. Carn as in carnival and chili con carne, meat, vora, to eat. The eaters of flesh. At the top of that, we have Otariidae, the eared seals, are close related to Odobenidae, the walruses. And Otariidae and Odobenidae are close related to Phokidae, the earless or true seals. In the next group, Mustelidae, which is your badgers, all over Daggerfall and Skyrim and elsewhere, and Morrowind, your badger-like animals. It's also stoats, weasels, polecats, ferrets and otters. So, give them tens of thousands, millions of years, and those badgers might eventually, they don't turn into, that population of badgers turns into, because generation by generation, parts of each population will become more and more like stoats, weasels, otters, and so on, and mink. Maybe in elsewhere where it's swampy, the more otter-like the offspring are, the better they do. And generation by generation, tiny changes that make them more and more otter-like will slowly make the whole population become more and more otter-like. And over a few million years, you get otters. Whereas in Skyrim, where snow camouflage is really useful, you'll get that stoat thing where they are brown and cream underneath, brown on the back with a black tip on the tail in summer, and white all over apart from a black tip on the tail in winter. And out in Daggerfall, you would get badgers, just bigger than fennec foxes. Mustelidae are closely related to Prochionidae, which are raccoons and smart little guys. And Mustelidae and Prochionidae are close related to Mephitidae, skunks. And again, close inspection will reveal certain similarities, but you probably don't want to closely inspect a skunk without first doing a really good job of earning that skunk's trust. And then the whole group, I'm not going to give it a technical term because there isn't one. It's a superorder? No, because you've got the family Otariidae in a superfamily, it's not named on this diagram, within the order Carnivora. But the group of Otariidae, Odobenidae and Phokidae, and the group of Mustelidae, Prochionidae and Mephitidae, and three more families, Ursidae, Iluridae and Canidae, all share a common ancestor, which shares a common ancestor with the common ancestor of Felidae and Herpestidae. But we group them all together as Carnivora. Ursidae is bears. Brown bear, black bear, polar bear, Kodiak bear these days, spectacled bear and giant panda. Iluridae is red pandas. They are their very own thing. Canidae, as mentioned, wolves, foxes, domestic dogs, jackals, coyotes, African hunting dogs, Arctic foxes, all those dog-type things. Felidae, feline, cats, lions, tigers, and pumas, oh my. And jaguars, and leopards, and caracals, and servals, and ocelots, and sandcats, all in Felidae. Herpestidae is mongooses. Mongooses are more closely related to cats than they are to polecats, which are Mustelidae, even though the resemblance is more Mustelidae. If you take a close look at certain details, you'll find that actually mongooses do more closely resemble cats. They're just, in overall shape, they're kind of a little more stoat-like, and also kind of lemur-like. So this is obviously a 2D graph here. We have this chart laying things out. What are the axes? They're not labelled. Now, left to right is time, which may have already become obvious. Left to right is, the farther left of that list of orders down the right side, something is, a vertical line is drawn, the longer ago that last common ancestor existed. And the numbers actually give you a pretty good idea of how long ago it was. Those numbers are very useful for that. For example, the last common ancestor of primates and of Hominidae and Felidae, therefore of primates and carnivora, and of Euarchontoglerace and Laurasiatheria, was about 90 million years ago, which is before some known dinosaur species even came into existence, as far as we're aware. The oldest known fossils of some dinosaur species aren't as old as the calculated time since that last common ancestor. Okay, so left to right is time. What's top to bottom? Top to bottom is a list. There is no vertical scale on this. That's important. Just to add some labels. Cows, deer and pigs as mentioned. Horses as mentioned. Bats, moles, shrews as mentioned. Hominidae, that's us as mentioned. Squirrel. And as mentioned, Tupaiidae are adorable. And down here, it's the Macroscelididae, our elephant shrews. I knew there was some kind of not a shrew but called a shrew down there. Macroscelididae, it's not Macrosauridae. So I was half right. Okay. Just to I better do that so you can see, to make sure you can see the labels. Then jump to the next image just to provide the citation for Tupaiidae being adorable. Because I know you're going to want a citation for that, aren't you? There you go. That's Scandentia. That little guy there. That adorable little fluffy, kind of squirrel-like, kind of shrew-like. Not actually a squirrel or a shrew. Not a stoat, not a badger, not a wolf, not a monkey. Fluffy little adorable dude. And I can't help thinking, looking at that look on that animal's face and that front paw that's just visible below the chin there, that little animal has just realised that the thing on which it is sitting is awfully similar in shape, structure, firmness and temperature to its own front paws, but absolutely huge, and has had its mind blown by the implications. Next image. Same thing. As mentioned, those vertical lines don't represent anything, they're just an easy way to draw it. Here they are horizontal lines, they still don't represent anything, they're just an easy way to draw it. And here vertical doesn't represent anything either. This is simply the shape of the lines, it's just showing where the branches occur, not how far apart they are. It's just the sequence of branches. This is a list in English, and if we start way down in the bottom right with the asterisk, where there just wasn't room with that text size to actually list the bears, the seals, the red pandas, wolves, horses, pigs, dolphins, cats, hoppos, boing, 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 rhinos, deer, etc. So I put in an asterisk, which is up there. Over on the left, we have all those things in Marsupialia. The opossums, the shrew opossums, which are these adorable, fluffy little... Well, they're not shrews, and they're not... Well, shrew. It's called a shrew. It's another thing that's called a shrew without being a shrew. But they're these fluffy little, long-nosed, four-footed, adorable little, not shrew, not ferret, not stoat, not dog, adorable little fluffy guys. Tasmanian tigers, quoll, antechinus, dunnuts. Those dunnuts are also adorable. Dunnuts are the things in that meme of not every animal in Australia will kill you. He wants to, he just can't. Phascogale, Mulgara, Planigale, Tasmanian devils, pouched mice. Imagine crossing a kangaroo with a mouse somehow. Pouched mice. Numbats, which are maybe not quite as adorable as dunnuts. Maybe more. It's a matter of personal taste. But they are small and fluffy and not shrews and not stoats. Monito del Monte, marsupial moles, bilbies, bandicoots. Yes, bandicoots are a real animal. Koalas, don't touch. Cuscuses, brush-tailed possums, kangaroos, wallabies, quokkas, which are ridiculously cheerful. Bettongs, potoroos, feathertail gliders, which are adorable and fluffy. Feathertail possums, honey possums, which are fluffy and adorable. Triox, striped possums, gliders, and ringtail possums, which are tiny, fluffy and adorable. On the branch of marsupials, on the other branch of placental things, you've got the branch of all the primates over here, the tarsiers, lorises, potos, and guantibos, aye-ayes, lemurs, night monkeys, squirrel monkeys, baboons, macaques, great apes, gibbons, and flying lemurs. They are that branch of skin-wing things and primates. And the branch down there, down the middle, that is rabbits and hares on one side and dormice, squirrels, dormice, just these adorable, fluffy little, not shrews. Blind mole rats, hamsters, voles. You might think voles are adorable, you might not. Lemmings, mice, rats, gerbils, cane rats, which are alarmingly large, fluffy, not shrew things. Guinea pigs and capybaras, which are absolutely huge, but not alarming, because capybaras are chill. And then the branch is rabbits and hares. And then there's that fourth branch, the tree shrews, the adorable guy sitting in someone's hand in that photograph. And of course, Placentalia also has the armadillos, sloths, and anteaters. Thank you, armadillo. That was the other thing, the one I couldn't remember. It's an armadillo. Told you I'd get around to telling you. Right. And then the other branch, the Afrotheria, with its branches of elephants, hyraxes, dugongs, aardvarks, tenrecs, golden moles, and elephant shrews. Golden moles aren't moles. They're over there in Afrotheria. Moles are way over in the other branch, the asterisk branch down here. And elephant shrews aren't shrews, because shrews are in the asterisk branch, and elephant shrews are Afrotheria. But they are small and fluffy and kind of adorable, unless they freak you out, in which case they're small and fluffy and freaky. So, there is this lie that certain violent, abusive, convicted tax fraud felons who've set up trailers by the road in a desert somewhere and called them universities so they can award themselves honorary PhDs so they can pretend to be entitled to being called doctor, and who break their wives' hips trying to make them scream while secretly recording them so they can pretend their wives are insane so that they can steal their wives' houses and life savings. Like to tell. There are a lot of lies that they like to tell to fleece suckers out of their money. One of the things they like to say is that you don't see pine trees giving birth to elephants, or you don't see ducks giving birth to wolves, or something like that. Now that's technically true, but they're still being dishonest because they're trying to use that as an argument against evolution as taught, and evolution doesn't teach that that happens. Over here on the right, we have adorable, fluffy little golden moles and elephant shrews. And dugongs, if you happen to find dugongs, absolutely adorable. Armadillos, sloth, and anteater are not so much small and fluffy and adorable. Maybe adorable, maybe fluffy, but not really small. But you've got the tree shrews, which are small, fluffy, adorable, and kind of shrew-like, kind of squirrel-like. You've got rabbits, which are small and fluffy and adorable, and very destructive. Dormice, which are small, fluffy, and adorable, and not actually shrews or squirrels, but kind of similar to them both. Lemmings, which are small and fluffy and adorable, and not shrews or squirrels, but in some ways similar to them both. Gerbils, which are, at least in some people's opinions, small, fluffy, and adorable. You've got all these weird things with hands and opposable thumbs and big brains, and among the great apes, flattened fingernails rather than claws, which are strange. On the asterisk branch, you've got seals. Take a look at a harbour seal cub, by the way. And take a look at a Great Pyrenean shepherd dog pup. Note the similarities. Oh yeah, the Germans may have been wrong about Fledermaus, but they got Seehunde right. Seals, they're sea dogs. Also, those little cubs, they're adorable. And here you have the actual shrews, which are, pretty much by definition, shrew-like. They're also small and furry. And then in the marsupial branch, you have these small, adorable, fluffy, shrew-like shrew opossums, and honey possums, and ringtail possums, and numbats, and dunnuts. So you have small, fluffy, adorable, shrew-like things in every branch. That kind of suggests that somewhere back in history, They all descended from small fluffy shrew-like things. That badger-like animal that spreads out across the world of the Elder Scrolls descended from a small fluffy shrew-like thing that survived the KT mass extinction by being small and fluffy and shrew-like rather than by being a huge great T-Rex, which did not survive the KT extinction for many reasons. And if you could find, an elephant, a hyrax, a dugong, or one elephant and one elephant, because of course there are Elephantidae and Elephantidae, and one dugong, one aardvark, one tenrec, one golden mole, one elephant shrew, one armadillo, one sloth, one anteater, one tree shrew, and so on, all the way across the list, all the way down the previous one. Find one representative of each genus within each of the families listed, and line up their mothers and their mothers' mothers, their mothers' mothers' mothers, back 10 generations. You would have no trouble matching the female line ancestor 10 generations ago to the modern animal at all. I hope, for your sake. If you could keep doing that all the way back to the last common ancestor of all placental mammals and the last common ancestor of all marsupial mammals, and the last common ancestor of both of those, you would have immense difficulty saying which was which over the first 10 generations from the common ancestor. Because the last common ancestor was one last female line common ancestor, was one member of a huge population, a huge and diverse population of animals. And some of her daughters had daughters that had daughters that had daughters that had daughters that became, that had daughters that ... had daughters that are elephants now. That doesn't mean one of her daughters was an elephant and another one was a dugong and another one was a wolf. It means that her daughters weren't identical to each other. 10 generations down the line, the ancestor of an elephant and the ancestor of a wolf could still have both had the children of a single male of that species. Because they were still, at least in that sense, the same species. They were compatible with much of the population in the area. They were just very slightly different. So 100 generations, you might, great care, be able to guess correctly which one was going to turn out to be the ancestor of which modern animal. But I really doubt it over 100 generations of shrews. We're talking 90 million years back, just to the last common ancestor of seals and humans. 90 million years is a lot of generations. At no point, anywhere on this diagram, does it say that a shrew gave birth to a wolf, or that a duck gave birth to an elephant, or that a pine tree gave birth to a hyena. Those last common ancestors were little shrew-like things. And that common ancestor there wasn't a pine tree, Kent. Bit more biology. This is a Punnett square. It's so named because it was invented by someone called Punnett. It has absolutely nothing to do with baskets of strawberries. On the left, you have the chromosome of a particular pair inherited from the father. At the top, you have the chromosome of the same pair inherited from the mother. We're off mitochondrial DNA now, we're on nuclear DNA. So we're talking about chromosome pairs, and one of the father's chromosome pair and one of the mother's chromosome pair being inherited by the zygote that may eventually become a baby. The father being male and having XY genotype, the spermatozoa is going to deliver either an X chromosome or a Y chromosome. The mother being female and having XX genotype, the ovum is going to have an X chromosome. That produces on the upper row XX female, on the lower row XY male. But the X chromosome also carries one allele of a particular gene, allele being a version of a gene. And in this case, we have the black allele on the father's X chromosome, one black allele and one red allele on the mother's X chromosomes, which means if the offspring inherit the father's X chromosome, they're going to get one black allele. If they inherit the father's Y chromosome, they don't get an allele at all from the father. From the mother, they could inherit either an X chromosome with the black allele or an X chromosome with the red allele. That gives you these 4 combinations. Top left, 2 of the black allele, black. 2 X chromosomes with the black allele. Bottom left, 1 X chromosome with the black allele from the mother, Y chromosome from the father, still black. But top left is female, bottom left is male. Top right, X chromosome with the black allele from the father, X chromosome with the red allele from the mother. That is labelled on this diagram calico, which is Spanish or Portuguese or something and used in the USA. In Britain we call those tortoise shell. In the bottom right, the Y chromosome from the father, the X chromosome with the red allele from the mother, which produces orange or ginger. We can illustrate this with actual photographs. On the left we have the father, a black male cat. At the top we have the mother, a female tortoiseshell cat. And within the Punnett square we have quarters of their offspring, representative examples of their possible offspring. If over the course of a few years they have 32 babies, you would expect to get 8 of each of these. Upper left, female black cat. Bottom left, male black cat. Upper right, female tortoiseshell cat. Bottom right, little ginger idiot. Sorry, male orange cat. And that is how black and ginger and tortoiseshell fur colours and patterns arise in cats, at least in domestic cats. Just need to do that with the zoom to make sure that appeared on your screen. So, the black cats among this litter can be male or female. You get male black and female black kittens, both of which inherited the black allele from the mother. But if you get a ginger cat from this particular mating, that's going to be male. If you get tortoiseshell, that's going to have to be female, because tortoiseshell only happens when you have 1 black allele and 1 red allele of a gene that is found on the X chromosome, not on the Y. So to be tortoiseshell requires having 2 X chromosomes, which requires being female. Therefore, all tortoiseshell cats are female. It's just basic biology, dude. Given everything that's come up in this video so far, nobody should be surprised to find out that biology is not that simple. This slightly angry looking creature, probably psychotic because it's a domestic cat, that is Harry, the male tortoiseshell cat. Yeah. Oh, so I found one. So what? Yeah, meet Gunther, the male tortoiseshell cat. Look at that stripe. Look at that. Left and right divide. It's like one cell went black fur and one cell went ginger fur, and each of those cells divided and became half the fur on the face. Apart from that ginger eyebrow. I don't know whether he's adorable or horrible. Even has different fur length one side of the face from the other. But anyway, male tortoiseshell cat, they do exist. So there's that. Here's another Punnett square. Zooming in. And moving it so that you can still see it when I zoom in. That was too much zoom. There we go. This is a Punnett square with 2 chromosomes on each side. 2 chromosomes on the left, 2 at the top. 2 separate chromosomes. Now, as mentioned, randomized mixing happens with nuclear DNA, because which of the 3rd or 4th or 5th or 6th chromosome pair you inherit from the father, and which of the 8th or 9th or 10th or 11th or 12th chromosome pair you inherit from the father is completely independent of each other. So if in one chromosome pair, you have the father has a dominant brown allele and a dominant allele of the brown eye colour gene and a recessive allele of it. And in another chromosome pair, he has a dominant allele and a recessive allele of the gene for green eye colour. You could inherit both the dominant alleles or both the recessive alleles, or the dominant brown and recessive green, or the recessive brown and dominant green. Same applies to the mother. You could inherit any of those pairs from her. So you have a 4x4 grid, not a 2x2 here. The upper two rows are rows in which the offspring inherited the dominant brown eye colour allele from the father. Whichever chromosome pair it is that has that gene on it, they got the particular one of that chromosome pair that happens to have the dominant brown eye colour allele on it. Therefore they have brown eyes. The two columns on the left, likewise, but female. They inherited dominant brown eye colour from the mother, so they have brown eyes. The two columns on the right and the lower two rows didn't. They got the recessive allele for the brown eye colour gene. Therefore their eye colour depends on which allele of the green eye colour gene they got. And here we have not just green or not green. We have, if you only get one, if you get one dominant and one recessive, which is the lower left and upper right, you get pale green eyes, bright green eyes, or light green eyes, or sparkling green eyes if you want to be more romantic. Or eyes the green of sunlight through the first leaves of spring, or something like that. And in the upper left, you get, with both dominant green alleles of the dominant alleles of the green eye colour gene, you get dark green eyes, also known as hazel eyes. And these can be green and brown. I've seen eyes that are blue at the centre, then mostly green with brown around the outside. The very bottom right cell of this whole 4x4 grid is all four recessive alleles. And that's how you get blue eyes. To get blue eyes, you have two of the recessive allele of the gene for green eye colour and two of the recessive allele of the gene for blue eye colour. So your eyes don't go from blue to green or from blue to brown, they stay blue. And that's how human eye colour works. Here's an article about it. One of the most puzzling aspects of eye colour genetics is accounting for the birth of brown-eyed children to blue-eyed parents. This is a real phenomenon and not just a case of mistaken fatherhood. Based on the simple two-factor model, we can guess that the parents in this case are probably little b, big G, little g, which is homozygous for, meaning having two copies of, two the same of, the recessive brown eye colour allele, and heterozygous, meaning having two different alleles for the green. One dominant green, one recessive green, with a shift toward the lighter side of a light hazel eye colour. This is how the green gene was expressed so lightly that it didn't manage to turn their eyes from blue to green. But in the child who inherited both those dominant green alleles and something else, the green alleles managed to confer a brown eye colour. How? I suspect because the green pigment can become brown with the help of some other process which is only expressed very weakly, or maybe it's a recessive trait and they inherited both of that. It's on another gene, it's on another chromosome. But yes, blue-eyed parents can have brown-eyed babies. It doesn't mean someone else was the father. It means genetics is a little more complicated than that simple Punnett square back there. Now that we're into human genetics, let's get into human genetics on that 23rd chromosome pair. Here's where I get demonetised. Oh yeah. Because, as everybody knows, as we was taught in grade 4, just basic biology, dude. a father is a man who is male who has 46XY genotype. So that spermatozoon is going to deliver either an X chromosome or a Y chromosome. A mother is a woman who is female who has a 46XX chromosome, 46XX genotype or karyotype if you prefer. So the ovum is going to have an X chromosome, just one of those two, a copy of one of those two X chromosomes. Which means which chromosome you get from another doesn't affect your birth sex. It's just which one you get in that spermatozoon. If it delivers an X chromosome, your karyotype, genotype is going to be 46XX. You are going to be, not you, the baby produced, assuming this fertilized ovum becomes a zygote and implants and develops and becomes a fetus and eventually makes it as far as being born and drawing breath. If it gets 2 X chromosomes, it is going to be 46XX. It is going to develop female, which means having a vulva, a vagina, a cervix, a uterus, ovaries producing ova, the ones that keep their mitochondria, a female hairline with female pattern hair loss later in life, boobs, because those happen, a butterfly-shaped pelvis, very sloping, very high at the sides, very low in the middle, creased in the middle. Narrow hands, because we all know women have narrow hands, and no Adam's apple, because no woman has an Adam's apple at all, ever. And if that spermatozoon delivers a Y chromosome, the fertilized zygote, and therefore the baby, if it gets as far as baby, is going to have a 46XY karyotype, genotype, and therefore be male. Well, turn male during development, not as a single cell zygote. A single cell zygote is not male, but somewhere during fetal development, it's going to become male, which means the labia fuse and become a scrotum, the penis extends, the clitoris grows longer and is wrapped in skin and becomes a penis. There is a distinct prostate gland. The gonads become testes, which produce spermatozoa. This individual is going to have a male hairline, a male pattern hair loss, maybe at age 40 if they're lucky, maybe at age 17 if they're not. Not going to grow boobs because men don't have boobs. Have a shield-shaped pelvis without that crease in the middle. Very broad hands because men have gentle souls, butcher's hands. And a prominent Adam's apple, which all men have. Because it's just basic biology, dude. Right? Yeah. You're a fool if you think it's that simple this late in this video. No, it's not that simple. It's not that simple at all. For a start, there's Turner syndrome. 1 in every 2,000 baby girls isn't 46XX. Doesn't have a 46XX karyotype. They have 45X. They don't have 23 chromosome pairs. They have 22 chromosome pairs and a single X chromosome. And you can read the effects of Turner syndrome there on screen. Someone who only has one X chromosome may not be diagnosed until a girl fails to show sexual development associated with puberty, usually between the ages of 8 and 14 years. Up to that point, they're indistinguishable from 46XX girls. It's just not enough X chromosome to trigger female puberty, and somewhere around age 14 you start thinking it's kind of weird that things are happening to other girls and not happening to this girl. Other characteristics can vary significantly between individuals, so it's not a simple case of 45X it looks like this, 46XX looks like that. It's some girls are 45X, not 46XX. How on earth can this happen? I described the division of cells with the duplication of the whole genome, the separation of its one entire nuclear genome, nuclear DNA complement to each end of the cell before it divides, and then the separation of the chromosomes in each of those daughter cells, taking just one of each chromosome pair to each end of the cell before it divides into 2 gametes. Quite simply, it doesn't always happen like that. Sometimes the 23rd chromosome pair, both chromosomes go to the same end of the cell and end up in the same gamete, and you get a gamete with no 23rd chromosome. Either an ovum with no 23rd chromosome gets fertilized by a spermatozoon with the usual 23 chromosomes, If it delivers a Y chromosome, that is going to be an ovum with no X chromosome at all. That is not viable. 45Y doesn't happen. If it delivers an X chromosome, you get the 45X genotype. Now logically, or you get an ovum with 23 chromosomes fertilized by a spermatozoon with only 22. So then you definitely get 45X. I suspect only one of these is happening. I suspect that because I've seen the next slide. See, obviously, if you can have this division, this anomalous cell division that puts both of the 23rd chromosome pair chromosomes across into one gamete, that one can be the one that either fertilizes or gets fertilized by the other gamete. So you can also get 47XXX genotype, karyotype, trisomy X, triple X. Females with this condition may be taller than average. Yeah, so it's not necessarily a problem at all. It's, you might never notice. It even says in frequency, this condition occurs in about 1 in 1,000 female newborns, twice as often as 45X, suggesting that it only happens one way round for 45X, but it can happen both ways round for 47 triple X. No, it can't, because you can't get 2 X chromosomes from the father. So why twice? Because 47 triple X has an ovum with 2 X chromosomes, which is viable, and 45X with an ovum with no 23rd chromosome isn't viable, so it only happens if you get the X and the 0 from the male, maybe. It's a suspicion. I haven't investigated it. I haven't done research, but double the frequency is interesting. 5 to 10 people with trisomy X are born in the United States every day. So this isn't one male tortoiseshell cat in Scotland. This is 5 to 10 people every day just in the US. It's 1 in 1,000 female newborns. So, when you say, a girl is someone with a 46XX genotype, it's just basic biology, dude, you are quite clearly wrong. But oh, it gets better. Or worse, depending on your point of view. I'm going to call it better. See, if this incorrect division can happen, anomalous, let's call it anomalous division, like anomalous materials at the start of half-life, can happen, producing 45X or 47 triple X, it can also produce 45Y, which isn't viable, and 47XXY genotype, which is viable. 47XXY is usually, and it's often enough, it comes up often enough to have a usually attached to it, male with reduced fertility. Male, but not quite as male, because there's a lot more X chromosome driving female development relative to the amount of Y chromosome driving male development. But there have been cases of babies being born and identified as boys and named as boys and raised as boys and identified as boys and going through school as boys and going through male puberty and becoming men and meeting women and marrying them and getting them pregnant and raising those children and then finding out when those children hit puberty that those children have anomalous genotypes. And getting tested because their children have anomalous genotypes and finding out they are 47XXY, not 46XY. And up until that point, there was no reason to suspect. Right. What we have here is a report on PubMed of a 47XXY female. Yeah, that happens. And this is the third reported case of 47XXY with a female phenotype in spite of the presence of a Y chromosome and the normal SRY. Not just in spite of the presence of the Y chromosome, in spite of the presence of a Y chromosome and normal testis determining factor. See, we know that somewhere in those genes that produce proteins and signaling molecules and receptor molecules and hormone producing molecules and so on, that cause that change from female to male, we know that different mutations in there can cause that whole sequence to that whole cascade to just not happen. It's like a pinball machine. You've got all these things that can happen. If the ball never gets launched, it's not going to happen. If there's a blockage in the tube up which the ball gets launched, it's not going to happen. If that flipper there isn't plugged in, it's not going to happen. We know about us, but this is the third reported case when all the ways we know it can not happen appear to be functioning as, quote, normal, close quote. And we don't know why it didn't happen, but it clearly didn't. And then we get Swyer syndrome, a rare disorder characterized by the failure of the sex glands, testicles or ovaries, to develop. Meaning, if you go back to that Punnett square, on one row the gonads develop as ovaries, on another row they develop as testicles. Well, Swyer syndrome is when they don't. Swyer syndrome is classified as a disorder of sex development, which encompasses any disorder in which chromosomal, gonadal, or anatomic sex development is abnormal. Wow. So it's a pretty broad description there. I think they mean disorder of sex development is a pretty broad description. Girls with Swyer syndrome have an XY chromosomal makeup, as boys normally do, instead of an XX chromosomal makeup, as girls normally do. Despite having the XY chromosomal makeup, girls with Swyer syndrome look female and have functional female genitalia and structures, including vagina, uterus, and fallopian tubes. But they lack sex glands. They don't have ovaries, they have little bits of scar tissue. And because they don't have ovaries, they're not producing the hormones to send them through puberty, so that doesn't happen unless they get those hormones provided. But this is referring to babies that are, the baby comes out one way or another, and the doctor looks and says, oh yeah, that's a girl right there, and they get named as a girl and raised as a girl, and they identify as girls, and they go to school as girls, and for, up until, 8 to 14? Nobody has any reason to believe that this is anything other than 46XX girl. And then puberty just doesn't happen, and then you eventually find out, via a whole lot of medical tests by actual medical professionals, not liars who own their own churches, or weirdos who write for church magazines and hate everybody, but actual medical professionals with actual qualifications from real universities, not trailers in the desert, do suitable tests to figure out what's going on, and they eventually find out that this girl has a 46XY genotype. Got an actual example here. In the Journal of Clinical Endocrinology and Metabolism. This is on PubMed. Wonderful website. Published, 15 years ago? Nearly 16 years ago now. Well, it was published online more than 16 years ago, but it's dated just under 16 years ago, which is kind of strange. Report of fertility in a woman with a predominantly 46XY karyotype in a family with multiple disorders of sexual development. Miroslav Dumik, Karen Linsou, Natasha Leibel, Serko Siglar, Giovanna Vinci, et al. Et al, yeah, and others. Right. The abstract. It's good to put an abstract. It means people can quickly read what this is about and decide whether or not to read the whole thing. The title's right there. If you want to read the whole thing, you can look it up. I don't even have to remember to put a link in the description. We report herein a remarkable family in which the mother of a woman with 46XY complete gonadal dysgenesis was found to have a 46XY karyotype in peripheral lymphocytes, mosaicism in cultured skin fibroblasts, 80% 46XY and 20% 45X, and a predominantly 46XY karyotype in the ovary, 93% 46XY, 6% 45X. Oh yeah. This is one of those cases where they found out because the offspring went to the doctor and said, look, some girls start later than others, ain't really cutting it. I'm 17 and nothing started yet. Only she didn't say it in English because she was in Croatia. Or from Croatia, at least. 39-week gestation, perfectly normal. Delivered by caesarean section due to a maternal hip fracture isn't necessarily normal, but it does happen quite a lot. Caesarean sections are done all the time. There's nothing really unusual about that. Birth weight 3.8 kilograms, perfectly healthy. Length 52 centimeters as far as I'm aware. That's perfectly normal size for a newborn baby. Breastfed for 1 year, and to the best of my knowledge, that's fairly normal, usual. Sought medical attention at age 17. And that phrase already tells you it took 17 years for she's different to actually become obvious enough for anybody to go and say, excuse me, doctor, but I'm different. Because of lack of breast development, primary amenorrhea. Amenorrhea is not having periods. Things that all the other girls in her class were presumably experiencing for several years before she went to the doctor and said, this is more than just slow, this is more than just late here. Intelligence was normal, determined by her standing as a top student in her class, so if any of those previous slides said, learning development may be delayed or learning difficulties may be present, not in her case. On exam, so this is a medical professional here, someone who knows about this stuff, examines this patient and describes her as an articulate, tall, thin woman. Height 187 centimeters, that is tall, but it's in the top 20th of the Croatian population. Mid-parental target height of 181 centimeters, so she was taller than the average of her parents' height. That happens all the time too. Her weight was 68 kilograms, 187 centimeters tall, 68 kilograms. Yeah, it's thin. It's not ridiculously low weight for that height. Sounds healthy to me. I haven't checked the charts. She had a normal frontal hairline. So, if you get a 46XX genotype with a female hairline, yeah, she had. Mild facial acne, it does happen to girls. No facial hair, which you would expect if she was a boy. Tanner stage 1 breasts, which means she had the breasts you'd expect on a 5-year-old. Tanner stage 4 pubic hair, she had the pubic hair you'd expect on a 25-year-old. So, some of puberty has happened, but puberty going from girl to woman hasn't. External female genitalia were normal. So, just as happened when this girl was born, a doctor looked between her legs and said, yep, that's a girl. Without clitoromegaly or labial fusion. I mentioned that clitoris grows much longer and gets wrapped in skin and becomes a penis in the conversion from female to male within the womb. Actually, it's not always within the womb because guava dotches exist. Sometimes it waits 12 years and then happens. Or labial fusion, which is where the outer lips fuse together and become the scrotum, the ball bag to give it a crude name. The vaginal introitus was normal, so this doctor went a little more further than looking and still found, yep, that's a girl. Pelvic examination revealed a hypoplastic uterus with no palpable gonads. That is the first line that says, oh, this girl isn't quite like other girls, apart from the lack of breast development and primary amenorrhea. Bone age was 14 years to chronological age of 17 years. Great, her bones are slightly younger than her age. It's probably nice. Means osteoporosis might happen later. Karyotype on peripheral blood performed twice was 46XY. Karyotype is checking what chromosomes are there. Performed twice means that the doctor said, nurse, take a blood sample from this patient and this, that and the other, and checked what chromosomes are there and saw a 46XY karyotype and went, nah, no way, throw all of that out. Fresh set of kit. The other arm will take a blood sample from that side instead, with a fresh needle and a fresh syringe and a fresh everything and a fresh kit, and it's still 46XY. Wow. See, this patient was so very obviously girl that medical professional examining her got as far as seeing a 46XY genotype, went, nah, can't be right. Further investigation revealed multiple family members on the mother's side, and this is where we get into, the full report is actually about the mother and the mother's family more than about this girl. But everything about this girl identifies her as girl, clearly. Or woman, as described in this report. According to some bills that certain creepy old men have attempted to pass, it would become a felony in some US states for her to use the girls' changing rooms, because having a 46XY genotype means she's a boy and has to get changed with the boys. Does anybody here think that would be a good idea? Forcing her to change with the boys. After she spent 17 years as a girl and identifies as a girl and is known as a girl and has been with the girls the whole time and all the boys consider her a girl and she looks like a girl and feels like a girl unless you happen to check in just the right place and know what to expect. I don't think forcing her to identify as a boy would be a really healthy idea. Like, at all. And now it comes time to introduce Nature magazine. These are 6 covers of Nature magazine, just to have something for you to look at while I talk about it. This is a scientific publication, as you can probably guess by the covers shown. And it publishes papers by various scientists who send them in. This is not the only, open quote, scientific journal, close quote, on the planet. But Nature is, well, not like other girls. Now, Nature is not like many other publications. There are some out there where you can pay to have your work published. You send your paper in, you send in a fee, they will publish your paper. And that's how they fund it, so they'll publish it in as many places as they can get away with publishing it. And that's pretty much it. There are also some out there, like Answers in Genesis, for which Mike Johnson, Speaker of the US House of Representatives, has written in the past, which will publish any old guff, but you have to swear an oath that you believe that the earth is only 6,000 years old and that every story in the Bible, including the contradictory ones, is absolutely true, and that all kinds of other stuff, and that even if you find evidence that disproves that, you won't publish it. And that what you're printing, what you're sending in for publication, does support that. So you have to promise to lie to get published in Answers in Genesis, and you have to be full of hate, and you have to be willing to swallow some obvious nonsense. To get published in Nature is a little different. Nature isn't funded by people paying to be published in Nature. Nature is funded by people paying to be able to read it. University libraries pay to have the latest issue of Nature there for people to read. And research firms pay to have all the latest issues of Nature there for people to read, because they want to know. They want to know what research is being done, what findings are being found, what discoveries are being made, and so on. And when you send something into Nature to be published, they don't print it. First they look at it and they decide for themselves whether they think it's even worth the effort and the cost. And then if they think it is, they send it out to experts in the field. If you are writing a paper about dentition in gibbons, or the difference in dentition between male and female gibbons, Erica can tell you a lot more about the subject than me, and you send it in, they will send that paper to somebody who is an expert in the field of gibbon dentition. They will find as many experts in the field as they can and send this paper to all of them and pay them to read it. This is a job you can get with a really good degree, a postgraduate degree from a really prestigious university, not a trailer in the desert, reviewing other people's work. Why would you do this when you could be out there doing research? Because contrary to what flat earthers might want you to believe, the government doesn't have a big bucket of money and just hand it out to graduates. You can't go up to the government department and say, "Hello there, my good man. Can I come in for a moment? I want to research the effects of tetrahydrocannabinol on rats' ability to solve mazes." And reasonably expect to be handed £5 million. Just, here you go and build yourself a lab and a whole load of mazes and a rat breeding facility and your own secure cannabis farm and, breed rats and feed some of the population different doses of this at different stages in development, because obviously you want to research what effects it has if it's fed to a rat while she's pregnant, what effects it has on her babies, what effect it has on a growing rat that hasn't reached adolescence yet, what effect it has on an adult rat, how long it takes the effects to wear off, and the effects of different doses at different frequencies. So you'd need a heck of a lot of rats, you would need a huge rat breeding facility, you would need a huge laboratory with all your mazes to test. You would need a phenomenal supply of treats with which to reward the rats, as well as just food and bedding and the standard toys for them. You'd need a lot of money. You can't just go to the government and say, I've got this idea, and reasonably expect to be handed whatever it's going to cost. Now, the government has a fund, and they fund research. And you go to them and you say, I've got this idea. And they say, well, what use is it? And you have a very long, hard time explaining why your research is going to be sufficiently beneficial to the country to justify the government spending the people's money on your research and you. And at the end of it, they say, who the heck are you anyway? And you go, I'm a graduate. Yeah, we've got hundreds of thousands of those. We have thousands of fresh new graduates every year. Who are you? If you have nothing to your name, they laugh you out of the hall, probably, unless you've a really good presentation of a really interesting idea. If you are a published research scientist and your name is known and you are one of these people really look forward to hearing from whom people really look forward to hearing, good for you. You have a chance to get one of these huge amounts of money where you can set up your own facility and do your own research, really do your own research, not watch YouTube videos. And, produce these research papers and send them in for publication. If you are not that guy, that man or woman or in between or whatever, the person who got that research fund in this field, the field in which you have got your qualifications, the field in which you are an expert, just not the most prominent expert, and you missed out on that research grant because somebody else got it, what do you want to do? What is the one thing you really, really want to do this year? You want to read a paper that the top expert in your field who did get the research grant sent in for publication and find a mistake. You want to find something, another explanation that the top expert in your field has overlooked, or a mistake in the technique, a place where something else could have crept in and changed the results, or some other explanation can account for what they found, or something invalid in their explanation. And you want to be the person who exposed the former top expert in this field's mistake, because then you're the top expert in this field and you get the next research grant. So if something is printed in Nature, it has been sent out to a whole lot of people who tried really hard to find mistakes in it. This, I think, is worth pointing out about Nature before we read an article from Nature, or at least parts of an article from Nature. I'm not going to read you the whole thing. Here is that article in Nature. This is just the abstract. This is just the short, simple version that you read quickly to decide whether you want to read the rest of it. Yeah. Stuff published in Nature is to the things we were taught in the 3rd grade. Like an actual flight simulator that can accurately simulate thermal updrafts and winds being deflected upwards by mountains and the changes in humidity and density due to all of that, and cloud formation and rain and snow effects and stratospheric winds and polar vortices and the gravitational effects of the moon and Jupiter and all of its moons and Mars and its moons and Venus and Mercury and Saturn, Uranus, Neptune and Pluto and the Sun and everything else, and fuel burn rate and the shifting centre of mass of the aircraft due to fuel burn rate and flexing of the wings and everything else is to the symmetrical parabolic arc of similar Abel's arrow on the GCSE mathematics paper. The abstracts in Nature get long. So to translate this into plain English, these genuine scientists trained a computer to look at living people's brains with the aid of one of those MRI scanner machines, and to guess whether that living person is male or female. And with cisgendered individuals, people who were born male and identify as male, these are people who fit in every sense into one row or the other of that very simple Punnett square, XY versus XX. It got really good. But it gets confused by transgender individuals because their brains are actually different. Yeah. From both. Ever heard of heart transplant? You can have somebody else's heart beating in your chest, you're still the same person. You can lose both legs in a horrific motor vehicle accident or a rocket-propelled grenade incident in Afghanistan. You're still the same person. You can have to have a kidney removed due to cancer. You're still the same person. You can have to have your entire reproductive system removed due to cancer and still be the same person. But your brain? Oh, that's who you are. And scanning the brain, in cisgendered men and women, it's really easy to say, yep, that's a man, that's a woman. But not in transgender individuals. Their computer got confused. Which means it's real. There really are differences in the actual part of the body that defines who someone is as a person, the brain. Physical differences. Analysis, getting more detailed than the abstract. And I'm not going to read the whole thing to you. I'm just going to let you take a look at that and look it up yourselves if you really want to. And the conclusion. In this study, we present a highly accurate biological sex classifier in cisgendered individuals that shows a significantly decreased accuracy in transgender individuals. Based on our brain structural data, we suggest a dimensional rather than binary gender construct. Real scientists who really publish in the really prestigious Real Science journal that people pay to read because it's that good, suggest a dimensional rather than binary gender construct. It's right there in black and white. And in case right there in black and white wasn't good enough for you, it's right here in white and black. Gender isn't binary. And they say this will contribute to the destigmatization of transgender individuals. So if you are trying to stigmatize transgender individuals by saying that gender is a binary, you are the one going against science. And that was the final slide. Thank you for sticking with me this far, if you did. Thank you for skipping to the end rather than just leaving, if you did that. As a reward, you get the view from the side door of Erebor at the last light on Durin's Day. And between you and me, thank you for watching.